Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr. Fazullah. In this video, we shall study a full course, Complex Variables and Transform, with code MATH-232. These are the contents of this course. Let us start from the introduction of complex numbers.
In this lecture, we shall study the basic concepts of complex analysis, complex numbers. At the end of this lecture, we will have the knowledge of at least these topics, which you can see on the screen. Complex numbers. Let us start from the solution of a very simple problem. X square plus 1 equal to 0. If I solve this equation, I get a solution x is equal to minus 1 under the root. This minus 1 under the root is not a real number, and it is denoted by iota. Now if we multiply iota with any real numbers, as a result, we get another number, and that number is called an imaginary number. For example, 2 is a real number, but if I multiply this with iota, then 2 iota is an imaginary number. Under root 3 is a real number, but if I multiply this under root 3 with iota, I will get this number, which is an imaginary number. If we add or subtract a real and imaginary number, the result is a complex number. For example, 2 plus 3 iota is a complex number. Minus 1 over 2 iota is a complex number. Generally, a complex number is denoted by z, and it is given by x plus iota y. This x is called the real part of the complex number z, and this y is called the imaginary part of the complex number z, which we can write that real of z is equal to x and imaginary of z is equal to y. Argand diagram: any complex number z is equal to x plus iota can be written in the form of an ordered pair, and hence we can plot this on the xy axis with the real part on the x-axis and imaginary part on the y-axis. Let this x, small x is here and small y is here, so the point where they intersect each other, that point is x comma y, which is equal to z. This graphical representation of the complex numbers is called the Argand diagram. For example, let us express a complex number z is equal to 2 plus 3 iota on the Argand diagram. Then, like in the previous classes, we have to take 2 along the positive x-axis. So this is 1, this is 2, and 3 along the y-axis, 1, 2, 3. Now the point where they intersect each other, that point is z is equal to 2 plus 3 iota. Modulus of a complex number. A modulus of a complex number z is equal to x plus iota y is denoted by z absolute or by small r and is defined as follows. Z absolute is equal to a real part of z whole square plus imaginary part of z whole square under the root. Or we can write that z absolute is equal to a real part is x. So x square and imaginary part is y square under the root. Now let us solve an example. The example is, let z is equal to 2 plus 3 iota. Find its modulus. So its modulus is 2 square plus 3 square under the root, which is 13 under the root. It is the distance of the point xy from the origin. Let us see it on the Argand diagram. If this is a point z is equal to x plus iota y, then r or z absolute is that distance which is from the origin to that point. Argument of a complex number. Again, let z is equal to x plus iota y. Then what do we mean by the argument of this complex number z? An angle between r, which is also called the position vector, and the positive x-axis is called argument of the complex number z. And usually we obtain this by taking tangent theta. Tangent theta is equal to perpendicular divided by base, and from here we can get that theta is equal to tangent inverse of y by x. So this theta is called argument of the complex number z. Let us solve an example. If z is equal to 3 plus 3 iota, then find its argument. So its argument can be obtained by using tangent theta, which is equal to perpendicular over base. So real part is 3 and imaginary part is also 3. So from here we can get that theta is equal to tangent inverse of 1. And we know that tangent inverse of 1 is pi by 4. So this is the required solution. Conjugate of a complex number. So the conjugate of a complex number x plus iota y is denoted by z bar, and it is defined as x plus iota y whole bar, which is equal to x minus iota y. So you can see that the conjugate only changes the sign of the imaginary part. Let us see some examples. Let z is equal to 2 plus 3 iota. Find its conjugate. So its conjugate z bar is equal to 2 minus 3 iota. Let us write another one. Z is equal to 1 minus 4 iota. So its conjugate is 1 plus 4 iota. Addition and subtraction of complex numbers. If we want to add or subtract two complex numbers, z1 is equal to a plus b iota and z2 is equal to c plus d iota, the rule is to add or subtract the real and imaginary parts separately. Such as, if I have to add z1 with z2, I will add a with c, so the answer is a plus c, and then I will add imaginary parts, so I will get b plus d. Similarly, if I have to subtract z2 from z1, I will subtract c from a and then I will subtract d from b. For example, let us take z1 is equal to 4 plus 3 iota and z2 is equal to 2 plus iota. Then z1 plus z2 is equal to, add real parts, 4 plus 2 is 6, and then add the imaginary part, 4 iota. If I have to subtract z2 from z1, then subtract the real part of z2 from the real part of z1, I will get 2, and subtract the real part of z2 from the real part of z1, so I will get 2 iota. Multiplication of complex numbers. We multiply two complex numbers, z1 is equal to a plus b iota and z2 is equal to c plus d iota, just as we multiply two expressions. For example, let us multiply z1 with z2. This is equal to a plus b iota and this is equal to c plus d iota. We have to multiply a with c and d, so we will get ac plus a d iota. Now we have to multiply b iota with c and d iota, so we will get b c iota and plus b d iota square. But we know that iota square is equal to -1, so this will be minus b d iota, so we can write ac minus b d, and taking iota common from here we can get ad plus bc. Some people remember it as a real with real minus imaginary with imaginary, plus iota, a real with imaginary plus imaginary with real. And now let us see an example. The example is, let z1 is equal to 4 plus 3 iota and z2 is equal to 1 plus 2 iota. Then just multiply these two expressions. So z1 into z2 is equal to 4 plus 3 iota into 1 plus 2 iota. And if we multiply 4 with 1, we will get 4, then plus 8 iota. Now we can multiply 3 iota plus 6 iota square, but we know that iota square is -1, so this is -6, and we can get that this is -2 and plus 11 iota. Division of complex numbers. Let we have two complex numbers, z1 is equal to a plus b iota and z2 is equal to c plus d iota. Then the rule is to multiply the top and the bottom with the conjugate of the denominator. It means if I have to find z1 over z2 divided by z2, then this must be equal to z1 over z2. This is top, this is bottom, but we have to multiply the top as well as the bottom with the conjugate of the denominator. For example, in this case I can write that z1 over z2 is equal to a plus b iota divided by c plus d iota. So what I have to do, I will multiply the top and the bottom with the conjugate of this denominator. So the conjugate of this is c minus d iota, and again c minus d iota, and after simplifying we will get the answer. So let us see an example. Let we have two complex number. Z1 is equal to 4 plus 3 iota and Z2 is equal to 1 plus 2 iota. Now we have to find Z1 divided by Z2, which is equal to 4 plus 3 iota divided by 1 plus 2 iota. Now the rule is to multiply the top and the bottom with the conjugate of the denominator. So just multiply these two expressions. If I multiply, I will get 4 minus 8 iota plus 3 iota minus 6 iota square and divided by, you can see this is formula a plus b into a minus b. So we can get 1 square and minus 2 iota square, which is plus 4. Now let us simplify this. This is plus 6, so we will get 10 here, and from here we can see this is 5 iota divided by 5. And if I simplify this, I will get 2 minus iota, which is the required solution. Polar coordinates of a complex number. Let z is equal to x plus iota y is a complex number which is in the Cartesian coordinates. Then this complex number has the polar coordinates r comma theta. Now let us express this complex number into the polar coordinates. We draw the Argand diagram. This is x, this is y, this one is theta, and this one is r. So from this figure we can obtain that cos theta is equal to x by r, and from here I can get that x is equal to r cos theta. Again from here I can get that sin theta is equal to y by r, which gives that y is equal to r sin theta. So the complex number z, just put the values of x and the value of y. So this complex number can be written as r cos theta plus r iota sin theta. Now if I take r as a common, I can get z is equal to r into cos theta plus iota sin theta, and this is called the polar form of the complex number z. Let us solve an example. The example is to express the number z is equal to 1 plus iota in the polar form. So to express this in the polar form, we need r and theta, where r is the modulus, and we know that r is equal to x square plus y square. So x is 1, y is 1, so 1 square is 1, 1 square is 1. We will get that r is equal to under root 2. And we have to obtain theta. Tangent theta is again 1 by 1. So from here we can get that theta is equal to tangent inverse of 1, which is equal to pi by 4. So now just put these values and we will get that z is equal to under root 2 into cos theta plus iota, sorry, theta is pi by 4 and plus iota sine theta is pi by 4, and this is the required solution for this problem. Exponential form of the complex number and Euler formula. So let us start from the famous Euler formula, which is given by e power iota theta is equal to cos theta plus iota sine theta. This is the Euler formula. Its proof is very simple. Let us see the proof. We know by the Taylor series that e power z is equal to 1 plus z square divided by 2 factorial and plus up to so on. So according to this formula, now let us take left hand side. So left hand side is e power iota theta. Let us use this formula and expand this. So by using this formula we can get 1 plus iota theta minus theta square divided by 2 factorial plus iota theta cube divided by 3 factorial and plus up to so on, keeping in mind that iota square is equal to minus 1. Now this is our equation number 1. Now we also know from the Taylor series that cos z can be written as 1 minus z square divided by 2 factorial plus z4 divided by 4 factorial and minus up to so on. Similarly, from the Taylor series we know that sin z is equal to 1 minus z cube divided by 3 factorial plus z5 divided by 5 factorial and minus up to so on. Now let us take the right hand side of this formula, which is cos theta plus iota sine theta. So in a similar way, just expand cos theta according to this one and sine theta according to this one, and after the simplification you will get that this is equal to this thing plus up to so on, which is 2. So from 1 and 2 we can see that e power iota theta is equal to cos theta plus iota sine theta. Now this is a very important result. With the help of this result we can express a complex number into the exponential form. Let us see a complex number in the polar form. So in the polar form we have z is equal to r cos theta plus iota sine theta. Now according to this formula we can write that cos theta plus iota sine theta is equal to e power iota theta. So this is the exponential form of a complex. Multiplication of complex numbers in polar form. We have two complex numbers. Z1 is equal to r1 cos theta 1 plus iota sine theta 1. And z2 is equal to r2 into cos theta 2 plus iota sine theta 2. An easy way to multiply these two complex numbers is that first of all we have to convert them into the exponential form. Like z1 can be written as r1 e power iota theta 1 and z2 can be written as r2 e power iota theta 2. Now it's very easy to multiply these two numbers. So if I multiply, I will get r1 into r2 and you can see the bases are same, so I have to add the exponents. So by adding the exponent, I will get that this is r1 r2 e power iota theta 1 plus theta 2. And now you can express this again into the polar form. So you will get r1 into r2, and this is equal to cos of theta 1 plus theta 2 plus iota sine of theta 1 plus theta 2. So this is the multiplication of two complex numbers in the polar form. Similarly, to multiply two complex numbers, to divide two complex numbers in the polar form, we will do the same procedure like z1 over z2. First of all, we have to write them in the exponential form. And now this is equal to r1 e power iota theta 1 divided by r2 e power iota theta 2. And from here I can get that this is r1 over r2 e power iota theta 1, and the bases are same, so it will be subtracted iota theta 2. And from here I can write that this is equal to r1 over r2 and e power iota theta 1 minus theta 2. So now you can convert this again into the polar form. So you will get r1 over r2 into cos of theta 1 minus theta 2 plus iota sine of theta 1 minus theta 2. So this is the required division of two complex numbers in the polar form. Let us solve this example. Express z1 is equal to 1 plus iota and z2 is equal to under root 3 plus iota in polar form, and then find its multiplication and division. So first of all, from the first complex number, we have to obtain r. So r is equal to 1 square plus 1 square under the root, which is 2. And we have to obtain its angle. So angle is theta is equal to tangent inverse of 1 by 1, which is equal to pi by 4. So now we can express this number as z is equal to z1 is equal to r1, which is under root 2, and cos of theta 1, which is pi by 4 plus iota sine pi by 4. So this is the polar form of the first complex number. Now let us see the second complex number. For the second complex number, this is r1. So let us obtain r2 from the second complex number. Under root 3 square plus 1 square, this is 4. 4 under root is 2. So r2 is equal to 2. And now let us find the angle. The angle is tangent inverse of 1 over under root 3. So now 1 over under root 3 is equal to pi by 6. So we can write that z2 is equal to 2 into cos pi by 6 plus iota sine pi by 6. Now these are two complex numbers. They are in polar form and we have to find their multiplication. So the rule is same. Just express them into the exponential form. So we will get this thing, and similarly express this into the exponential form by using the Euler formula. You will get that this is equal to this one. And now we have to multiply z1 into z2. So z1 into z2, this is under root 2 into 2, and now e power iota pi by 4 into e power iota pi by 6. So as the bases are same, the power must be added and we can get e power iota pi by 4 plus pi by 6. And if I add these numbers, I will get 2 under root 2, and this is e power iota. And e power iota, if I take the LCM will be 12. So I will get 5 pi by 12. And now you can express this again into the polar form, which is 2 into 2 under root, and this is cos of 5 pi by 12 plus iota sine of 5 pi by 12. And this is the required multiplication for the two complex numbers. Similarly, we can divide these two complex numbers. So the division is z1 divided by z2. Again, z1 is under root 2 and this one is 2. So z1 under root 2 e power iota pi by 4, and this is 2 e power iota pi by 6. So if I simplify, I will get 1 over under root 2, and from here I can get iota pi by 4 minus pi by 6. Again, if I take the LCM will be 12. So I can get that this is equal to 1 over under root 2 e power iota, and pi by, if we simplify these two numbers, we will get that this is equal to pi by 12. So pi by 12, and if I express it again into the polar form, I can get 1 over under root 2 into cos of pi by 12 plus iota sine of pi by 12. So this is the required division of two complex numbers. De Moivre's formula. It is a very useful formula and important in the complex analysis. With the help of this formula, we can evaluate the complex numbers which have different powers. So let us write the statement of this formula. Let z is equal to cos theta plus iota sine theta be a complex number. Then with the help of De Moivre's formula, we can write that cos theta plus iota sine theta whole power m. This is equal to cos m theta plus iota sine m theta, where m is 0, plus minus 1, plus minus 2, and up to so on. Now we can use this formula to evaluate this complex number. This is a complex number 1 over 2 plus 1 over 2 iota whole power 8. So here let z is equal to 1 over 2 plus 1 over 2 iota. So first of all, we need to convert this number into the polar form. So into the polar form, first of all, we need r. R is equal to this square plus this square under the root. So if you do this process and simplify, you will get r is equal to this thing. And similarly, theta is equal to tangent inverse of 1 over 2 divided by 1 over 2, which is 1. So you will get pi by 4. And now in the polar form, I can write that z is equal to under root 2 divided by 2 into cos of pi by 4 plus iota sine pi by 4. And now what is z? Z is 1 over 2 plus 1 over 2 iota, but I need its whole power 8. So this is equal to under root 2 divided by 2 whole power 8 into cos pi by 4 plus iota sine pi by 4 whole power 8. So now we can use the de Moivre's formula to evaluate this thing. So by the de Moivre's formula we can write that first of all, if you simplify this, you will get this is 2 power 4 divided by 2 power 8, and from here we can get that this is 8 into pi by 4 by the de Moivre's formula plus iota sine 8 pi by 4, and if we simplify this we can get that this is equal to 1 over 2 power 4 into cos 2 pi plus iota sine 2 pi, and if I simplify this I will get 1 over 16. Cos 2 pi is 1 and sine 2 pi is 0. So we will get that the answer is 1 over 16. That is all.
Complex functions, limits and continuity. So let us start from the definition of a complex function. A relation between two sets of complex numbers in which each element of first set is connected to a unique element of the second set is called a complex function. From the definition, it is clear that if we replace the word complex by the word real in this definition, we can get the definition of a real. The main difference between the complex function and real function is that this function is a particular type of relation between two sets of complex numbers, and a real function is that particular type of relation between two sets of real numbers. So that is why we can also define a complex function as a function whose domain and range are sets of complex numbers. If we have a function f from z1 to z2, then z1 is called its domain, z2 is its range. If z1 and z2 both are sets of numbers, then this is called a complex function. And if z1 and z2 are sets of real numbers, then this is called a real function. A complex function is represented by f of z is equal to u plus iota v, where u is a real part of this function and v is called an imaginary part of this function. Here z is equal to x plus iota y is a complex numbers. And let us see some definition of complex function. F of z is equal to x square plus iota y square. This is a complex function. F of z is equal to sine z. This is another complex function where z is equal to x plus iota y. F of z is equal to log z is a complex function where z is equal to x plus iota y. And now let us start from the limits of a real function. Before to define the limits of a real function, let us explain it by an example. In this example, we have a real function f of x is equal to x square minus 4 divided by x minus 2. And we have to find its limits at the point x is equal to 2. Now we can find its limits at x is equal to 2 from left hand side and also from the right hand side. So you can see if I put x is equal to in this function, I will get 0 by 0, which is an indeterminate form. So let us simplify this function. We can use the formula of a square minus b square, which is equal to a minus b into a plus b. And
After cancelling x minus 2 with x minus 2, we can get that f of x is equal to x plus 2. To find limits at x is equal to 2, you can see that we can go towards 2 from left hand side. So we can put 1.8 in this function. Then we can go a little more near towards 2 and put 1.9 in this function. We can go a little more near towards 2 and we can put 1.99 in this function, and so on. And we can see the behavior of this function, that to which side f of x is approaching. So let us start from the left hand limit. If we put x is equal to 1.8, we can see 1.8 plus 2, we can get 3.8. So f of 1.8 is equal to 3.8. If we put x is equal to 1.9 in this function, we can get 3.9. If we get put x is equal to 1.99, we can get 3.99. So we can see that as x approaches towards 2, the value of the function is going towards 4. So let us put one more point which is more near towards 2. X is equal to 1.999. And as a result, we can get a number 3.999. So from this we can say that as x approaches to 2, in the result of this, the function f of x approaches to 4. And that is called the limits, which we can symbolically write like this one. Limit x approaches to 2, f of x is equal to 4. This minus sign shows that we are taking left hand limit. And from here we can define the limit of the function. So the definition is that we say that the limit of the function f of x is 4 as x approaches to 2 if the value of the function f of x can be made as close to 4 as we wish. The value of x very, very close to 2. And now let us see the right hand limits of this function. So now we are going from the side of 3. So I will put 2.1 in this function, then I will put 2.01, then 2.001, and we will examine the behavior of this function. So let us put x is equal to 2.1. If I put 2.1 here, 2.1 plus 2 is 4.1. So as a result, we get 4.1. If x is equal to 2.01, it gives 4.01. If I put x is equal to 2.001, as a result, I get 4.001. So we can see that as we go towards 2, the value of the function is going towards 4. And let us put another number, 2.0001. And we can get that the value of the function is very near to 4. It is 4.0001. So we can say that as x approaches to 2, as a result, the value of the function f of x goes to 4. And we can write this in the symbolical form that limit x approaches to 2, f of x is equal to 4. And this plus sign shows that we are taking a right hand limit. And from here we can define the limits of a function. The value, we can say that the limit of the function f of x will be 4 at x is equal to 2 if the value of the function f of x can be made as close to 4 as we wish, close to 2. Now let us see the definition for the limits of a real function. Here, instead of 4, we use a general number L, and for 2, we use a general number x naught. So the limit of a real function f of x is a real number L as x approaches to a real number x naught. That is, limit x approaches to x naught, f of x is equal to L if the value of the function f of x can be made as close to L as we wish by taking the value of x very, very close to x naught. And now, if we just replace the word real by complex, we can get the definition for the limits of a complex function. If left hand limit is equal to right hand limit, this will imply that limit exists. And now let us see the definition for a complex limits of a complex function. We say the limit of a complex function f of z is a complex number w as z approaches to a complex number z naught. That is, limit z approaches to z naught, f of z is equal to w. If the value of f of z can be made as close to w as we wish by taking the value of z very, very close to z naught. Here we have to note that the main difference in the case of limits for a complex function is that we can take these limits along several paths. And if we have unique solution along all paths, we will say that the limits of a complex function exist. For example, look at this figure number A. In figure A, this is a real number 2, and we can only limits from only two sides. We can come from right hand side, we can also come towards 2 from left hand side. But let us take a complex number and look at figure B. In this figure B, I have a complex number z is equal to 2 plus 2 iota, which is 2 comma 2. So this point is here inside the complex plane. Now I can come towards this point along this red path. This is one direction. I can also go towards this point from the origin along this blue path. I can also go towards this point from a line from this black path, which is parallel to y-axis. Similarly, I can take limits at this point while coming from the above and also from the right hand side. So there are several paths to find limits of a complex function at a point. And if all these limits have a unique solution, we will say that the limit exists. Otherwise, we will say that the limits does not exist. Let us see the limits of a complex function by an example. We have to find limits of the function f of z is equal to z square plus z plus 1 as z approaches to 1 plus 2 iota along path 1, which is parallel to the x-axis coming from the right, along path 2, which is parallel to the y-axis coming from above, along path 3, which is the line joining the point 1 plus 2 iota to the origin, coming from the origin. So let us solve this example. Solution of part 1. To find limits of this function, we need three things. We need a function which is given. We need a point at which we have to find its limits, which is 1 plus 2 iota. It is also given. And we need a path which is given parallel to the x-axis coming from the above. So we need this path. So to find equation of this path, let me show you figure number 1. Now, in this figure, first of all, let us represent the point. The point is z is equal to 1 plus 2 iota. This point lies here. We have to find a line which is parallel to the x-axis and coming from the right side. So this red line is that line. We can see it is coming from the right hand side and it is parallel to the x-axis. But we need equation of this line. To find equation of this line, first of all, you have to put z is equal to x plus iota y. Now look at this line. At this line, y is fixed. Y is equal to 2. So y is fixed. But x is a variable. Infinity towards this point. So we can say just put y equal to 2 in z is equal to x plus iota y. So you will get equation of this line, which is z is equal to x plus 2 iota. So this is equation of this line. And now let us find its solution. So along path 1, z is equal to x plus 2 iota and f of x is already given. So we have to put z equal to x plus 2 iota in this function and we can simplify this. And after simplification, we can get square plus x minus 3 plus 2 into 2x plus 1 iota. Now we have to take limits on both sides. The limits are z approaches to 1 plus 2 iota. Now what is z? Z is x plus iota y. So let us replace z by x plus iota y, which means that x is approaching towards 1 and y towards 2. But there is no y in this equation. So we can only use the limits as x approaches to 1. So if I put x is equal to 1, we will get the solution, which is minus 1 plus 6 iota. And now let us find the solution of 2, which is a line parallel to the y-axis coming from above. So first of all, this line, let us again see another figure. Let us see figure number 2. In this figure, we have to draw a line parallel to the y-axis coming from above. So this green line is parallel to the y-axis. It is coming from above and touching this point. So now we have to find equation of this line. And we can see that at this line, x is fixed. X is equal to 1. Throughout this line, x is equal to 1. But y is changing. Y is coming from infinity towards this point. So just put x is equal to 1 and z is equal to x plus iota y, and we will get equation of this line, which is equal to 1 plus iota y. Now let us see the solution. So along path 2, z is equal to 1 plus iota y, and the function is given in the question. So we have to put this z is equal to 1 plus iota y inside the given function and simplify this. After simplification, we can get 3 minus y square plus 3y iota. And now we have to take limits on both sides. So taking limits, z approaches to 1 plus 2 iota, but you can see on the right hand side, there is no x. So from here, we can only take the limits of y. So y is approaching to 2. If we put y is equal to 2 in this equation, we can get the solution, which is the same, minus 1 plus 6 iota. And now let us see solution of part 3. Part 3 is the line joining the point 1 plus 2 iota to the origin. Let us see from the figure. So look at figure number 3. The line joining the point 1 plus 2 iota, 1 plus 2 iota is the given point, and the origin is 0, 0. So you can see this is the required line, which is coming from the origin and joining the origin and this point. So now what we need equation of this line. To find equation of this line, we can see x and y both are changing throughout this line. But from here we can get that x is equal to 1c and y is equal to 2c. So if I put these values and z is equal to x plus iota y, we can get equation of this line, which is c into 1 plus 2 iota. And now you can see that if I put c is equal to 0, I will get the origin. And if I put c equal to 1, I will get this point. So the value of c is between 0 and 1. So c is a 1. And now let us see solution. So now we have to put this point, which is z is equal to c into 1 plus 2 iota. This is the path in the given function. But one thing we have to note here, that after putting this point inside this function, there will be only c. So we need the limits of c. Now, as z approaches to 1 plus 2 iota, this implies that c is approaching to 1. In other words, if you put z is equal to 1 plus 2 iota here, you can see 1 plus 2 iota will be cancelled with 1 plus 2 iota, and we can get c is equal to 1. So as z approaches to 1 plus 2 iota, c is approaching towards 1. Now let us put that the value of z in the given function and simplify this. After simplification, let us take limits on both sides. So we take limits z approaches to 1 plus 2 iota, but on the other side, we don't have any x or y or z. We have only c now. So we can take limits c approaches to 1. And after applying these limits, we can get the same solution, which is minus 1 plus 6 iota. So the limits of this function at the given point exist. And finally, let us see the definition of continuity for a complex function. A function f of z is said to be continuous at a point z naught if it satisfies three conditions. The first condition is f of z naught exists. It means that if we put the point z naught inside the given function and simplify this, its answer must not be equal to infinity or minus infinity. So if the answer is not infinity and minus infinity, we say that f of z naught is defined or f of z naught exists. Second, we have to find the limits, and the limits must exist any path. The third one is that the answer obtained from part 1 and part 2 must be equal. In other words, limits z approach z naught f of z must be equal to f of z naught functions or derivative of a complex function. First of all, we shall see the definitions, then the proof of these definitions, and finally we shall solve problems. So let us start from the definition. We say that a complex function f of z is differentiable if the limits on the right hand side in this formula exist. And if we replace z by z naught, then we say that the function f of z is differentiable at the point z naught. What do we mean by this limit exists? This limit exists mean if we are given a function and we find this limit and we get some answer, the answer must be a finite number. It means if dash of z naught is not equal to plus infinity or minus infinity. Unique mean if we evaluate this limits along any direction, along the vertical axis, along the horizontal axis, or any other direction, but we must get a unique solution. We obtain these definitions by the method of first principle or by ab initio method. So let us prove this. Let W is equal to f of z be a complex function. Now according to the method of first principle, we have to add delta W with W and delta Z with Z. Now we have to transfer W to other side of the equation. And now we can put W equal to f of z. So we can get that this is equal to this one. In the next step, we have to divide both sides by delta z. And finally, we have to take limits delta z approaches to 0, which is equal to limit delta z approaches to 0, f of z plus delta z minus f of z divided by delta z. And this thing is equal to dw over dz, which is equal to this one. Now dw is equal to f of z. So from here we can write that f of z is equal to limit delta z approaches to 0, f of z plus delta z minus f of z divided by delta z. And you can see that this is the same definition or the same formula which we can see from the definition. So this definition can be obtained by using the method of first principle. Now a function is differentiable at the point z is equal to z naught, mean just replace z by z naught and we can get limit delta z approaches to 0, f of z, but this z must be equal to z naught, delta z minus this z, again we can change it, replace it by z naught divided by delta z. And you can see this is the second definition which we can obtain from here. So if we are given a function f of z and someone say to differentiate this function by definition, then we can use this formula, and if a point z naught is given, then we can use this formula. Let us solve the first problem. Find the derivative of f of z is equal to z conjugate by definition. To differentiate this function, we have to write the formula that if dash of z is equal to limit delta z approaches to 0, f of z plus delta z minus f of z divided by delta z. Now f of z is equal to z bar, so f of z plus delta z must be equal to this thing, limit delta z approaches to 0, and we can write that this is z plus delta z whole bar and minus this is f of z, which is equal to z bar divided by delta z. This can be written as limit delta z approaches to 0, z conjugate plus delta z conjugate minus z conjugate divided by delta z. These two terms will be cancelled. And now we have to replace delta z by delta x plus iota delta y. So we can write that this is equal to delta x approaches to 0 and delta y approaches to 0. And this is equal to delta x plus iota delta y conjugate and divided by delta x plus iota delta y. From here we can get that delta x approaches to 0, delta y approaches to 0, and this is delta x minus iota delta y divided by delta x plus iota delta y. We say that this is equal to 1. Now we have to evaluate this limit along different paths. The first one is along the real axis. On the real axis, we have delta y equal to 0. So just replace delta y equal to 0 in 1 and we can get that f dash of z is equal to limit delta y is 0, so delta x approaches to 0. And here we can get delta x divided by delta y because delta y is 0. If I simplify this, we can get an answer which is equal to 1. Number 2, along the imaginary or vertical axis. Vertical axis. At the vertical axis or at the imaginary axis, we have delta x equal to 0. And 1 implies that from 1 again we can get f dash of z is equal to limit. Now delta x is 0, so we have to take limit delta y approaches to 0. And now from here we can get minus iota delta y divided by plus iota delta y. These two things will be cancelled and we can get minus 1. We can see that the limits are not unique since we don't have unique limits. This implies f of z is not differentiable. Let us see an important problem. What does a complex function f of z is equal to u plus iota v need to be differentiable. Here f of z is equal to u of x comma y plus iota v of x comma y, and we know that delta z is equal to delta x plus iota delta y. Now, by definition of the complex function, we know that f dash of z is equal to limit delta z approaches to 0, f of z plus delta z minus f of z divided by delta z. So if we put values in this formula, we can get that f dash of z is equal to, from here we can get that this is equal to u of x plus delta x comma y plus delta y, and plus iota v of x plus delta x comma y plus delta y minus f of z. F of z is u of x comma y and minus iota v of x comma y, and whole divided by delta z. Now let us arrange these things. We can get that f dash of z is equal to, we arrange u with u, so we can get that this is u of x plus delta x comma y plus delta y, and minus u of x comma y divided by delta z. Delta z is delta x plus iota delta y. Here we have to write the limits that delta z approaches to 0, and here we have to again write the limit delta x approaches to 0, delta y approaches to 0, and now plus iota, this is common, so we can write v of x plus delta x comma y plus delta y, and minus v of x comma y, and whole divided by delta z is equal to delta x plus iota delta y, and we have to use the limits here. Delta x approaches to 0 and delta y approaches to 0, and let this is equation number 1. Now for the limits, we can take these limits along the x-axis and along the y-axis. So first of all, let us consider x-axis, and we know that at x-axis delta y is equal to 0. So put delta y equal to 0 and 1, we can get that this is equal to f dash of z, which is equal to limit delta y is 0, so we have to take only delta x approaches to 0, and here we can get u of x plus delta x comma y because delta y is 0, and minus u of x comma y, and this is divided by delta x because delta y is 0. Similarly, here we can write plus iota and limit delta x approaches to 0, and this is v of, there is iota, v of x plus delta x comma y minus v of x comma y, and divided by delta x. You can see that this is the definition of del u over del x plus iota This is the definition of del V over del X. So f dash of z is equal to this thing, and let this is equation number 2. Now again from 1 we can take limits along the y-axis or the vertical axis or imaginary axis. So along the y-axis, delta x is equal to 0. So putting delta x equal to 0 in 1, we can get that f dash of z is equal to limit delta y approaches to 0, u of x comma y plus delta y minus u of x comma y divided by delta y, and plus iota delta y, and plus iota limit delta y approaches to 0. Here we can write that this is v of x comma y plus delta y and minus v of x comma y whole divided by iota delta y. Now this iota will be cancelled with this one. And here to cancel this iota, we can multiply this by iota by iota. So if I multiply this with iota by iota, I can get minus iota here, and this will be cancelled because iota into iota is minus 1 and 1 iota must be here. So from here we can write that f dash of z is equal to minus iota, and this is the definition of del u over del y, and plus this is the definition of del v over del y. Let this is equation number 3. Now the limits must be unique. So comparing 1 and 2, they must be equal. So from 1, comparing 1 and 2, we get delta u over delta x plus iota delta v over delta x is equal to delta v over delta y and minus iota delta u over delta y. Comparing a real with real, from this we can get the delta u over delta x is equal to delta v over delta y. And comparing imaginary with imaginary, we can get delta v over delta x is equal to minus delta u over delta y, or we can write delta u over delta y is equal to minus delta v over delta x. These two equations are called the Cauchy-Riemann equations. So you can see that these limits exist only if this is equal to this thing and this is equal to this thing, and the limit exists mean that the function is differentiable if these two equations are satisfied, and that is the definition of the Cauchy-Riemann equations. Let us see another definition of the derivatives, which are also called the Cauchy-Riemann equations. We say that a complex function f of z is equal to u plus iota v is differentiable if it satisfies these two CR equations. Now if the function f of z satisfies these two equations, we will say that f of z is differentiable. And then how we can find its derivatives? Then derivatives of f of z is equal to ux plus iota vx. Let us see by solving a problem. In this problem, we have to find the derivative of f of z is equal to e power z by using the CR equations. So here f of z is equal to e power z, which can be written as e power x plus iota y, which is equal to e power x into e power iota y. And by the Euler formula, we can write that f of z is equal to e power x into cos y plus iota sin y. And if we multiply this inside, we can get that here u is equal to e power x cos y and v is equal to e power x sin y. This is equation number 1 and this is equation number 2. Let us verify the CR equation. From 1 we have differentiate 1 with respect to x. This is partial differentiation. So we can get that this is e power x cos y. Now differentiate 2 with respect to y. So we can get Vy is equal to e power x and differentiation of sine is cos y. From these two we can see that ux is equal to Vy. So first equation is satisfied. Again let us take 1. So from 1 we can differentiate this with respect to y. So to differentiate with respect to y, we can get e power x, a differentiation of cos y is minus sin y. And from 2, we can take differential of 2 with respect to x. We can get e power x sin y. From these two equations, we can get that uy is equal to minus vx. So both CR equations are satisfied. This means that f of z is differentiable. Now if f of z is differentiable, what will be its differentiation? So its differentiation if dash of z is equal to ux plus iota vx. Let us put values in this ux. Ux is e power x cos y from here plus iota vx. Vx is this one, which is e power x sin y, and from this we can get that this is e power x into cos y plus iota sin y. By the Euler formula we can get that e power x into e power iota y, which is equal to e power x plus iota y, and this is equal to e power z. So this is the required solution. Problem number 3. Differentiate f of z is equal to z square by using the CR equations. Here f of z is equal to z square. So if we put z is equal to x plus iota y whole square and differentiate this, open the square, we can get f of z is equal to x square minus y square plus iota 2xy. Now you can see that u is equal to x square minus y square and v is equal to 2xy. Let this is 1 and this is 2. So from 1 we can obtain the differentiation of u with respect to x, which is equal to 2x, and from 2 we can differentiate v with respect to y, which is 2x. So from these two we can get that ux is equal to vy, and first equation is satisfied. Now again from 1 we can get uy, differentiating u with respect to y, which is equal to minus 2y, and from 2 differentiating v with respect to x, which is 2y, and we get that uy is equal to minus vx. Since both CR equations are satisfied, this implies that f of z is differentiable. And now we can find f dash of z, which is equal to ux plus iota vx. So putting values, we get ux is 2x plus iota, vx is 2y. So if we simplify, we can get 2x plus iota y, which is equal to 2z, and this is the Cauchy-Riemann equations in polar form. A complex function f, which is given in the polar form, is said to be differentiable if it satisfies the following CR equations in the polar form. ur is equal to 1 over r v theta, and u theta is equal to minus r vr. Now if a function satisfies these two equations, that function is said to be differentiable, and in that case we can find its differentiation by using this formula. F dash of z is equal to e power minus iota theta into ur plus iota vr at the point z is equal to r naught comma theta naught. Now let us solve an example by using CR equations in the polar form. Problem number 4. Differentiate f of z is equal to under the root r e power iota theta by 2 by using the CR equations. Here f of z is equal to r power 1 over 2, and e power iota theta can be written as cos theta by 2 plus iota sin theta by 2. From here we can get that u is equal to r power 1 over 2 cos theta by 2, and v is equal to r power 1 over 2 sin theta by 2. This is equation number 1 and this is equation number 2. Now let us differentiate 1 with respect to r. So if we differentiate 1 with respect to r, we can get that this is 1 over 2 r power 1 over 2 cos theta by 2, and differentiate 2 with respect to theta, then this is equal to r power 1 over 2. Differentiation of sine is cos, and inner differentiation is 1 over 2. From these two equations you can see that we can get ur is equal to 1 over r v theta, and the first equation is satisfied. Now again from 1 we can get u theta, which is equal to r power 1 over 2 differentiation of cos is minus sin theta by 2 and the inner is 1 over 2, so minus 1 over 2. And from 2 we can get VR. So VR is 1 over 2 r power minus 1 over 2, and assign theta by 2. From these two equations we can see that u theta is equal to minus r VR. So second equation is satisfied. So it means that f of z is differentiable function. And now how we can find its differentiation? So we know that f dash of z is equal to e power minus iota theta into u r plus iota VR. Just put the values. This is equal to e power minus iota theta. VR is this thing, which is 1 over 2 r power minus 1 over 2. UR is this one, which is 1 over 2 r power minus 1 over 2 cos theta by 2, and plus iota VR is this one, 1 over 2 r power minus 1 over 2 sine theta by 2. Now you can see 1 over 2 r power minus 1 over 2, this thing is common, and cos theta by 2 plus iota sine theta by 2 can be simplified with the Euler formula. So we can get that this is equal to 1 over 2 r under the root, and this is e power iota theta, and this one is e power iota theta by 2. If we simplify, we can get 1 over 2 into r under the root e power minus theta by 2, and this is the required solution. Problem: differentiate f of z is equal to z square at any point z by using the definition. So here, first of all, let us write the formula. The formula is that f dash of z is equal to limit delta z approaches to 0. F of z plus delta z minus f of z divided by delta z. And now we have to put the values. F of z is this thing, so just replace z by z plus delta z, and we can get that this is equal to limit delta z approaches to 0, z plus delta z square minus f of z, it is z square divided by delta z. Now we have to just expand this formula, and we can get that this is equal to z square plus delta z square plus 2z delta z and minus z square divided by delta z. Now this z square will be cancelled with this one, and let us take delta z as common. So we will get that this is equal to delta z into delta z plus 2z divided by delta z. Now we can cancel these two terms, and we get that this is equal to delta z plus 2z. Now just put delta z equal to 0 here, and you will get that the answer is 2z. But just for similarities, I have to use the similar way. So we can write this thing like limit delta y approaches to 0 and delta x approaches to 0, and delta z is equal to delta x plus iota delta y. Similarly here I can write z as x plus iota y, and let this is equation number 1. Now first of all I have to find these limits along the horizontal axis. At the horizontal axis we know that delta y is equal to 0. So just put delta y equal to 0 in 1 and we can get from 1 that f dash of z is equal to limit delta x approaches to 0. Delta x, this is 0, plus 2 into x plus iota y, and now if I put values delta x approaches to 0, I will get that this is 2 into x plus iota y. So f dash of z along the horizontal axis is equal to 2z. Now in second case I have to find the derivatives along the vertical axis, and at the vertical axis we know that delta x is equal to 0. So again from 1 we can get that f dash of z is equal to limit delta y approaches to 0, because now delta x is 0, and in this now delta x is 0, so we can write iota delta y plus 2 into x plus iota y, and if I put delta y equal to 0 we can get 2 into x plus iota y, and finally we get that the derivative of the function f of z along the vertical line is same, 2z. Hence we have unique limits, and hence the differentiation of this function is 2z, and this is the required solution. Now let us see another problem. In this problem we have to differentiate this function f of z is equal to z into z conjugate at any point z. So in a similar way I am going to write the definition. The definition is f dash of z is equal to limit delta z approaches to 0 f of z plus delta z minus f of z divided by delta z. And now we have to put the values. Just replace z by z plus delta z. So we can get that this is equal to, we can get here z plus delta z, and similarly z plus delta z conjugate, and minus f of z, which is equal to z into z conjugate divided by delta z, and we have the limits delta z approaches to 0. Now we can split this conjugate. This means that this is equal to limit delta z approaches to 0 z plus delta z into z conjugate plus delta z conjugate minus z into z conjugate divided by delta z. Let us multiply these two terms. So we can get that limit delta z approaches to 0, this is z into z conjugate plus z into delta z conjugate. Now plus z conjugate delta z and plus delta z into delta z conjugate, and finally we have this term z into z conjugate divided by delta z. Now these two terms will cancel. And we have only this equation. So now we can write this equation as f dash of z is equal to limit delta x approaches to 0, delta y approaches to 0. Now z is equal to x plus iota y. Delta z is equal to delta x conjugate plus iota delta y conjugate, but conjugate only changes the sign of the iota term. So this is equal to delta x minus iota delta y, and plus now z conjugate x minus iota y, because conjugate only changes the sign of iota term, and this is delta x plus iota delta y. And finally we have to put the value here. This is delta x plus iota delta y into multiplied with delta x minus iota delta y, and whole divided by delta z, which is equal to delta x plus iota delta y. And now let us say this is our equation number 1. So we have to find the limits along the vertical axis and the horizontal axis. So along the horizontal axis we know that delta y is equal to 0. So put delta y equal to 0 and 1, and we will get that 1 implies that f dash of z is equal to limit delta x approaches to z, because delta y is 0, and this is equal to x plus iota y, and now delta y is 0, so here we have only delta x, this term is 0, plus from here x minus iota y, again delta y is 0, so we have only delta x here. Similarly, delta y is 0, so we have delta x and into delta x, and whole divided by delta x, because delta y is 0. Now taking delta x as common, we can see they will be cancelled, and we can get that limit delta x approaches to 0. So we have x plus iota y from here. From here we have x minus iota y, and from here we have delta x. Now this term will cancel with this one. If I put delta x equal to 0, so we can get that the answer is 2x. So f dash of z is equal to 2x. And now let us find the limits along the vertical axis, and we know that along the vertical axis delta x is 0. So in a similar procedure, from 1 we can get that f dash of z is equal to, just put delta x equal to 0, we can get that this is limit delta y approaches to 0, and we have x plus iota y, and this one is minus iota delta y, delta x will be 0, and there is x minus iota y, and this term is iota delta y, and plus from here delta x is 0, so we have iota delta y into minus iota delta y, and whole divided by iota delta y. Now let us take iota delta y as common. So if I take iota delta y as common, it will be cancelled, and we can get that this is equal to limit delta y approaches to 0. So here I can get x plus iota y, and iota delta y is cancelled, so we have only minus 1 here. Similarly, from here we can get that this is equal to x minus iota y, plus iota delta y is cancelled with this one, so we have plus 1, and from here we can see that this term is cancelled and we can get minus iota delta y. And now let us put the limits. So if I put the limit, this one is 0, but here I have to multiply minus 1 inside, so I will have minus x minus iota y plus x and minus iota y. X and minus x will be cancelled and we can get minus 2 iota y. So the limits of the function f of z along the vertical axis is equal to minus 2 iota y, and you can see that the limits are not unique. The limits are not unique. Here we have 2x and in this place we have minus 2 iota y. So since the limits are not unique, so this implies f of z is not differentiable, and that is all. Now in the next step I have to show you some differentiation formulas. Here I have to tell you that all the rules of calculus can be used here. For example, differentiation of a constant with respect to the real variable is 0, so in a similar way differentiation of constant with respect to a complex variable is 0. If a constant is multiplied with a function f of z, then that constant can be taken outside and we can only differentiate the function. Similarly, we can use the power rule that differentiation of z power n is nz power n minus 1. If two functions are in sum or in subtraction, we can just differentiate them individually. Similarly, we can use the product rule. If two functions are in product, then the differentiation is first differentiation of second plus second differentiation of first. If two functions are in division, we can use the quotient rule. G square g differentiation of f minus f differentiation of g. And in a similar procedure we can use the chain rule that d by dz of f is equal to df over dw into dw over dz. So you can use all the rules of calculus here. And now let us solve some problem to clear that concept. Differentiate f of z is equal to 2z square minus iota whole power 3. Just differentiate with the usual way. So I have to differentiate f dash of z. This is equal to, I will use the power rule 3 2z square minus iota power 3 minus 2 into inner differentiation, which is 2z square minus iota. So we can get 3 into 2 z square minus iota whole power, this is 1. So this is square, and from here we can get 4z. Now just simplify and we will get 12z into 2z square minus iota whole square. So this is the usual rule which we can use in the calculus. Let us show you one more example. Differentiate this function. F of z is equal to sine z into log z. So we will differentiate in a similar procedure. F dash of z is equal to, this is first function and this is second function. First function, differentiation of the second function, which is 1 over z. plus second function and differentiation of the first function, which is cos of z, and you can get the solution. Similarly, if we have two functions and they are in division, for example, we have x square divided by sine x, then just use, this is z square divided by sine z, then just use the quotient rule and solve the problem. If we have sine inverse z and we have to differentiate, to use the formula for sine inverse z, which is 1 over 1 minus z square under root, and you will get the answer. So you can use all the rules of calculus in the complex analysis and you will get the answer, and that is all. Function. We say that a complex function f of z is analytic at a point z naught if it is differentiable at each point in the neighborhood of z naught. From the previous two lectures, we know how to differentiate a complex function. We can use the method of Cauchy-Riemann equations, we can use the definition, or we can use direct formulas to find its differentiation. Now, if a complex function f of z is given, first of all, differentiate the function, then put the point z naught in this function and look at the answer. If the answer is not plus infinity or minus infinity, then we say that the function f of z is differentiable at the point z naught, and hence it is analytic at the point z naught. So let us see some examples. The first example, I have f of z is equal to z square. Let us differentiate this function. I will find f dash of z is equal to 2z. Now I have to see its differentiability at a point z naught which is equal to 0. So I have to put 0 in this function and look at the answer, and you can see it is not infinity or minus infinity. So we can say that this function is differentiable at the point 0 and hence it is analytic at the point 0. Now if you put any point here, for example, I can put another point. The point is 2 plus 3 iota. So I will get f dash of 2 plus 3 iota, which is equal to 2 into 2 plus 3 iota equal to 4 plus 6 iota, and this is not equal to infinity or minus infinity. So this function is differentiable at z is equal to 2 plus 3 iota, and hence it is analytic at this point. So if you put any point here, you can see that you will get some finite number. So polynomials are always differentiable. Let us see another example. I have to take another function, and the function is f of z is equal to 1 over z. Let us differentiate this function. I get f dash of z is equal to minus 1 over z square. Now let us put z is equal to 0 in this function. F dash of 0 is equal to anything divided by 0 is infinity. So you can see that we get minus infinity. This implies that f of z is not differentiable at 0, and hence f of z is not analytic at z is equal to 0. Now if you put any other point, for example, let us put z is equal to 2 iota. I will get f dash of 2 iota is equal to minus 1 over 2 iota square, and I will get the answer, which is a finite number. So we can say that this function is differentiable at the point z is equal to 2 iota. So we can see that if we put any other point without 0, we get a finite number. So the function f of z is analytic for all values of z belongs to the whole complex plane set minus 0. So if I just remove 0 from the complex plane, at all other points this function is analytic. Harmonic function, a twice 2 times continuously differentiable function h which satisfies this equation is called a harmonic function. So to show that the function h is harmonic, we have to prove that h satisfies this equation. This equation is called Laplace equation, and it can also be written as delta h is equal to 0. Let us see this problem. Show that h is equal to e power minus x sine y is harmonic. To show that this is harmonic, we have to prove this equation. So let us say this is 1. Now from 1, I have to differentiate h with respect to x. So I will get e power minus x sine y. And if I differentiate this function again, I will get del square h over del x square is equal to, here I will get plus e power minus x sine y. Now let us differentiate 1 with respect to y. So I will get e power minus x and differentiation of sine is cos y. Let us differentiate this once again. I will get del square h over del y square is equal to e power minus x differentiation of cos is minus sine. So from here I can get that this is minus sine y. I will put minus here. Now let us take the right hand side of this equation. I get del square h over del x square plus del square h over del y square. And now let us put the values. Del square h over del x square is this value. So I have to put e power minus x sine y. Del square h over del y square, this is equal to this one. So I have to put e power minus x sine y. They will cancel and I will get 0. So since it satisfies this equation, this implies that h is harmonic. Now let us prove an important theorem which says that if we are given a function f is equal to u plus iota v, which is analytic, then u and v both are harmonic functions. Let us prove this. Since f is analytic, so it means that f is differentiable, and we know that if f is differentiable, it satisfies the CR equations. The first CR equation is del u over del x is equal to del v over del y. And the second CR equation is del u over del y is equal to minus del v over del x. Now let us prove the first one. The first one is u is harmonic. To prove that u is harmonic, we must prove that del square u over del x square plus del square u over del y square is equal to 0. So let us find its solution. From here we can write del over del x into del over del x of u and plus, split this one also, del over del y into del over del y of u. Now del over del x, and you can see that del u over del x from 1. This is del v over del y. Now here del u over del u over del y is equal to minus del v over del x. So we can write that this is del over del y into del v over del x. And if we cancel these two, we will get 0, which implies that u is harmonic. Similarly, we can prove that v is harmonic. To prove that v is harmonic, we must prove that del square v over del x square plus del square v over del y square is equal to 0. So let us do that. From here we can get del over del x into del over del x of v. From here we get del over del y into del over del y of v. And now look at the CR equation. This is del over del x, but del v over del x. Del v over del x. This is equal to minus del u over del y. So I can write minus del u over del y. Similarly, del over del y. And from 1 we can see that del v over del y is equal to del u over del x. So I can write del u over del x. This is minus, this one is plus, and we will get 0. So this implies that v is harmonic function. Harmonic conjugate. Let us see the definition. If we are given a complex function f is equal to u plus iota v, if u and v are harmonic and satisfy the Cauchy-Riemann equations, then v is called a harmonic conjugate of u. Please keep it in mind that u is not a harmonic conjugate of v. Only v, which is the imaginary part, is a harmonic conjugate of u. This is an important result, that if v is a harmonic conjugate of u, then in that case the function f must be an analytic function. Sometime we are given a function u and we have to find its harmonic conjugate v. So let us learn this from problem this one. Show that u is equal to x square minus y square is harmonic. Find the harmonic conjugate v of u. And finally find the function f. Here we are given that u is equal to x square minus y square. Let this is equation number 1. Now, to show that this is harmonic, we must prove that del square u over del x square plus del square u over del y square is equal to 0. So, if we differentiate u with respect to x, I get ux is equal to 2x. And if I differentiate it again, I will get uxx is equal to 2. Similarly, if I differentiate u with respect to y, I will get minus 2y. And if I differentiate it again, I will get minus 2. So now using these values, we can get that del square u over del x square plus del square u over del y square is equal to, just put the value of this one which is 2 and the value of this one which is minus 2, and we get 0. So this implies that u is harmonic function. To find the harmonic conjugate v, we use the Cauchy-Riemann equations. The Cauchy-Riemann equations are ux is equal to vy, this is first equation, and uy is equal to minus vx, this is second equation. Now, from equation number 2, we can find vy because ux is equal to 2x. So from 2 we can see that vy is equal to ux, and this implies that vy is equal to, just put the value of ux is equal to 2x. So we get that vy is equal to 2x. Now differentiate both sides with respect to y. Integrate both sides. So if I integrate with respect to y, I will get v here. If I integrate this term with respect to y, I will get 2xy and plus constant of integration, and that constant of integration is a function of x because the integration is with respect to y and it is partial integration. It means that if I differentiate this equation with respect to y, from here I will get vy. If I differentiate this with respect to y, I will get 2x. If I differentiate this with respect to y, then this is 0 because this is a function of x. And now let us say this is equation number 3, equation number 4. And in the next step I have to use this third equation, and from the third equation I can get that uy is equal to vx. So just take vy equal to vx and we can get from equation number 3. From equation number 3 we can see that we have uy which is equal to vx minus vx from equation number 3. This is equation number 3. Let us show you that this is equation number 3 is this one. So I just take uy is equal to minus vx, and now I have to put the values. So the value of uy, you can see that u is given in the question, which is x square minus y square. From here I can get uy. So uy is equal to minus 2y. Just differentiate with respect to y. And Vx from equation number 4, you can see this is equation number 4. From equation number 4, we can see this is 2xy plus h of x. Just differentiate this with respect to x. So I will get 2y, and plus with respect to x, differentiation is h dash of x. So I have to put these values in this equation. So if I put these values in this equation, I will get uy is minus 2y, which is equal to minus vx. So I will get minus 2y and minus h dash of x. Now you can see these two terms will be cancelled, and I can get h dash of x is equal to 0, and you can see it is a function of x only. So just integrate both sides with respect to x. We will get h of x is equal to constant. Now if you differentiate it again with respect to x, you will get h dash, and differentiation of constant is 0. So put h of x is equal to c in equation number 4. This is equation number 4, and we can get v, which is equal to 2xy plus c. This is the required harmonic conjugate. Harmonic conjugate. Finally, we have to find the function. So the function f of x comma y is equal to u plus iota v. And now I have both values. U is given in the question, which is x square minus y square plus iota, and v is this value, 2xy plus c. So this is the required function f of x comma y, and that is all. We know that a complex number z in the Cartesian form is written by x plus iota y, and in the polar form this can be written as r into cos theta plus iota sine theta, and in the exponential form it is equal to r e power iota theta. Now here r is the absolute value, which is equal to x square plus y square under the root, and theta is the argument, which is equal to tangent inverse of y by x. From this we take the exponential form only. So let us write z is equal to r e power iota theta. Throughout this lecture, by log we mean natural log, log z to the base e, which can be written as ln z. So let us take log on both sides. So we obtain ln z, which is equal to ln r e power iota theta. Now here we use a basic rule of logarithm, that log m cross n is equal to log m plus log n. According to this rule, we write it as ln z is equal to ln r plus ln e power iota theta. And now there is another basic rule, log m power n. This is equal to n log m. So according to this rule, we write ln z is equal to ln r plus iota theta into ln e. Now we know that the value of log e is equal to 1. So we get ln z is equal to ln r plus iota theta. So this is the basic formula which we shall use to find the logarithm of a complex number. This can be written as ln z, which is equal to ln r. We are just putting the value of r, which is x square plus y square whole power 1 over 2, plus iota theta is the argument, so we can write tangent inverse y by x. And now from this we can write ln z is equal to 1 over 2 ln of x square plus y square plus iota tangent inverse y by x. Log z is equal to log r plus iota theta. This is called the principal logarithm, sometimes called the particular logarithm. Now, if theta is the angle here in the first quadrant, then after a rotation of 2 pi, we get theta plus 2 pi. And you can see we get the same angle in the same quadrant. If we make another rotation of 2 pi, then we have theta plus 4 pi. And you can see again we come to the same place in the same quadrant. In other words, 2 pi is the period of sine and cos. So sine theta plus 2 pi is equal to sine theta. Similarly, cos theta plus 2 pi is equal to cos theta. And any multiple of 2 pi is a period of sine and cos. So instead of theta here, if we write theta plus 2n pi, then we get that z is equal to r e power iota into theta plus 2n pi. And now if we use the same procedure, we get this formula, and this is called the general logarithm for a complex number. So if in a question someone said to find the logarithm of the following complex number, we shall use this formula. If someone said to find the particular logarithm or the principal logarithm, we shall use this formula. To solve this example, let us find the principal logarithm of z is equal to 1 plus iota. The basic formula for the principal logarithm is given by ln r plus iota theta. Let us say this is 1. For this now we need the value of r, which is given by this formula. So let us substitute the value of x and y. X is 1, y is also 1. So we can write 1 square plus 1 square under the root. From this we get under the root 2. In the next step, let us find the value of theta, which is the argument given by this formula. So let us substitute the values of x and y, which is 1 by 1. So from this we get tangent inverse 1, and tangent inverse 1 is equal to pi by 4, which is an angle of 45. Substituting these values in 1, we get that log of the value of z is now 1 plus iota. Log of 1 plus iota is equal to log of under root 2 plus iota pi by 4. And that is the required solution. In the next step, now let us find the general logarithm of this number. So the formula for the general logarithm is given by ln r plus iota, and now with theta we have 2n pi. N is any integer. Just substitute values in this formula, we get the required solution. So this is the general logarithm of the given complex number. Now let us use the same procedure to find the principal logarithm of this complex number and the general logarithm of this complex number. Again, for the principal logarithm, log of z is equal to log of r plus iota theta. And let us say this is 1. And here to find the value of r, we shall write r is equal to x square, which means 1 square, plus y square, which means under root 3 square. And from this we get 1 plus 3 under the root, which is 4 under the root, and from this we get 2. To find the angle theta, we write tangent inverse of y by x, which is equal to tangent inverse of under root 3 divided by 1. And this is a special angle. We know that its solution is pi by 3. So using these values in 1, we get the value of the principal logarithm, ln 2 plus iota theta is pi by 3. So that is the solution. To find the general logarithm, we use this formula, log z is equal to log r plus iota. The difference is very small. We just add 2n pi with theta, and now using our values, we have log 2 plus iota, and we know theta is pi by 3. So here I am writing pi by 3 plus 2n pi, and that is the required general logarithm of the given number. And in this lecture, we shall study the complex line integral. So first of all, let us see the difference between the real integral and the complex integral. If we have to integrate a function f of x from a point A to B with respect to x, then in the real case, what do we mean? We mean that here f of x is a real value function. Here a is a real number, b is a real number, and what does actually it mean? It means that we are integrating the function f of x from a point x is equal to a to another point x is equal to b, which is actually the real line. So in the real integration, we are integrating this function with the fixed real line. And now let us see that what we do in the case of complex integration. In the complex integration, first of all, we have to know that z is equal to x plus iota y is a complex variable, or x represents a complex plane. And from z is equal to x plus iota y, we can get the differential of z by dz equal to dx plus iota dy. And now if we have to integrate a function f of z, then f of z is again a complex function which can be written as f of z is equal to u plus iota v with respect to dz from a point z0 to another point z1. Now let us see what do we mean by this integral. Here z0 is a complex number. Z1 is a complex number. If I represent this thing in the complex plane, then let z here z0 is equal to x0 plus iota y0, and x1 is equal to z1 is equal to x1 plus iota y1. So these are actually 2 points in the complex plane. So let us, the first point is here. I can also write this thing like x0 comma y0, and this one x1 comma y1. So let us say that this is our point x0 comma y0, and I have another point here, and this point is z1, which is x1 comma y1. Now if I have to integrate this function f of z, I need a path. So you can see that one option which I have is this curve, which is a straight line. So for the complex integration, I need a curve or a path of the integration. But you can see that I can also obtain another path. If I come from this point to here and this from here to at this place, then this one is another path. Let us say that this path is C2. This is the curve C2. And similarly, I can also integrate this thing with respect to another path. Let us say this is another path, and I say that this path is r of t. So you can see that we have many options to find the complex integral. So that is why for each complex integral, we always need some particular path. If someone say to integrate the following complex function, then we need some complex curve or some path for the integration. And now let us see from the screen that how we can evaluate the complex integral. So there are different methods. You can see that the first method is given on the board. In this method, you can see that C is some curve. If the curve C is given in the symmetric form, then we can use f of z is equal to u plus iota v, and similarly we can use dz is equal to dx plus iota dy, and then this complex integral along the curve C is given by 1, which you can see from the board. And now let us show you another method. From the screen, the second method is, again we are given some curve C, and this curve is in the parametric form. So if the curve is given in the parametric form, then we can use equation number 2 to solve the given problem. In this method, r of t is given. From r of t we have to obtain r dash of t, which is differentiation of r with respect to t. And then we have to obtain f of r of t, and then we have to find the complex multiplication of f of r of t and r dash of t. And in this way we can solve different questions. So now I will solve some problems for you, and you can see that if we use any of these methods, you will get the same answer. So these methods are equivalent to each other. Another point which I have to tell you, that the complex line integrals are also called the path integrals or the contour integrals. And now let us solve this example. In this example, we are given the integration of some function which is z square, which we have to evaluate, and the curve is also given. The curve is a straight line which is from the origin to the point 2, 1. So first of all, let us use the first method to obtain the solution for this example. So in this example, let us see that integration along the path C of z square into dz. Now we are given that the curve starts from the origin. The coordinates of the origins you can see 0, 0, and to the point 2, 1. So we can say that there is a point. So 2, 1 is another point. Let this is O and this point is A. The coordinates are 2, 1. And I have to obtain the integration along this straight line. So for this reason, first of all, I need the equation of the straight line. And the equation of the straight line, we know that any slope of, let there is some point P which is x, y. Now slope of any 2 points of the straight line is equal to the slope of any 2 other points. And we know that the slope is actually the ratio between the changes in the y coordinates into the changes in the x coordinates. So we know that for a straight line, that slope of PA is equal to slope of the line OA. And now from here we can obtain, let us find the slope of PA. This is P, this is A. y2 minus y1 divided by x2 minus x1. So we can find y minus 1 divided by x minus 2, which is equal to slope of OA. OA is this point. So again y2 minus y1 divided by x2 minus x1. So from this we can get that 0 minus 1 divided by 0 minus 2. And if we solve this thing, you will obtain that 2y is equal to x. Or I can write that x is equal to 2y. So this is the required curve or equation of a straight line. Now from the given question, we can see that here f of z is equal to z square. So if I put z equal to x plus iota of y whole square, and if I evaluate this thing, I will get x square minus y square and plus iota to xy. Now this is u, which is the real part, and this is v, which is the imaginary part. And now you can see that the integral of the function z square dz is equal to u plus iota v into dx plus iota dy. This is actually the value of the function. This is u and this is v. So from this I can write that this is x square minus y square plus iota to xy and dx plus iota dy. And this is equation number 1. Now from the given curve, I can replace x by 2y. So just replace this x by 2y, this x by 2y. And similarly, you can see that if I take the differential of both sides, I will get that dx is equal to 2 dy. And I can replace now dx by 2 dy. So if I put this thing in 1, I will get that integration of z square dz is equal to, now x should be replaced by 2y. So let us write that this is 2y square, which is equal to 4y square, and minus y square now plus 2. Now let's replace x by 2y. So this is 2y into this y, and now let us replace dx by 2 dy plus iota dy, and now let us simplify this thing. So if we simplify, now what we need, if we convert this equation into y-axis, then we need the limits of y from the given 2 points. So the limits of y are from 0 to 1. If you convert this equation into x-axis, then you should need the limits for x, which are from 0 to 2. But now it is in y, so the limits are from 0 to 1. And let us simplify this thing. So if you simplify this thing, you will get that from here we get, here is also iota, from there we get 3y square. Iota comes from here, okay. And this one is plus 4 iota y square into, let us take dy as common, so 2 plus iota into dy. And from here we can take y as common, so if I take y as common, I will get 0 to 1. This is 3 plus 4 iota into y square, but I have to write this thing here, 2 plus iota, and now y square comes here into dy. Now you can see that this is a constant term, and it is multiplication of two complex numbers. So if you multiply this thing, you will get, let us start from here. After the multiplication, you will get that integration of z square dz along the curve C is equal to, from this we will get just like 2 plus 11 iota. Just multiply these two terms and take it outside from the integration, and you will see that you will get 2 plus 11 iota. And now we have to integrate y square. So integration of y square is y cube divided by 3. The limits are from 0 to 1. So if you put the limits, you will get that this is 2 plus 11 iota into 1 over 3. And this is the required solution for the given complex function along some curve. Now I have to show you that how we can use the second method, which is the parametric method, to obtain the solution. So the second method, method number 2, is method 2. Now we have already obtained that x is equal to 2y. From this we can get that x divided by 2 is equal to y divided by 1. So we have already obtained that x divided by 2 is equal to y divided by 1. And if we put this thing equal to t, we will get that x is equal to 2t and y is equal to t. And now what is r of t? R of t is equal to x of t plus iota y of t. Just put values in this one, so you will get 2t plus iota t. And from this you can get that this is actually 2 plus iota into t. And now we can use the second method. According to the second method, we need r dash of t. So we have to differentiate r of t with respect to t, and we will get that r dash of t is equal to 2 plus iota. Now the other thing we need, since we have f of z is equal to z square, so I need f of r of t. So r of t is this thing, so I have to write 2 plus iota all square. And if I expand this thing, I will get 4 minus 2 square is 4 plus iota square is minus 1 and plus 2 into 2 iota. So we will get 4 iota, which is equal to 3 plus 4 iota. Now you can see the integration of z square dz can be written as f of r of t into r dash of t dt. So from here I can get that f of r of t, this is equal to 3 plus 4 iota, and r dash of t, okay, this is equal to, and also r of t here is t, so we have to write t square here. So it means we have to write t square here. This is also t square. Okay, so now this is t square. And now we need r dash of t. R dash of t is this thing, which is equal to 2 plus iota into dt. Now these two terms are constant, so they will go outside, and if we multiply these two terms, again we will get 2 plus 11 iota integration from 0 to 1 t square dt. And if you evaluate these integral, you will get the same answer, which is this one. So integration along the curve c z square dz is equal to this thing. Now in the next step I have to show you the third method. The third method is that if you have to use this equation but you have the curve in the parametric form, then how you can use this method to solve a problem where the curve is given in the parametric form. So let us see method number 3, and you will see that from all these methods we can obtain the same answer. So now you can see that here f of z is again given by z square, okay, and now f of z is equal to z square, and you know that this is equal to x plus iota y whole square, which is equal to x square minus y square, and plus iota 2xy. Okay, and now the main formula is, that integration of the function z square along the curve c is equal to, here I have to write u plus iota v, where this is u, this is v, and here I need dx plus iota dy. So now I have to put this thing here, and I will get that this is x square minus y square plus iota 2xy, and this thing is dx plus iota dy. Now the given curve, you can see that we have x is equal to 2t and y is equal to t. So just replace x by 2t and y by t. Similarly, from here, if I take the differential of x, I will get dx is equal to 2 dt, and from here I can get that dy is equal to dt. So just replace dx by this thing and dy by this thing in this formula. So let this is 1. So if I replace this thing, I will get that integration of z square dz is equal to integration, again this is from 0 to 1. Now x is 2t, so 2t square means this is 4t square. Y square, now y is t, so this is t square, plus iota 2, x is 2t, and y is t, and now dx is 2 dt and dy is dt. And now let us simplify this thing. So if now this is the usual integration, if you simplify and solve this question, you will see that the answer for this problem is 2 plus 11 iota into 1 over 2. So you will get the same answer. So you can see that in all of these questions, we have the same solution. So now we have to solve another problem. The other problem, let us see from the screen. In the screen you can see that in example number 2, we are given that we have to integrate the same z square, but along some other curve. The curve is a unit circle, and the equation for a unit circle is r of t is equal to cos t plus iota sin t. So let us see the solution of this example. Now, in this example, we are already given the parametric form. So let us use that method, and we have r of t is equal to cos t plus iota sin t. By the Euler equation, we can write that this thing is equal to e power iota t. Now from here I need r dash of t. So just differentiate and you will get e power iota t divided by iota. If you multiply this with iota by iota, you will get that this thing is equal to minus, this is differentiation, so the differentiation of r of t is iota e power iota t. Okay, now I have to obtain f of r of t. Now f of z is equal to z square, and I have to obtain f of r of t. So I have to obtain e power iota t whole square, which is equal to e power 2 iota t. And now I can use the method that integration of z square along the curve C, this is equal to integration. The limits are given, but the formula is f of r of t into r dash of t dt. So let us just put the values in this formula, and we need limits for t which are already given. So if I put the limits, this is from 0 to 2 pi, and f of r of t is e power 2 iota t into r dash of t. R dash of t is iota, I will write it outside, e power t dt. And now from this you can easily obtain that integration of the curve z square of the function z square along the curve C is equal to integration from 0 to 2 pi, and e power iota will be here, e power 3 iota t dt. Let us integrate this thing. So if we have to integrate this thing, we will get e power 3 iota t divided by 3 iota, and integration is from 0 to by the Euler formula you can see that okay, so this is from 0 to 2 pi. Okay, now just simplify this thing. Iota will cancel the iota, I will get 1 over 3, and by the Euler formula you can expand this thing. So by the Euler formula you can write that this is equal to cos 3t plus iota sin 3t. Integration is from 0 to 2 pi, and if you put the values, you will get that integration of this function is equal to 0 along the given circle. And now I have to show you from the screen another problem. In this problem, you can see we have to evaluate some complex function, the limits are given from 0 to 1 plus iota. So I have to just give you some hints. Here again, z is equal to 0 mean the origin 0 comma 0, and z is equal to 1 plus iota mean 1 comma 1. So if these are 2 points, one is 0 and the other point is 1 comma 1, which is p. So using the method of the previous example, you can obtain a curve which is y is equal to x. And if you use the same procedure, you will get that the answer of this problem is minus 1 over 3 into 1 minus iota. But just try this by yourself. And let us see the other part of this example, which says that we have to evaluate the given function along the path from z is equal to 0 to z is equal to 1, and then from z is equal to 1 to z is equal to 1 plus iota. So if you evaluate this, from the first of all you have to obtain the equation of straight line, which is from origin to m of 1 comma 0, and using the same procedure you will get that the equation is y is equal to 0, and you will get this answer. Similarly, for the next point, this is m and p, you will use the same procedure, you will get x is equal to 1, your curve, and then using the same procedure, you will get this solution number 4. Now adding 3 and 4, you will get the answer for problem example number 3, part number 2. Now these are some questions, and by using the concept which we have learned in this lecture, you can solve all of these questions. So till the next lecture, Allah Hafiz, Assalamu Alaikum. Confusion. First of all, let us see the statements of these two results. Cauchy integral theorem. In my previous lecture, we have studied that if we are given a function f of z, which is analytic for all points inside and on a closed simple curve C. In other words, if there is no singular point of the function f of z inside this curve C or on the boundaries, then this integral will vanish. And now let us see the statement of Cauchy integral formula. If we are given a function f of z such that this function f of z has a singular point inside the closed curve or on the boundary, then of course I cannot use the Cauchy integral theorem. So what I have to do, I have to use the Cauchy integral formula. And in that case, I will split that function f of z into two parts. I will take one part to the numerator and the other part to the denominator. The part which is a function in the numerator, now that function must be analytic for all points inside or on the boundaries of this closed curve. In other words, this function which is in the numerator will have no singular point inside this curve. And in that case, this integral must be equal to 2 pi iota, and we have to put that point z naught which is in the denominator inside the function g of z. So we will get g of z naught. And you can see that of course f of z is not analytic, but the function which is in the numerator, that is analytic at all points inside or on the boundaries. So now let us solve a problem. In this problem, we will take two domains. So let us see the statement. Evaluate the integral log of z plus 1 over z square plus 1. But in the first part, this curve C is a circle of this form, and the second part, this curve C is a circle of this form, and you can see that the radius, this radius is different from this one. So let us start from the solution. To solve the first part, first of all, we know that we have this circle z minus 2 iota is equal to 1 over 2, which is a circle. From this circle we can see that the radius is 1 over 2, and we need the center of this circle. So to find the center of this circle, we will put this equal to 0. So z minus 2 iota is equal to 0 implies that z is equal to 2 iota. This 2 iota can be written as 0 plus 2 iota. And in the form of point, we can write that the x coordinate is 0 and the y coordinate is 2. Now we have to draw this circle. So if I draw the circle, I will get, this is a real axis, this is imaginary axis. The center is 0 comma 2, y, x is 0 and y is 2. So let this is 1 and this one is 2. So this one is 3. 1, 2 and 3. So the center of this circle is this one. And the radius is half. So half, this is half, this is half. So if I draw the circle, I will get a circle like this one. Now let us take the function. So our function f of z is this one. So we have f of z is equal to log of z plus 1 divided by z square plus 1. And this can also be written as log of z plus 1 divided by, if I factorize, I will get z minus iota into z plus iota. So now I have to find the singular points of this function. To find the singular points, we have to put the denominator equal to 0. So we have to put z minus iota into z plus iota equal to 0. From this we can get 2 points. Z is equal to iota and the other one is z is equal to minus iota. From this you can see that this is actually 0 plus iota. So in the form of a point, this is 0 comma 1, and this one is z is equal to 0 minus iota. In the form of a point, we can write this is 0 comma minus 1. Now let us draw these 2 points on the graph. So z 0 comma 1, x is 0, y is 1. This point is z is equal to iota, or in other words, this is 0 comma 1. And z is equal to minus iota. So this point is here, this is minus iota. So this point is z is equal to minus iota, or we can say this is 0 comma minus 1. Now you can see that this function f of z has 2 singular points, but both of these singular points are outside of the circle, of the closed curve, of the given closed circle. In other words, this function has no singular point inside the circle. And if it has no singular point, then in that case we can use the Cauchy integral theorem. So by the Cauchy integral theorem, we can say that integration of this function f of z, which is log of z plus iota divided by z square plus 1 dz will vanish. This is equal to 0, and this is the required solution. Now let us see the second part. In the second part, we have a circle of this form. So let us start the solution. We have from part 2, again we have to find the radius. In this case, the radius is 2 and the center is same. Z is equal to, as we have obtained, this is 0, 2. So again we have to draw this circle. So the graph is like this one. Now let this is 1, let this is 2, this is 3, and this is 4. So the center is again here. The center is 0, 2. But the radius is 2. Radius mean its radius will be here, will pass from this place. So to draw the circle, we can draw a figure like this one. So this is now a circle whose radius is 2. And now let us see the function. The function f of z is again the same. Log of z plus 1 divided by z minus iota into z plus iota. If we draw this point, you can see that z is equal to iota is this point which is inside the circle. So it means this function now has a point z is equal to iota which is inside the circle. So I cannot use the Cauchy integral theorem. Now what I have to do? I have to split this function into two parts. I have to take the other part like log of z plus iota divided by z plus 1, log of z plus 1 divided by z plus iota and whole divided by z minus iota. Now in this case, this is our g of z. This is a function g of z, and you can see this function has no singular point here because z is equal to minus iota lies outside the given closed curve. So in that case, I have to use the Cauchy integral theorem, which says that g of z divided by z minus iota, iota is now z naught, is equal to 2 pi iota g of iota. So I have to put values in this formula, which is equal to 2 pi iota and g iota. This is our function g of z. Just replace z by iota. We will get that this is log of iota plus 1 divided by iota plus iota, which is 2 iota. And this 2 will cancel with this one, iota will cancel with iota. And this is the required answer. Or in the other way, we know that log of z is equal to log of r plus iota theta. So you can even simplify this a little more. So if I simplify this, I will get log of r is under root 2 plus iota theta. Theta is tangent inverse 1, which is pi by 4. And this is the required solution. That is all. We shall study the complex power series, its radius of convergence and interval of convergence. So let us start from the definition of the complex power series. A series of the form summation an z minus z naught power n, where n is from 0 to infinity, is called a power series centered at the point z naught. If we expand this series, we get, if I put n is equal to 0 here and here, I will get a naught plus a1 z minus z naught and plus a2 z minus z naught square and plus up to so on. So here in this series, the coefficients a n are some real or complex numbers, and z naught is a fixed point. Z naught, this is some fixed point which is called center of the power series. And now in this series, if I put z naught equal to 0, I will get a series of the form summation a n z power n, where n is from 0 to infinity. And if I expand this, I will get a naught plus a1 z plus a2 z square and plus up to so on. So this is a series centered at 0. This is some particular form of this one, because if we put z naught here, we automatically get this series. Now let us show you some examples of the power series. Example is that one power series is this one, summation z power n divided by n factorial, where n is from 0 to infinity. If I put 0 here and here, I will get 1. If I put 1 here and here, I will get z. If I put 2 here and here, I will get z square divided by 2 factorial up to so on. So this is a particular power series whose center is 0. And now let us see another example. In this example, let us take another series of the form this one, z minus 3 whole power n divided by n, where n is, or let us, this is n plus 1, so then we can take n from 0 to infinity. And now if I put the values, I will get, if I put 0 here and here, I will get 1. If I put 1 here and here, I will get z minus 3 divided by 2. If I put 2 here and here, I will get z minus 3 whole square divided by 3 and plus up to so on. Sometimes we are given a function and we have to find its power series. So let us see an example that how we can find a power series from a given function. So from a given function, let us solve an example. The example is, find the power series of number 1. The function is f of z is equal to 1 over 4 minus z, but about z is equal to 0. And number 2, we have to find the power series of the same function, but its center is at 1. Then how we can find the power series? So let us solve this example. First of all, to solve part number 1, we usually use here the binomial expansion. The binomial expansion is that 1 minus x power minus 1 is equal to 1 plus x square and plus up to so on. So now let us take the first part of this example, where f of z is equal to 1 over 4 minus z. And now I have to take 4 common from this one. So I will get 1 over 4 into 1 minus z divided by 4. And after the simplification, I will get 1 over 4 into 1 minus z divided by 4 whole power minus 1. Now I can use this expansion. So from this one I will get 1 over 4 into 1 plus z by 4 plus z square divided by 4 square and plus up to so on. And now if I multiply 1 over 4 inside, so I will get that f of z is equal to 1 over 4 plus z divided by 4 square plus z square divided by 4 cube and plus up to so on. If I write this in the summation notation, I will get that this is equal to summation z power n divided by n plus 1, where divided by 4 power n plus 1, where n is from 0 to infinity. So this is the required power series for the given function f of z, whose center is at z is equal to 0. Now for this you will see later that the radius of convergence of this thing is 4. So if I draw the graph of this curve, its center is at 0. The center is at the origin. And its radius is 4, so this point is now 4. This point is 4, and this is the origin, 0, 0. So this is 1, 2, 3, and 4. This is the required. So basically, this series is convergent inside this disk. And later we will check some other thing, that whether it is convergent on a radius 4 or not. So we will learn this after some time. And now let us see how we can find the power series of that function when the center is at 1. So let us do the process again for the next question. Now here again f of z is equal to 1 over 4 minus z. I have to split 4 such that I have to get the center 1, z minus 1. So I can write this thing that this is equal to 3 minus of z minus 1. And now I have to take 3 as common. So I will get, that 1 over 3 into 1 minus z minus 1 divided by 3. And in the next step, after simplification, I will get that f of z is equal to 1 over 3 into 1 minus z minus 1 divided by 3 whole power minus 1. And again I have to use this binomial expansion, and I can get that this is equal to 1 over 3 into 1 plus z minus 1 divided by 3 plus z minus 1 square divided by 3 square and plus up to so on. If I multiply this 1 over 3 inside, I will get 1 over 3 plus z minus 1 divided by 3 square plus z minus 1 square divided by 3 cube and plus up to so on. So if I express this in the summation notations, I will get that this is equal to z minus 1 power n divided by 3 power n plus 1, where n is from 0 to infinity. So now you can see that this is a power series whose center is at z is equal to 1, and its radius, of course, you will learn after some time that how we can obtain the radius of convergence. So its radius is 3. If I draw the graph of this curve, then its center is at 1. So let this is 1. This is Argand and this is 1. And its radius is 3. So 1, 2, 3. Similarly 1, 2, 3. So I can get a curve of the form this. Now again this is 4. This one is 4. So this is the required circle or disk for the given curve. So this power series is convergent inside this disk, and outside of this disk it is divergent. So this is all. Thank you. Now let us see that what do we mean by the radius of convergence and how we can find the radius of convergence of a power series. So you can see from the definition that if we are given a power series of the form this one, then there exists a real number r. There exists some number r. If z minus z naught absolute is less than r, then this series is convergent. And if this is greater than r, then this series is divergent. And that number r is called the radius of convergence. So basically this z minus z naught absolute less than r will give us this disk, that inside this disk our power series must be convergent, and if we go away outside of the disk, then the series will be divergent. And now let us find the methods which we will use to find that number r. So let us see this. Finding the radius of convergence. Finding the radius of convergence r. So there are two methods which we can use and find that number r. The first method is the ratio test, and the second is the root test. So the first method, we know that from the ratio test, if we take limit n approaches to infinity, a n plus 1 divided by a n absolute, and if we evaluate this, we will get some number r. And now from that number, some number L, and from that number L, we can get r. So r will be equal to 1 over that number L. So this is radius of convergence for a power series. Similarly, this is just like this is the ratio test. We can also use the root test, and by the root test we can evaluate the limits n approaches to infinity, nth root of a n, and we can find L. And then again, radius of convergence r is equal to 1 over L. So this one is called the root test. Now we have to solve some example to find that number r. So let us find some example. The example is find radius of convergence for the power series is given as summation 2 power n z power 2n, where n is from 0 to infinity. So let us see that how we can find the radius of convergence. First of all, we have to write an from here. So this coefficient, this is an. So here an is equal to 2 power n, and from this we can obtain that an plus 1 is equal to 2 power n plus 1. And now we can find L, which is equal to limit n approaches to infinity and an plus 1 divided by an absolute. So just put in values and you will see that limit n approaches to infinity, n plus 1 is 2 power n plus 1 divided by 2n. And if I simplify this and evaluate the limits, we will get 2. So now in this case L is equal to 2. So what will be the radius of convergence? So the radius of convergence in this case is equal to 1 over L. So just put in the values, we get that R is equal to 1 over 2, which is the required answer, or radius of convergence for this example. Now let us solve another example. For example, and you can see that in this example, you can see that the center is at 0. But we have to find another example in which the center is not 0. So let us find another example. Again, another example is we have to find radius of convergence of the series. The series is summation n is from 0 to infinity and 4 power n divided by n, 4 power n divided by n into z minus 3 whole power n. So let us find radius of convergence for this power series. Again, here in a similar procedure we can find an, which is equal to 4 power n divided by n. From this we can find an plus 1, which is equal to 4 power n plus 1 divided by n plus 1. And now let us find L. L is equal to limit n approaches to infinity, an plus 1 divided by an. And now let us put the values. We get limit n approaches to infinity. N plus 1 is 4 power n plus 1 divided by n plus 1. Divided by an, so I will inverse this thing and we will get that this is n divided by 4 power n. So if I simplify this thing, I will get that limit n approaches to infinity. From here I will get 4. And from here I will get n divided by n plus 1. So if I apply the limits, you can see this is infinity by infinity form, which is an indeterminate form, so you can use the L'Hopital rule. Or the other procedure is that you have to divide the numerator and denominator by n, and you will get that limit n approaches to infinity 4 into 1 divided by 1 plus 1 over n. And now if you apply the limits, so you will get that the answer is 4. So in this example you can see that our L is 4. So what will be R? R is equal to 1 over L. So from this we can get that the radius of convergence for this power series is 1 over 4. That's all. Now let us see interval of convergence. Let R be the radius of convergence of a complex power series of the form this one. Then we know that if R is the radius of convergence, then Z minus Z naught absolute is less than R. And if we simplify this thing, we get this thing, which is interval of convergence. But here is a condition that the series may or may not be convergent at the end point this one and at the end point this one. That is why if we have to find the interval of convergence, we first of all we have to reach to this place and obtain this thing. So half work will be done to that point. Next, we have to put Z is equal to Z naught minus R in the given power series, and we have to check whether the series is convergent at this point or not. Then we have to put Z is equal to Z naught plus R in the given power series, and we have to check whether the given series is convergent at this point or not. So let us solve an example from which it will be clear that how we can find interval of convergence. So the example is find the radius of convergence and interval of convergence of the complex power series Z power n divided by n, where n is from 1 to infinity. Okay, this is the given series, and we have to solve there whether what is the radius of convergence and interval of the convergence. Okay, so here again an is equal to 1 over n, and from this I can obtain that an plus 1 is equal to 1 over n plus 1. And now I have to find L. So L is equal to limit n approaches to infinity, an plus 1 divided by an absolute. And if I put values, I will get limit n approaches to infinity. An plus 1 is 1 over n plus 1. And n is 1 over n, so if I take the inverse of this thing, I will get n over 1. And now we have to evaluate the limits. So if I apply the limits, again this is infinity by infinity form, so we can use the L'Hopital rule, or we can divide the numerator and denominator by n. So we get that this is equal to limit n approaches to infinity and 1 divided by 1 plus 1 over n. And from this we get that L is equal to 1. So now a radius of convergence is 1 over L. So we get that R is equal to 1. In the next step, we have to find a radius interval of convergence. So to find interval of convergence, here we have to use that Z minus Z naught is less than R. But Z naught in this power series is 0. That is centered at 0. So we can put values, and from the values we can get that Z absolute is less than 1, where R is equal to 1. And from this we can obtain that minus 1 is less than Z and Z is less than 1. So half work is done. But now we have to check whether the given series is convergent at this point or not. Then we have to check whether the given series is convergent at this point or not. So let us see the convergence at the end point. At Z is equal to 1. So I have to put Z is equal to 1 in this series. So the series becomes summation n is from 1 to infinity, and this is now 1 power n is 1, so 1 divided by n. I have to check the convergence of this series. So I can use different tests. Here I use the integral test. By the integral test, I have to write this 1 over x dx, where integral, the limits are from 1 to infinity. If I integrate this, I will get log x from 1 to infinity, and you can see that log infinity is infinity. So the given power series is divergent at z is equal to 1. So this point is not included in the interval. Now let us see that whether the given series is convergent at this point or not. So let us put z is equal to minus 1 in the given series. So at z equal to minus 1, we get that summation minus 1 power n divided by z power, okay, divided by n, where n is from 1 to infinity. And you can see that this is an alternating series. And if I find the absolute convergence from the absolute value, I will get 1 over n, and this will be divergent. So it is not absolutely convergent. So what I have to do, I have to use the alternating series test. What is the alternating series test? We say that an alternating series must be convergent if it satisfies two conditions. The first condition is that if I take limit n approaches to infinity of an, the answer must be equal to 0. The second condition is that this must be non-increasing. Non-increasing means that n plus 1 must be less than an. So let us see whether it is conditionally convergent or not. So this is called conditionally convergent. So again, here an is equal to 1 over n, and if I take the limits, so limits n approaches to infinity, an is equal to 0. So the first condition is satisfied. And now let us see the second condition. From 1 over n, I can say that if I divide 1 by n plus 1, and on the other hand, if I divide 1 by only n, then this must be less than 1 over n, which means that an plus 1 is less than an. And this means that the second condition is satisfied. So this implies that summation minus 1 power n divided by n, where n is from 1 to infinity, is conditionally convergent. Okay, so now this point, the series is convergent at minus 1. So what will be the interval of convergence? So in this case, the interval of convergence is given by interval of convergence. This is minus 1 is less than or equal to z, and z is less than 1, because it is not convergent at that point, but the series is convergent at minus 1. And we can also write that the series is convergent in this interval. That's all. So till the next lecture, Allah Hafiz, Assalamu Alaikum.
Let us study the power series, its radius and interval of convergence. A power series is a series of the form this one. Here Z0 is called center of the power series. It is a fixed number. If Z0 is 0, we get a power series centered at 0 of the form this one. To find a radius of convergence of a power series, we use the ratio test.
With the help of the ratio test, after evaluating these limits, we get a number L. And then a radius of convergence is equal to 1 over L. Sometime we use the root test to find the number L, and then R is equal to 1 over L. It is also convenient to use directly this formula or this formula and find the radius of convergence. To find interval of convergence from the given series or from the given question, we substitute z minus z naught absolute less than r. We simplify this to find the value of z. Now we check whether the series is convergent or divergent at the endpoint this one or at this endpoint. So we put z is equal to z naught minus r in the given question and simplify this, so we get a new series. Then we check the convergence of the new series. Let us say the new series is convergent at the endpoint z naught minus r. Then we put z is equal to z naught plus r and simplify this to get a new series. And again we check the convergence of the new series. Let the new series is divergent at the point z naught plus r. In this case, interval of convergence is given by this one. On the left hand side, we use the closed bracket, and on the right hand side, we use the open bracket, because it is convergent at the point this one and divergent at the point this one. If we do the same process, but we get that the series is convergent at both endpoints, then interval of convergence is given by this one. You can see we use closed bracket on both sides. And if it is divergent at both endpoints, then interval of convergence is given by this one. Here we use open brackets on both sides. Let us use our method to find the radius of convergence and interval of convergence for the power series given in this example. We start to write the formula for the radius of convergence, which is given by an divided by an plus 1. And now let us say this is 2. Now here the value of an, this is given by 1 over n square 9 power n, and from this we can get the value of an plus 1. Just replace n by n plus 1. So we get the value of an plus 1. Substituting these values into, we get that r is equal to limit n approaches to infinity. an is 1 over n square 9 power n divided by an plus 1. So we can write 1 over n plus 1 whole square 9 power n plus 1. And now let us simplify this. So if we simplify this, we get limits n approaches to infinity. And now we get 1 over n square 9 power n into n plus 1 whole square 9 power n plus 1 divided by 1. And from this, if we further simplify this, we get limit n approaches to infinity. And now we can write n plus 1 whole square divided by n square. So we write it n plus 1 divided by n whole square. Now from 9 power n plus 1 divided by now 9 power n, from this we get 9. And now if we simplify it, we take 9 as common and limit n approaches to infinity. And from this now we get 1 plus 1 over n whole square. And if we apply the limits, we get 9 into 1 plus 0. So radius of convergence for this power series is 9. To find interval of convergence, we know that we put z minus z naught absolute less than r. And from this we get z minus 5 absolute is less than 9. If we further simplify this, we get minus 9 is less than z minus 5, which is less than 9. And from this we obtain 5 minus 9 is less than z, which is less than 5 plus 9. And if we further simplify this, we have minus 4 is less than z and z is less than 14. Now the next task is to check the convergence at the end point. Let us take the end point z is equal to 14. So if we put z is equal to 14 in the given series 1 implies that n is from 1 to infinity. 14 minus 5 power n divided by n square 9 power n. And if we simplify this, we get 9 power n divided by n square 9 power n. N is from 1 to infinity. 9 power n will cancel with 9 power n. So we get the series 1 over n square, where n is from 1 to infinity. And by the p series, we can see it here. If this p is greater than 1, then we say that the series is convergent. So this implies that it is convergent. Now let us check the series at the other endpoint. The next endpoint is z is equal to minus 4. So let us put z is equal to minus 4 in 1. So 1 becomes n is from 1 to infinity. Minus 4 minus 5 power n divided by n square 9 power n. And from this we get summation minus 9 power n divided by n square 9 power n. N is from 1 to infinity. And this can be further simplified as summation minus 1 power n 9 power n divided by n square 9 power n. 9 power n will cancel with the 9 power n. So we get an alternating series. Minus 1 power n divided by n square, where n is from 1 to infinity. Since it is an alternating series, we use the absolute convergence test, which says that if we are given an alternating series, then this alternating series is said to be absolutely convergent if the absolute value of summation an is convergent. So let us take the absolute convergence. So here now we use summation an absolute. N is from 1 to infinity, and it will become summation from 1 to infinity 1 over n square. So we can see that n absolute here is 1 over n square, which is again the p series, and p is greater than 1. So by p series, we can say that summation an absolute is convergent. And this implies that the given series, which is minus 1 power n divided by n square, is convergent. Now, since this is convergent at both endpoints, minus 4 and 14, so interval of convergence is given by square brackets minus 4 to 14, and that is the required solution. Now consider example number 2. Here we use the same procedure. So an is equal to 1 over n 2 power n. And from this we can obtain the value of a n plus 1, which is equal to 1 over n plus 1 into 2 power n plus 1. Now, radius of convergence r is equal to limits n approaches to infinity a n divided by a n plus 1. Let us substitute values here. So we have limit n approaches to infinity. The value of a n is 1 over n 2 power n. And the value of a n plus 1. So if we convert division into multiplication, we have n plus 1 into 2 power n plus 1 divided by 1. And from this we obtain limit n approaches to infinity. 2 power n will cancel with 2 power n plus 1. So here we have only n, and n plus 1 whole divided by n can be written here. So from this we get limits n approaches to infinity. Let us take 2 outside of the bracket. So we have 1 plus 1 over n, and we write 2 here. So if we simplify this, we get 2 into 1 plus 0. So radius of convergence is equal to 2. In a similar procedure, now we find interval of convergence. So using the values, we have z minus 3 absolute is less than 2. And from this we get minus 2 is less than z minus 3, which is less than plus 2, which gives minus 2 plus 3 is less than z, which is less than 2 plus 3. And from this we obtain 1 is less than z and z is less than 5. Now the next task is to find the convergence at the endpoint. So let us take the first endpoint at z is equal to 5. Putting z is equal to 5 in the given question, we get summation n is from 1 to infinity 5 minus 3 whole power n divided by n into 2 power n. And if we simplify this, we get 2 power n divided by n 2 power n. N is from 1 to infinity. Now 2 power n will cancel with 2 power n, and we get
a new series which is 1 over n. N is from 1 to infinity. And by the P series, we can see P is 1 here. So it is divergent. Now let us take the next endpoint, z is equal to 1. So substituting z is equal to 1 in 1, we get summation 1 minus 3 power n divided by n 2 power n. N is from 1 to infinity. If we simplify this, we get minus 2 power n divided by n into 2 power n. N is from 1 to infinity. If we further simplify this, we have n is from 1 to infinity. This is minus 1 power n into 2 power n divided by n into 2 power n. 2 power n will cancel with 2 power n. And we get a new series. Minus 1 power n divided by n. N is from 1 to infinity. And we can see that this is an alternating series. So first of all, let us check whether it is absolutely convergent or not. So to take the absolute value of this series, n absolute, we have n is from 1 to infinity and we get a positive term series 1 over n, which we can see is not convergent or it is divergent by the P series. So we write it is not absolutely convergent. So when an alternating series is not absolutely convergent, then we use the alternating series test, which says that an alternating series is convergent if it satisfies two conditions. The first one, take limits n approaches to infinity of an and the answer must be 0. The second one, n must be a decreasing sequence. So let us take limits n approaches to infinity of an. Here an is 1 over n. So limit n approaches to infinity of 1 over n is 0. So the first condition is satisfied. For the second condition, we can see that 1 over n plus 1 is less than 1 over n. And now an plus 1 is actually 1 over n plus 1, which is less than an is 1 over n. So it says that the sequence an is a decreasing sequence. So since both conditions are satisfied, now we can say that it is convergent. It is actually conditionally convergent. Now, interval of convergent, that must be equal to, look at the first endpoint, which is 1, and the second endpoint, which is 5. And we can see at 5 the series is divergent. So here we use the parenthesis, and in the left hand side it is convergent at 1. So here we use the square brackets. So interval of convergent is given by this one. That's all. Now I have to explain the Laurent series by solving some more problems. So let us start from this example. In this example, we are given a function f of z of the form this one, and we have to obtain the Laurent series first in the domain 1. The domain 1 is that z absolute is between 1 and 2. Then again we have to solve the problem and we have to obtain the Laurent series for this function in the domain 2. In the domain 2, z absolute is less than 1. And then the third problem, we have to obtain the Laurent series for this function
in the domain 3 where z absolute is greater than 2. So let us start the solution. From the given function, we can write that f of z is equal to, if I take minus as a common, so I can write minus 1 divided by z square minus 3z plus 2. And now I have to factorize this function. So after the factorization, I will get that this is equal to z minus 1 into z minus 2. And now I have to use the partial fraction. So by the partial fraction, I can write that minus 1 over z minus 1 into z minus 2 is equal to a over z minus 1 plus b over z minus 2. And if I multiply with the LCM, I can get that minus 1 is equal to a into z minus 2 plus b into z minus 1. And let this is 1. So if I put z is equal to 1 in this equation, then this is 0. And if I put 1 here, I will get minus 1. So this minus and this minus will be cancelled, and I can get that a is equal to plus 1. Similarly, if I put z is equal to minus 2, z is equal to 2 in this equation, so then this will be 0. And if I put 2 here, then this is plus 1, and I can get from 1 that b is equal to minus 1. So my function f of z will take this form. F of z is equal to, now a is 1, so I can write that this is 1 over z minus 1. B is minus 1, so I can write this is 1 over z minus 2. And now I have to obtain the Laurent series in the domain 1. So in the domain 1, I have z absolute which is between 2 and 1. So now I have to take this function f of z, and first of all let us consider the first part of this function. And look at this note, always take the greater value as a common in a given domain, and the given domain in this case is this one. So now we have to look at these two terms, whether z is greater. If z is greater, we have to take z as common. If 1 is greater, then we have to take 1 as a common. So you can see from here that 1 is less than z. In other words, z is greater. So we have to take z as a common. So if I take z as a common, I will get 1 minus 1 over z. And now look at this one. If z is greater, we have to take z as the common. If 2 is greater, we have to take 2 as a common, but considering the given domain. And in the given domain, you can see that z absolute is less than 2, which means that 2 is greater. So we have to take 2 as a common from here, and we can get that this is equal to 2 into, this will be z by 2 minus 1. And if I take minus as a common as well, then I can obtain a little more simplified form, that this is minus 1 minus z divided by 2, and this will become plus. So just take minus 2 as a common, you will get plus 1 here, and here you will get minus z by 2, and minus and this minus will become plus. And now I can write that this is equal to 1 over z, and I can write this 1 minus 1 over z whole power minus 1. Similarly, 1 over 2, and this can be written as this one. So now I can use the binomial expansion. for this one as well as for this one. So I can write that f of z is equal to 1 over z, and here this is 1 plus 1 over z square plus 1 over z cube and plus up to so on. And now plus 1 over 2, again I have to use the binomial expansion for this one, so I can get 1 plus z by 2 plus z square divided by 2 square and plus up to so on. So now I have to multiply 1 over z inside. Similarly, I have to multiply 1 over 2 inside. So I can get that this is equal to 1 over z plus 1 over z cube plus 1 over z power 4 and plus up to so on. And similarly, I can get 1 over 2 plus z by 2 square and plus z square divided by 2 cube and plus up to so on. And this is the required Laurent series of the given function in the given domain. So you can see that this is the principal part of the Laurent series, and this one is now the analytic part of the given series. So now let us solve the second part of this question. In the second part, you can see that again we are given the domain. The domain is given. The domain is that z absolute is less than 1. So again let us take the function. The function f of z is equal to 1 over z minus 1 and minus 1 over z minus 2. So now in the similar procedure we have to take common. So let us consider the first part. If one is, now the domain is only this thing. This is our given domain. So we have to consider only this domain. In this domain we can see that 1 is greater than z. So we can take 1 as a common. So we can write that f of z is equal to, let us take minus 1 as a common. So we can take minus 1 over, and this become 1 minus z because 1 is greater. Now if z is less than 1, so of course z is less than 2. And it means that 2 is greater than z. So we have to take 2 as a common from here. And we can get again, taking minus 2 as a common, this will be plus, and we can get that this is equal to 2 into 1 minus z by 2. So you can see that by taking minus 2 common, this will become minus and this will become plus. So we can get 1 minus z by 2. And now we have to evaluate this function. So from here I can get that this is 1 minus z whole power minus 1, and this one is 1 minus z divided by 2 whole power minus 1. So let us use the binomial expansion first of all for this one. So f of z is equal to minus, this will be 1 plus z square and plus up to so on. Now plus 1 over 2, and I have to use the binomial expansion. So this is 1 plus z by 2 plus z square divided by 2 square is 4 and plus up to so on. Now let us multiply this minus and this 1 over 2 inside. So we can get that this is equal to minus 1 minus z square and minus up to so on. And plus this is 1 over 2 and plus this is z divided by 4 plus z square divided by 8 and plus up to so on. And now let us simplify. Minus 1 and plus 1 over 2 will give us So I will get that f of z is equal to minus 1 plus 1 over 2. It will give us minus 1 over 2. So I have to write minus 1 over 2. Now minus z and plus z by 4. It will give us minus 3z by 4. So I have to write minus 3z by 4. Now minus z square and plus z square by 8. It will give us minus 7z square by 8. So we can write minus 7z square by 8 and up to so on. So this is the required Laurent series for the given function according to the given domain. And now let us solve the same problem by considering the third domain. So in the third domain, we are given, in domain 3, we are given, in the third part, we are given that z absolute is greater than 2. This is greater than 2. And now I have to write the function. The given function is f of z is equal to minus, 1 over z minus 1 and minus 1 over z minus 2. So again, I have to use this note. So you can see that this note is very important for solving the problems of the Laurent series. So if z is greater in the given domain, I have to take z as common. If 1 is greater in the given domain, I have to take 1 as a common. So you can see that z is greater than 2, and of course 2 is greater than 1. So z is greater than 1. So we have to take 1 as a common. So I can write that this is equal to, let us take minus 1 as common, so I can obtain 1 minus z. Now here, you can see z is greater than 2. You can see from the first part that z is greater than 1. So I have to take z as a common. Always take the greater value as a common. So the greater value is z. So from here I can write that this is equal to, I will take z as a common. So this is 1 minus z minus z, minus 1 over z. Just take z as a common. If you multiply z, you will get z, and if you multiply here, you will get minus 1. Now again from here, z absolute is greater than 2, which means that this is the greater value, and I have to take the greater value as a common. So I have to take z as common. So here I will obtain 1 minus 2 by z. 1 minus 2 by z. And of course, if I multiply z inside, I will get z, and here I will get again minus 1. So now I have to simplify this function. So I will get that this is equal to 1 over z into 1 minus 1 over z power minus 1, and minus, again this is 1 over z into 1 minus 2 by z whole power minus 1. And now I have to expand this by using the binomial expansion. So I can write that this is equal to 1 plus 1 over z plus 1 over z square and plus up to so on. And now minus 1 over z. This is 1 plus 2 by z plus 2 square is 4 and z square and plus up to so on. Now I have to simplify this thing. Just multiply 1 over z inside. So you will get 1 over z. From here you will get 1 over z square. From here you will get 1 over z cube and plus up to so on. And if I multiply here, I will get minus 1 over z. Here I will get minus 2 by z square, and here I will get minus 4 by z cube and minus up to so on. Now plus 1 over z and minus 1 over z will be cancelled, and now from 1 over z square and minus 1 over z square I can obtain that f of z is equal to, this is minus 1 over z square. Now from plus 1 over z cube and minus 4 over z cube I can obtain minus 3. I can obtain minus 3 over z cube and minus up to so on. So this is the required solution for the given function. So till the next lecture, Allah Hafiz, Assalamu Alaikum. Of zeros and singularities for a complex function. So let us start from the topic 0. So first of all we have to define that what we mean by the zero of a function. We say that a point z0 is called a zero of a function f of z if f of z is analytic at z0 and f of z0 is equal to 0. From my previous lectures, you know that what we mean by an analytic function. So a function f of z is called an analytic function at the point z0 if it is differentiable at the point z0. So first of all, this function must be differentiable. Now if we are given a function f of z and I have to put some value inside this function and I get an answer which is exactly 0, then z0 is called a zero of this function. So let us explain it by some examples. Let there is some function f of z which is equal to z minus 1. If I put z is equal to 1 in this function, I will get f of 1 is equal to 1 minus 1 which is equal to 0. And this implies that z is equal to 1 is a 0 of the function f of z. Now let us see another example. I take a function f of z which is equal to z square minus 3z plus 2 divided by sine z. Sometimes we are given a function like this one and we have to find the zeros of this function. Then what we have to do? In that case, we have to put the numerator equal to 0 and then we have to factorize it. So the roots of the numerator are called the zeros of this function. For example, let us do that. Put the numerator which is equal to z square minus 3z plus 2 equal to 0. Now let us factorize this thing. So if I factorize, I will get this thing. Let us take common. So I get z minus 2. If I take common as minus 1, I will get this thing equal to 0. And from this we obtain that z minus 1 into z minus 2 equal to 0. So this implies one point I get from this one, which is z is equal to 1, and the other point I get from this, which is z is equal to 2. So z is equal to 1 and z is equal to 2 are two zeros of the function f of z. Now if we put z is equal to 1 in this function, f of 1 must be equal to 0. Similarly, if we put z is equal to 2 in this function, f of 2 must be equal to 0. So now let us generalize this definition a little more. So we have to write another definition. These are called simple zeros, and now I have to find the order of zeros. So I have to define that a point z naught is called a zero of order k of the function f of z. If f of z is analytic, at z naught, and if I put z naught inside the function, I will get 0. Now if I differentiate this function and I get f dash of z and put z naught, I get that this is equal to 0. Similarly, if double dash of z naught is equal to 0 and up to if k minus 1th derivative at z naught is equal to 0, but the kth derivative of the function at z naught is not equal to 0, then this is called that z naught is a zero of order k, where k is a non-negative integer. So let us explain it by some examples. Let us take a function f of z is equal to z minus 2 power 3, and now we can see that if I put z is equal to 2 in this function, I will get that f of 2 is equal to 2 minus 2 cube, and the answer must be 0. Now I have to differentiate this function. So if I differentiate, I will get f dash of z is equal to 3 into z minus 2 whole square. And if I put z is equal to 2, I will get that f dash of 2 is equal to 0. Now let us differentiate it again. So f double dash of z is equal to 6z minus 2 power 1, and if I put z is equal to 2, I will get that f double dash of 2 is equal to 0. And now let us differentiate it again. So if triple dash of z is equal to, from here I can get only 6. And now if I put z is equal to 2, the answer is 6, which is not equal to 0. So this implies that z is equal to 2 is a 0 of order 3 of the function f of z. And now we have to solve Another example, sometime we are given a function and we have to find its zero. So let us solve another example. The example is, I have a function f of z which is equal to cos z minus 1 and plus z square divided by 2. The question is that show that z is equal to 0 is a 0 of this function and find the order of the 0 for this function. So what we have to do? You can see that if I put z is equal to 0 here, cos 0 is 1. 1 minus 1 is 0 and this is 0. So f of 0 is equal to 0. So it is clear that z is equal to 0 is a 0 of this function. But I have to find something more. I have to write the series expression of this function, which we know from the Taylor series. So I can expand this function like this one. F of z is equal to cos z is equal to 1 minus z square by 2 factorial and plus z4 divided by 4 factorial minus z6 divided by 6 factorial and plus up to so on. So this is the series expression of the cos z, and now I have to write minus 1 and plus z square by 2. And now you can see that 1 should be cancelled with 1 and minus z square by 2 factorial will be cancelled with z square by 2 because 2 is equal to 2 factorial. So I have the function that f of z is equal to z power 4 divided by 4 factorial minus z power 6 divided by 6 factorial and up to so on. Now if I put z is equal to 0 in this function, if I put z is equal to 0, let this is 1, then from 1 I can write that f of 0 is equal to this is 0 and all will be 0. So I get that f of 0 is equal to 0. Now I have to differentiate this function. So f dash of z is equal to, this is 4z cube, but 4 will be cancelled. 4 factorial means 4 into 3 factorial. So from this I can get that z cube divided by 3 factorial if you simplify. Similarly from here I can get 6z power 5 divided by, I can write this 6 into 5 factorial. So this should be equal to z power 5 divided by 5 factorial and plus up to so on. And now if I put z is equal to 0 and f dash of z, then this is 0 and this is 0, so the answer is 0. Now I have to differentiate it again. F double dash of z is equal to, from here I can get in the same procedure z square by 2 factorial. And from here z power 4 by 4 factorial and plus up to so on. And now if I put z is equal to 0 in f double dash of z, I will get 0. Now I have to differentiate it again. So if I differentiate it, I will get a triple dash of z is equal to, here I will get only z. This is actually 2z divided by 2 factorial, but they will be cancelled, so we will get only z. And minus z cube divided by 3 factorial and plus up to so on. And now if I put z is equal to 0, I will get that this is equal to 0. So I have to differentiate it again. If I differentiate it again, I will get that this is 1, and from here I get z square divided by 2 factorial plus up to so on. And now if I put z is equal to 0 here, I will get 1. So if I put 0, I get 1 which is not equal to 0. So this implies that z is equal to 0 is a 0 of order 4 of the given function f of z. Now let us define the singularity of a function f of z. So we said that a point z naught at which a function f of z is not analytic. Is called a singular point. Or singularity. Of a function f of z. A function is not analytic, means a function is not differentiable at that point. So let us explain this by some example. I have a function f of z which is equal to 1 over z minus 2. Now let us differentiate this function. If I differentiate this function, I will get minus 1 over z minus 2. Now if I put z is equal to 2 here, you will get that f dash of z is undefined. Like you can see, it is very obvious that f of 2, this is 0, anything divided by 0 is undefined. So it means that f of z is not differentiable at this point. And this implies that f of z is not analytic at the point z is equal to 2. So hence z is equal to 2 is a singular point. Is a singular point of the function f of z. Now let us see some more examples. Let us write f of z is equal to log of z, and let us find its singular point. So now again we have to differentiate this function. F dash of z is equal to 1 over z. Now if I put z is equal to 0 here, so anything divided by 0 is undefined, so it means that f dash of 0 is infinity. So the function f of z is not differentiable at the point z is equal to 0, so hence it is not analytic at the point z is equal to 0. And this implies that z is equal to 0 is an analytic. This is a singular point of the function f of z. Now let us consider one more example. In this example, let us take a function h of z which is equal to 1 over z square minus 9. Let us consider this function. And if I differentiate this function h dash of z, so by the differentiation I can get that the denominator square z square minus 9 whole square. And now I have to write z square minus 9 Differentiation of 1 is 0. So this term is 0. Now I have to write minus 1, and differentiation of this thing is 2z. So I will get that this is equal to minus 2z divided by z square minus 9 equal to whole square. So sometimes we are given a function, this one, and we have to find its singular points. In that case, we have to differentiate the function, and then we have to put the denominator equal to 0. And the root of the denominator must be singular points. So let us put z square minus 9 whole square is equal to 0. And this implies z square minus 9 is equal to 0. And from this we can get that z minus 3 into z plus 3 is equal to 0. And if we further simplify this, we will get that there are 2 points, z is equal to 3 and z is equal to minus 3. And these 2 points are the singular points for this function. If you put 3 here, you will get infinity. If you put minus 3 here, again you will get infinity. So this function is not differentiable at these 2 points. So it is not, so these 2 points are the singular points of this function. And now let us discuss some types of the singularities. So types of singularity. There are basically 2 types of singularities. The first one is called isolated singularity, and the second one is called non-isolated singularity. But the isolated singularity is further divided into 3 types. The first one is called removable singularity. The second one is called poles. And the third one is called essential singularity. We have to discuss types of singularities. So let us start from the isolated singularity. First of all, we have to write the definition. Isolated singularity. We say that a complex number z0 is called an isolated singular point or isolated singularity of the complex function f of z. If f of z is not analytic at z0, but f of z is analytic in a punctured disk, 0 is less than z minus z0, this is less than r. So from the definition you can see that the given function must be analytic at any other point near to z0. But of course it is not analytic at the point z0. So it means that the function is analytic in the neighborhood of z0. That is why if we replace this statement by some other statement like this one, I will write that there exists an open disk. An open disk, let us denote the open disk by B of Z0, comma R, whose center is that point Z0 and radius is R. So there exists an open disk B of Z0, comma R, such that f of z is analytic. F of z is analytic on B of z0, comma R, set minus the point z0. So it means that if I only remove that point z0, then my function f of z is analytic in the whole disk. And now let us see an example. Let us consider this function. F of z is equal to e power z divided by z minus iota. Now you can see that this function is not analytic at the point z is equal to iota. If you differentiate the function and put z is equal to iota, you will see that it is undefined. Or even you can see that the function is undefined. So it is not differentiable. In other words, it is not analytic at z0. But if you put any point, any other point near to iota, for example, if I put z is equal to iota minus 0.001 iota, then it is analytic. If I put any other point z is equal to iota plus 0.0 iota, then that is analytic. Now isolated singularity has three types: a removable singularity, essential singularity, and poles. Singularities are classified based on the Laurent series. From my previous classes, we know that the Laurent series of a function f of z has two parts. The first part is called analytic and the second one is principal part of. Let us write the definition of a removable singularity. Removable singularity. If all the coefficients b1, comma b2, comma up to so on are 0, then z0 is called a removable singular point. Singular point. In other words, there will be no principal part in the Laurent series of that function. Let us explain this by an example. We have a function f of z equal to sine z divided by z. You can see that at z is equal to 0, this function is not defined, even not differentiable. So it is not analytic at the point z is equal to 0. Now to find the type of the singularity of this function, I have to expand this function into the Laurent series like this one. f of z is equal to 1 over z. And now from the Taylor series we know that sine z is equal to z minus z cube divided by 3 factorial z5 divided by 5 factorial and up to so on. If I multiply this 1 over z, I will get that this is 1 minus z square divided by 3 factorial plus z4 divided by 5 factorial and up to so on. And you can see that in this function we have no principal part. There is no term in the principal part. So that's why this type of singularity is a removable singularity. It is called a removable singularity because we can remove this. We can redefine this function and we can obtain another function which must be analytic throughout the region. So let us see. I have to define a function f of z given by 1 f z is equal to 0 and sine z by z f z is not equal to 0. And you can see that there is no singularity for this new function. One more thing which you have to remember, that in case we have the removable singularity, if you take the limit of that function, that must exist. If I take limit z approaches to 0, f of z, you will see that the limit. To define the essential singularity, we say that if an infinite number of bn's are non-zero, then z0 is called an essential singular point. In other words, we can say that if there are infinite number of terms in the principal part of a Laurent series, then that type of singularity is called the essential singularity. Let us explain this by an example. I have a function f of z which is equal to e power 1 over z. And we can see that at z is equal to 0, this function is not analytic. It is not defined, it is not differentiable, and hence it is not analytic. To find the type of the singularity, we have to expand this function into the Laurent series like this one. F of z is equal to, we have to find the series of e power z. So we can see 1 plus 1 over z plus 1 over z square into 2 factorial and plus up to so on. And now you can see that in the principal part of this series we have infinite number of terms. So this singularity for this function is an essential singularity. To define pole, we say that if a finite number of Bn's are non-zero, then Z0 is called a pole of the function f of z. If m is the highest integer such that bm divided by z minus z0 power m is non-zero, then z0 is called a pole of order m of the function f of z. So you can see that if there are finite numbers, I mean if we stop here, like bm divided by z minus z0 power m. So now there are finite number of terms in the principal part of a Laurent series, and in this case we will say that f of z has a pole z is equal to z0 of order m. Let us explain this by an example. We take a function f of z which is equal to cos z divided by z square, and you can see that at z is equal to 0 this function is not analytic. To find the type of the singularity, I have to expand this function in the Laurent series, like f of z is equal to 1 over z square, and I have to obtain the Laurent series expansion of cos z, which is equal to 1 minus z square by 2 factorial and minus up to so on. If I multiply this inside, I will get 1 over z square. This is minus 1 over 2 factorial plus z square divided by 4 factorial and minus up to so on. So you can see that there is only one term in the principal part of this series. So we can say that z is equal to 0 is a pole of order 2. Now let us see the summary. First of all, we have to represent the function f of z into the Laurent series, and then if all terms in the principal part are 0, this is a removable singularity. If infinite number of terms in the principal part are non-zero, this is essential singularity. If finite number of terms in the principal part are non-zero, this is called a pole. So till the next lecture, Allah Hafiz, Assalamu alaikum. The residue of a complex function. We shall give the definition of residue and examples to explain it. Then we shall learn some simple techniques for computing the residue of different functions. First of all, let us revise the concept of Laurent series, with the help of which we shall define the residues. In my previous lectures, we have studied that the Laurent series of a function f of z is a series of this form which has two parts. The first one is called the analytic part, the second one is called the principal part. And now let us write the definition of residue. We say that if a function f of z is represented in the form of a Laurent series, then the coefficient of 1 over z minus z naught, the coefficient of 1 over z minus z naught, that is B1, is called the residue of the function f of z at the singular point z naught. It is denoted by B1 is equal to a residue at the point z is equal to z naught of the function f of z. Or sometimes we denote this that the residue B1 is residue of the function f comma z naught. From the definition, it is clear that if we are given a function f of z, first of all we have to represent it into the Laurent series. And then just look at the coefficient of 1 over z minus z naught. So the coefficient of 1 over z minus z naught will be our residue. In an informal way, I can say that the residue is nothing but just a coefficient of 1 over z minus z naught. And now let us explain it by some examples. Let us take a function f of z is equal to e power, f of z is equal to e power 1 over 2z. And the question is, find the residue of this function. Then what we have to do? First of all, we have to represent this function into the Laurent series form. Let us do that. F of z is equal to 1 plus 1 over 2z plus 1 over 2 factorial into 2z square and plus up to so on. And you can see that this function has an essential singularity at the point z is equal to 0. And the residue of this function f at the point z is equal to 0 is the coefficient of 1 over z, which is, we can see, 1 over 2. So this is the required solution. Now let us see another example. Let me have a function f of z which is equal to 1 over z cube plus 2 over z square plus 4 over z minus 5 minus 3z. Find the residue of this function. This function is already in the Laurent series. So we can see that this function has singularity at z is equal to 0, at which is a pole. So the residue of the function f at the point z is equal to 0 is the coefficient of 1 over z. And the coefficient of 1 over z is 4. So this is the required solution. Now let us see another example. In this example, I have a function f of z is equal to sine z by z. And the question is, find the residue of this function. So again, I have to represent this function into the Laurent series. So sine z can be written as z minus z cube by 3 factorial plus z5 by 5 factorial minus up to so on. And now I have to multiply 1 over z inside. So if I multiply 1 over z inside, I will get that f of z is equal to 1 minus z square by 3 factorial and plus z power 4 divided by 5 factorial and minus up to so on. Now you can see that this function has singularity at z is equal to 0, which is the removable singularity. And the residue of this function will be the coefficient of 1 over z. And we can see that the coefficient of 1 over z is 0 here. There is no 1 over z. So we can say that the residue of this function f at z is equal to 0 is equal to 0. Now let us solve one more example. In this example, we have a function f of z which is equal to z square into sine of 1 over z. And we have to find the residue of this function. So again, we have to represent this function into the Laurent series. So I can write z square, and again I can use the series of sine z. So I will write that 1 over z minus 1 over z cube into 3 factorial plus 1 over z power 5 into 5 factorial and minus up to so on. Now I have to multiply this inside. So I will get z here. Here I will get 1 over 3 factorial into z, and here I will get 1 over 5 factorial into z power 3 and minus up to so on. So now you can see that this function has singularity at z is equal to 0, and the residue of this function at the point 0 is the coefficient of 1 over z, which is minus 1 over 3 factorial, which is equal to minus 1 over 6. And now we have to learn a very simple technique with the help of which we can find the residue of some complex function f of z without expanding or representing the function into the Laurent series. So let us see the statement of this theorem. If z naught is a pole of order n of a complex function f of z, then the residue of the function f at the point z naught is equal to 1 over n minus 1 factorial n minus 1 time differentiation of the function f of z multiplied with z minus z naught power n at the point z is equal to z naught. From this theorem you can see that if we are given a function f of z which has a pole of order n at the point z naught, then what we have to do? We have to multiply z minus z naught power n with the given function. So of course you will see that this term will be cancelled from f of z. And then we have to differentiate that n minus 1 time. And at the end, after the simplification, we have to put z is equal to z naught and we will get the residue of that function. Let us simplify a little more. If f of z has a simple pole means it is a pole of order 1. So if n is equal to 1, just put 1 here, here and here, and we can see that the residue of f at z naught will be equal to, this is 0 factorial which is 1, and there is no n minus 1 is 0, so means there is no derivative, and z minus z naught power 1, so we can write that this is z minus z naught power 1 only, and the function f of z. And of course at the end we have to put z is equal to z naught in the answer. And now let us see if n is equal to 2. N is equal to 2 means if f of z has a pole of order 2 at the point z is equal to z naught, in that case residue of the function f at z naught can be written as, again just put 2 here, 2 minus 1 is 1 factorial which is again 1. If I put 2 here, 2 minus 1 is 1. So I will get d by dz, and this will become z minus z naught, and let us put 2 here, f of z, and at the end we have to put z is equal to z naught. Similarly, if I have a pole of order 3, in that case the residue of the function f at z naught is given by, just put 3 here, we can get 1 over 2 factorial, and if I put 3 here, I can get d square divided by dz square into z minus z naught power 3, just put n is equal to 3 here, and f of z, and at the end we have to put z is equal to z naught. And now let us explain this by some example. So let us find an example. F of z is equal to, I have to write an example. The example is that f of z is equal to 1 over z plus 1 into z minus 2 power square. 1 over z plus 1 into z minus 2 square. This is some given function. And the question is, we have to find all the residue of this function at the given poles. So you can see, first of all we have to find the poles. To find poles, first of all you have to put the denominator, which is z plus 1 into z minus 2 whole square is equal to 0. And from this you can get that z is equal to 1 is a pole of order 1, which is simple pole. And from this you can get that z is equal to 2 is a pole of order 2. So this is a pole of order 2. So now I have to find the residue as z is equal to 1, and then I have to find the residue at z is equal to 2. So let us start from z is equal to 1. To find the residue of the function f at the point 1, you can see if n is equal to 1, we have to use this formula. Now in this case, z1 is 1, so I can write that this is equal to z minus 1. If I take 1, okay, sorry, this is minus 1. Z plus 1 equal to 0 will give you z is equal to minus 1. So I can get z plus 1 and f of z, and the point is z is equal to minus 1. Now just we have to simplify this. If I simplify this, I will get that this is equal to z plus 1, and I have to put the value of f of z. The value of f of z is this one, so I can write that this is 1 over z plus 1 into z minus 2 whole square, and the point is z is equal to minus 1. Now this term will be cancelled with this one, and now we have to just put z is equal to minus 1 here, and we can get that this is equal to 1 over minus 1 minus 2 whole square, which is equal to 3 square is 9. So the residue of the function f at the point minus 1 is equal to 1 over 9. So this is the required answer. And now we have to find the residue at the other point. So the other point is z is equal to 2. To find, we can see that if n is equal to 2, we have to use this formula. So residue of the function f at the point 2 is equal to, we can write d by dz, and I have to write z minus 2 whole square, and into the function f of z at the point z is equal to 2. Now just put the value of f of z. So if I put the value, I will get d by dz of z minus 2 whole square into f of z. What is f of z? This is 1 over z plus 1 into z minus 2 square at the point z is equal to 2. So this will be cancelled with this one. So now I have 1 over z plus 1, but I have to find d by dz of this function. We have to differentiate this. So if I differentiate this, I will get that this is equal to minus 1 divided by z plus 1 whole square. And again, z is equal to 2 is the given point. So now we have to put z is equal to 2 in this function. If I put this, I will get minus 1 over 2 plus 1 square. And we can get that this is equal to 1 over minus 1 over 9. So the residue of the function f at the point 2 is minus 1 over 9, and this is the required answer. Now we have to solve one other question. In this question we have to find the residue of a function f of z, which is equal to z cube plus 2z, z cube plus 2z divided by z minus iota cube, z minus iota cube. This is the given question, and we have to find the residue of this function. So to find the residue, first of all we have to find the poles. For the poles, put the denominator equal to 0, and from this you will get that z is equal to iota is a pole of order 3. And now I have to find the residue. to find the residue of the function f at the point iota, and in this case n is equal to 3. So if n is equal to 3, I can use this formula. Just put n is equal to 3. You will get 1 over 2 factorial into d square over d z square and z minus iota cube into f of z. And the point is z is equal to iota. This is our pole. And now we have to simplify this. So we can get 1 over 2 iota is 1 over 2, and here d square over dz square into z minus iota cube. Put the value of f of z. The value is this one. So I can write z cube plus 2z and divided by z minus iota whole cube, and the point is z is equal to iota. So this will cancel with this one. But I have to differentiate this function 2 times. So let us, this is 1, and I take this function as g of z. G of z is z cube plus 2z. Now differentiate this. If I differentiate both sides, I will get 3z square plus 2. Now differentiate it again. D square over dz square of d is equal to 6z. Now let us put this value in 1, and we can get so 1 implies that residue of the function f at iota is equal to, this is 1 over 2 and d square over dz square of z cube plus 2z, this is 6z, and the point is z is equal to iota. Now we have to put this point inside. So if I put this point, I will get 1 over 2 into 6 iota. If I simplify these two terms, I will get 3 iota. So residue of the function f at the point iota is equal to 3 iota. In the next lecture, we shall study applications of the residues. So we shall study the residue theorem. With the help of it, we will solve different integrals. So residues at poles. In my previous lecture, we have studied that if we are given a function f of z which has a pole z0 of order n, then we can use this formula to find the residue of this function. Now if I put n is equal to 1 in this formula, I can get the residue of the function f at a simple pole. If I put n is equal to 2, then I can get the residue at a pole of order 2. And if I put n is equal to 3, I can get a pole of order 3, the residue at a pole of order 3. So we can use this formula to find the residue of any function which has poles. So let us start from the solution of a problem. Let us see the problem. The problem is find the residues of f of z is equal to 1 over z square into z minus 2 whole power 4 at all poles of f of z. So we will solve this problem, but you can use the procedure which I will use in the solution of this problem to solve any problem of this type. So let us start from the solution. From the solution, first of all, we have to obtain the poles. To obtain the poles, always we put the denominator equal to 0. So let us obtain the poles. So we have to put z square into z minus 2 whole power 4 equal to 0. And now the roots of this equation are called the poles of that function. So from this equation we can get one root, which is z is equal to 0. And you can see that this is a pole of order 2. Similarly, from here we can get another root, which is z is equal to 2, and you can see that this is a pole of order 4. Now I have to obtain the residue at the first point. So at z is equal to 0, I have to use the same formula. Now in this formula, if I put n is equal to 2, then 2 minus 1 is 1 factorial. Here I will put 2, then this is d by dz, and so on. So let us find the residue. So the residue of the function f at the point 0 is equal to d by dz into z square, and the function f of z at the point z is equal to 0. Now we have to put the value of f of z in this formula. So if I have to put the value, I can get that this is equal to d by dz z square, and the value of the function in the given question is z square z minus 2 whole power 4, and at the end we will put z is equal to 0. Now z square will be cancelled with z square. So I only have d by dz of 1 over z minus 2 whole power 4. So I have to differentiate this. If I differentiate this, I will get that this is minus 4 divided by z minus 2 whole power 5, and the point is z is equal to 0. Now finally I will put this point, and I can get that this is minus 4 divided by minus 2 power 5, and if I simplify this, we can get 1 over 8. So the residue of the function f at the point 0 is 1 over 8, and this is the required solution. Now I have to obtain the residue of the function at the other pole. The next pole is z is equal to 2, which is a pole of order 4. So again, if I put 4 here, you can see I will get 1 over 3 factorial. And if I put 4 here, 4 minus 1 is 3, and so on. So using the same procedure, I can get that the residue of the function f at the point 2 is equal to 1 over 3 factorial into d cube over dz cube, and now I have to put z minus 2 whole power 4 into f of z, and at the end we have to replace z is equal to 2. Now we have to put the value of the function f of z, and 1 over 3 factorial is equal to 1 over 6. This is d cube divided by dz cube, and z minus 2 whole power 4 into 1 over z square into z minus 2 whole power 4 at the point z is equal to 2. You can see these two terms will be cancelled. And now I have to obtain the third order derivative of 1 over z square. So first of all, from here we get that this is 1 over 6 into d cube over dz cube into 1 over z square. And let's say this is equation number 1. So now we put that let 1 over z square is g of z. So we have to differentiate this. To differentiate this, we can get that g dash of z is equal to minus 2 divided by z cube. We have to differentiate this again. G double dash of z is equal to 3 2s are 6 divided by z4. And we have to differentiate this function one more time. So third order derivative of g is equal to 6 4s are 24 minus 24 divided by z5. And now let's put this value in equation number 1. So equation number 1 implies that residue of the function f at the point 2 is equal to 1 over 6 into minus 24 divided by z power 5, and the point is z is equal to 2. Now 6 4s are 24, and now we have to put z is equal to 2 in this function, so we can get minus 4 divided by 2 power 5. And if we simplify this, we can get that the residue of the function f at the point 2 is minus 1 over 8. And this is all. Known as a residue theorem or the Cauchy residue theorem. In a simple word, this theorem states that if you have the residues of a function f of z, then by using the residues you can integrate that function along a simple closed curve. First of all, let us write the statement of this theorem. Let f of z be an analytic function on and inside of a simple closed curve C, except for finite number of singular points z1, z2, up to zn in this closed curve, then integration of that function f of z is equal to 2 pi iota into sum of all residues. We can write that this is equal to 2 pi iota, a residue of the function f at the first point plus residue of the function f at the second point plus up to a residue of the function f at the last point. In the summation notation, we can write that this is equal to summation a residue of the function f at the point zk, where k is from 1 to n. And now let us explain this theorem. This theorem says that if we have a function f of z which is analytic inside and on the boundaries of this closed curve C, however, there is a point z1 at which the function is not analytic. There is another point z2 at which the function is not analytic. And similarly, there are finite numbers of points at which the function is not analytic. In other words, these are singular points of that function. In that case, how we can integrate the function along this closed curve? In this case, first of all, we have to find the residue of the function at the first point. Then we have to find the residue of the function at the second point. And similarly, we have to find the residues of the function at all of its singular points. And then the residue theorem says that its integration is equal to 2 pi iota and sum of all the residues of that function. In the previous lectures, we have studied that if a function is analytic throughout this closed curve, in other words, if there is no singular point inside or on the boundary, then we can use the Cauchy integral theorem. And according to that theorem, integration of the function will vanish. Integration must be equal to 0. But on the other side, we have studied a Cauchy integral formula, which says that if there is some singular point inside the curve C, then still we have to integrate the function according to the Cauchy integral formula. Now the Cauchy integral formula and the Cauchy residue theorem behaves alike. They both can be used to find integral of this type. However, you will see that the residue theorem is more simple than the Cauchy integral formula. And now let us solve a problem to see the application of this theorem. Let us see problem number 1. By using the residue theorem, evaluate integration of 5z minus 2 divided by z into z minus 1, where C is a circle. Z absolute is equal to 2 taken in the positive direction. Now, first of all, we have to draw this circle. To draw the circle, let us recall that a general equation of the circle is this one, where R is a radius and A is a center. So according to this definition, Z absolute is equal to 2 means that we have a radius 2. And the center in this case is 0. So center of this circle is equal to 0, 0. So if we draw this circle, the center will lie here. This is real axis, this is imaginary axis. And the radius is 2. 2 means this is 1, 2, 1, 2, 1, 2, and 1, 2. So the circle will be something like of this form. Now let us see that in this question f of z is 5z minus 2 divided by z into z minus 1. So we have to find the residues, and for the residues we need the singular points. So for the singular points, we always put the denominator equal to 0 and we find its roots. So from this we can get that z is equal to 0 is a pole of order 1, which is called a simple pole. Similarly, from the other one, z is equal to 1 is a simple pole, of this function. So now we have to find the residue at the first point. So residue of the function f at the point 0 is equal to z into f of z at the point z is equal to 0. Now we have to put the value of f of z. So this is z into 5z minus 2 divided by z into z minus 1. So z will be cancelled with z. And now if we put z is equal to 0 here and here, we will get that this residue is equal to 2. And now we have to find the other residue. So residue of the function f at the point 1 is z minus 1 into f of z at the point z is equal to 1. So we have to put the value of f of z, which is equal to 5z minus 2 divided by z minus 1. And z minus 12 will cancel with the z minus 1. And now if I put z equal to 1, you will see that the residue at this point is 3. And now I have to use the Cauchy residue theorem. So by the residue theorem, integration of the function f of z dz is equal to 2 pi iota into residue of the function f at the point 0 plus a residue of the function f at the point 1. So let us put the values. We get 2 pi iota, and residue at 0 is 2 and residue at 1 is 3. So we can get that 5 into 2, this is 10 pi iota. So integration of this function along the given curve is equal to 2 pi iota. And you can see that both point lies inside the circle. 0 also lie here and 1 also lie here. So both lie here. And now we have to solve another problem. In this problem you can see that we have to evaluate this function where c is a positive oriented circle, z minus 1 is equal to 2. So first of all, from this result we have to obtain the radius and we have to obtain the center. So radius is 2 and you can see that the center is 1, 0. So if I draw this circle, you can see its center lies here. This is 1. So center is at this point, which is 1, 0. And its radius is 2. So it will pass 1, 2 similarly from here. So you will see that it is a circle like this one. It starts from 1, 2, 3. Okay, so now you can see first of all we have to write the function f of z, which is equal to sine z divided by z power 6. In such type of questions, first of all we have to find the series expansion of this function. So the series expansion of this function can be written like this one: 1 over z power 6 and sine z, this is equal to z minus z cube divided by 3 factorial plus z5 divided by 5 factorial and minus z7 divided by 7 factorial and plus up to so on. And now we have to multiply 1 over 6. So we can get that this is 1 over z power 5 and this is minus 1 over 3 factorial into z cube, and this is plus 1 over 5 factorial into z, and this is minus z divided by 7 factorial and plus up to so on. Now the coefficient of 1 over z, which is this number, is called the residue. So the residue of this function f at the point 0 is equal to 1 over 5 factorial, which is equal to 1 over 120. And you can see this is a pole of order 5. So now I have to use the residue theorem. So by the residue theorem, we can write that integration of this function f along the closed curve C is equal to 2 pi iota, and residue of the function f at the only 1.0. This is equal to 2 pi iota, and the residue in this case is 1 over 20. So if we simplify, we can get that the answer is pi iota divided by 60, and that is all. Evaluation of real valued integrals with the method of complex contour integration. First of all, in this lecture we shall do some discussions and then we shall solve problems. So let us start from part 1, which is definite integrals involving trigonometric functions. Let us see what do we mean by this statement. If we are given a function f of sin t, cos t, then how we can integrate this function from 0 to 2 pi with respect to t. You can see f as a function of sin t and cos t. What do we mean by this? Let us see some example. F of sin t, cos t may be a function like this one, 1 minus 3 cos t. F of sin t, cos t may be a function like 2 over 3 minus 4 sin t. F of sin t, cos t may be a function like cos t divided by 5 plus 3 cos 11t. So we can see that this must be some function in fraction, and you can see that this function is a real valued function. Now let us concentrate on the limits. The limits of t varies from 0 to 2 pi, which leads us to a circle whose center is at the origin and its radius is 1. So we shall convert this function into the complex function, and then we shall integrate that complex function with the help of a residue theorem along this closed circle. So another thing which we have to remember is that equation of the circle centered at 0 and with radius 1 is given by this thing. But in the parametric form, it can be written as z is equal to e power iota t. Now how we can convert this function to the complex function? In that case, we shall do some substitutions. In the first step, we have to remember that we will always put z is equal to e power iota t. And now if I differentiate both sides, I can get that dz is equal to e power iota t into iota dt. If I put e power iota t equal to z, this is equal to iota z dt, and from this I can obtain that dt is equal to dz divided by iota z. So we have to remember this substitution. In the second step, we know that z is equal to e power iota t, and by the Euler formula this can be written as cos t plus iota sin t. Similarly, z power minus 1, which is 1 over z, which is equal to e power minus iota t, this is equal to cos t minus iota sin t. Let this is 1 and this is 2. Now from 1 plus 2 we get that z plus 1 over z is equal to 2 cos t. These two terms will be cancelled if we add 1 and 2. And from here we can get that cos t is equal to z plus 1 over z divided by 2. If I simplify this, we can get z plus 1 divided by 2z. So we have to remember this substitution. Now if I subtract 2 from 1, in that case we get that z minus 1 over z is equal to, now cos will be cancelled with cos, and from here I will get 2 iota sin t, and from this I can get that sin t is equal to z minus 1 over z divided by 2 iota. And if I do a little more simplification, I will get z square minus 1 divided by 2 iota z. So we have to remember this substitution. Another way to remember this substitution is that from 1 we can see that e power iota t is equal to this, e power minus iota t is equal to this thing. So again if I do this process, I can see that from 1 plus 2 I can get e power iota t plus e power minus iota t is equal to 2 cos t, and from here I can get that this is cos t is equal to e power iota t plus e power minus iota t divided by 2, and you know that this is the formula from the previous classes. Now if I replace e power iota t by z, I will get that this is equal to z, the other is equal to 1 over z divided by 2, and I will get the same result. Similarly, if I subtract 2 from 1, I will get e power iota t minus e power minus iota t, which is equal to 2 iota sin t, and from here I can get that sin t is equal to e power iota t minus e power minus iota t divided by 2 iota. And again if I do that substitution, this is equal to z, the other is equal to 1 over z divided by 2 iota, and we will get the same result. So you can use this method or this method to obtain these substitutions. Now if we put these substitutions inside the given function, we will get a complex integration. And then how we can integrate this? So let us revise. We have to obtain the residues, and then we have to use this formula for the residue, that the residue of f at the point z0 is equal to, where z0 is a pole of order n, is equal to 1 over n minus 1 factorial into dn minus 1 divided by dzn minus 1 and z minus z0 power n into f of z at the point z is equal to z0. If z0 is a simple pole, then n is 1, so 1 minus 1 is 0. At that case, residue of f at z0 is equal to z minus z0 into f of z at the point z is equal to z0. If we do simplification, we can get the residue. And then another thing which we have to remember is the residue theorem. The residue theorem says that integration of the function f of z along the closed curve C is equal to 2 pi iota and sum of residues. And now we are in the position to solve some important problems. So let us start from the first one. Problem number 1, evaluate this integration of the real valued function with the method of complex line integration. So here the problem is to integrate 0 to 2 pi the function dt divided by 5 minus 3 cos t. So we have to put z is equal to e power iota t, and if we differentiate both sides, we can get that dz is equal to iota e power iota t into dt. And now if I put e power iota t equal to z, I can get this thing. And after simplification, we can get that dt is equal to dz divided by iota z. We have to use these substitutions. Next we need the value of cos t. So cos t is equal to e power iota t plus e power minus iota t divided by 2. And if I put e power iota t equal to z and this one equal to 1 over z divided by 2, we can get that z square plus 1 divided by 2z. So cos t is equal to this thing. Now let us substitute these values in the given integral. So 0 to 2 pi dt divided by 5 minus 3 cos t is equal to integration. The value of dt is dz divided by iota z and whole divided by 5 minus 3. The value of cos t is z square plus 1 divided by 2z. Now let us simplify this. So if we simplify, we can get dz divided by iota z whole divided by, let us take its LCM. So we can get that this is 10 z minus 3 z square minus 3 divided by 2z, and you can see z will cancel with z. And now if we simplify a little more, we can see that we will get minus 2 divided by iota, integration. This integration is now a complex integration along a closed curve. So we can get that this is equal to minus 2 divided by iota integration of dz divided by 3z square minus 10z plus 3. And now if we factorize this, or you can use the quadratic formula, you can get that this is equal to dz divided by 3z minus 1 into z minus 3. Now here f of z is equal to this thing, which is equal to 1 over 3z minus 1 into z minus 3. So we need the singular points. For the singular points, we put the denominator equal to 0, and from here we can get that z is equal to 1 over 3, and from this one we can get that z is equal to 3. Now let us see that whether these points are inside the closed curve or outside. So the closed curve in this case is a unit circle. This is the origin. Its center is on the origin, and this is 1, this one is 2, so this one is 3. So you can see that z is equal to 3 is outside, but z is equal to 1 over 3 is 0.3 something. So let this is 1, 2, 3. So z is equal to 1 over 3 is inside here. So we have to obtain the residue at this point. So we can see that z is equal to 1 over 3 is a simple pole. Now we can obtain the residue of the function f at the point 1 over 3, which is equal to 3z minus 1 into f of z at the point z is equal to 1 over 3. So let us put the value of f of z. The value of f of z is this one. So if we put this value, we can get that 3z minus 1 into 1 over 3z minus 1 into z minus 3 at the point z is equal to 1 over 3. Now this will cancel with this one. And if we simplify this, we can get that the residue, if we put z is equal to 1 over 3 here, we can get that this is equal to minus 3 over 8. And now in the next step, we have to integrate the function. So now let us see that the given function is 0 to 2 pi dt divided by 5 minus 3 cos t, which is equal to minus 2 divided by iota, and contour integration of the function f of z dz. So f of z is given here, you can see. Now we have to use the residue theorem. So by the residue theorem, we can get that this is equal to minus 2 divided by iota, and by the residue theorem, this is 2 pi iota, and residue of the function f at the point 1 over 3. So let us put the values. 2 divided by iota. Iota will cancel with iota. So 2 into 2 pi, and residue of this is equal to minus 3 by 8. If we simplify this, 4 2s are 8. We can get that this is 3 pi by 2. So the given integral has a solution which is equal to 3 pi by 2. And now let us solve another problem. In problem number 2, we have to evaluate this integral with complex contour integration. So again, let us write the integral. The integral is 0 to 2 pi dt divided by 5 plus 4 sine t. Using the method which we have discussed, just put z is equal to e power iota t. And if we differentiate, we can get that dz is equal to iota e power iota t dt. From this we can obtain that dt is equal to dz divided by iota z. And sine t, this is equal to e power iota t minus e power minus iota t divided by 2 iota. And if I put e power iota t equal to z, we can get that this is equal to this thing. If we simplify, we will get z square minus 1 divided by 2 iota z. Let us put these values in the given integral. So we can obtain that integration from 0 to 2 pi dt divided by 5 plus 4 sine t is equal to integration. The value of dt is dz divided by iota z, and whole divided by 5 plus 4. The value of sine t, is z square minus 1 divided by 2 iota z. This 2 will cancel here. And now let us simplify this. So if we simplify this, and this is again now a complex integration along a closed curve. So this is now, after simplification, we can get that this is equal to dz divided by 2z square plus 5 iota z minus 2. And if we factorize this quadratic equation, or you can use the quadratic formula, you will get that this is equal to dz divided by 2z plus iota into z plus 2 iota. And now we can see that here f of z is equal to 1 over 2z plus iota into z plus 2 iota. So for singular points, we have to put the denominator equal to 0. And if we simplify this, from here we can get that z is equal to minus iota by 2. And from here we can get that z is equal to minus 2 iota. Now let us see the closed curve. The closed curve is a unit circle whose center is at the origin and its radius is 1. So you can see that z is equal to minus iota by 2. So let this is minus 1. So half will be here. So z is equal to minus iota by 2 lies inside the circle, but z is equal to 2 minus 2 iota. So this point is z is equal to minus 2 iota, which is outside of the given circle. So we have to find the residue at this point, and we can see that z is equal to minus iota by 2 is a simple pole of the given function f of z. So we have to find the residue. The residue of f at the point minus iota by 2 is equal to 2z plus iota n to f of z at the point z is equal to minus iota by 2. Let us put the value of f of z. So we can get 2z plus iota. F of z is equal to this thing. So we can write that this is equal to 2z plus iota into z plus 2 iota at the point z is equal to minus iota by 2. Now this will cancel with this one, and now we have to put z is equal to minus iota by 2 here. So if we put here and simplify this, we can get that this is equal to 2 divided by 3 iota. And next we have to use the residue theorem. So according to the residue theorem, now you can see that our integration is from 0 to 2 pi dt divided by 5 plus 4 sin t is equal to contour integration of the function f of z dz, and by the residue theorem this is equal to 2 pi iota residue of the function f at the point minus iota by 2, and let us put the value of residue, which is 2 divided by 3 iota. Iota will cancel with iota, and we can get that this is 4 pi by 3. So this is the required solution of the given problem. And now finally I would like to give you some homework. The homework is use the method which we have discussed in this lecture and evaluate all these integrals. The answers are given. So till the next lecture, Allah Hafiz, Assalamu alaikum. Fourier series, we shall study periodic functions, even functions and odd functions. So let us start from the definition of a periodic function. We say that a function f of x is periodic if f of x plus p is equal to f of x, where p is a positive number and is called the period of f of x. So if we are given a function f of x, we have to just replace x by x plus p and solve the function. And at the end, if we get the same function f of x, we will say that f of x a periodic function. Let us see this example. Show that 2 pi is a period of sine x. Now to show that this is a period of sine x, we have to replace x by x plus 2 pi. So from f of x equal to sine x, we can get f of x plus 2 pi, which is equal to sine of x plus 2 pi. And now let us just expand this formula. We can get sine x cos 2 pi plus cos x sine 2 pi. Now we know that cos 2 pi is equal to 1. The value of cos 2 pi is 1 and the value of sine 2 pi is 0. So this term is 0 and we can get that f of x is equal to f of x plus 2 pi is equal to sine x. And you can see that sine x is f of x. So in other words, we can get that f of x plus 2 pi is equal to f of x. And this implies that f of x is equal to sine x is a periodic function of period 2 pi. Now let us see the definition of odd function and even function. Again, if we are given a function f of x, we will replace x by minus x and we will solve this. And after the solution, if we get that f of minus x is equal to minus f of x, we will say that this function f of x is an odd function. And if we do the same procedure but we get that f of minus x is equal to f of x, we will say that this function f of x is an even function. Let us see some examples. The first one is, let f of x is equal to x cube plus x. Determine whether it is an even function or odd function. So what we have to do? Replace x by minus x. So we can get f of minus x is equal to minus x cube plus minus x. And if we simplify this, we can get minus x cube minus x. If I take minus as common, I will get x cube plus x. So we can obtain that f of minus x is equal to minus x cube plus x, but x cube plus x is f of x. So we can get that this is minus f of x. So f of minus x is equal to minus f of x, which shows that f of x is an odd function. Let us take another example, another function. The function is f of x is equal to x power 4. Determine whether it is an even function or odd function. So in a similar procedure, just replace x by minus x. We can get f of minus x is equal to minus x power 4, which is equal to x power 4. And we can get that this is f of x. So f of minus x is equal to f of x, which shows that f of x is an even function. Now let us see the Fourier series. Before the Fourier series, we have studied different types of series like the power series, Taylor series, Maclaurin series, and Laurent series. So now let us see the definition of the Fourier series. If we are given a function f of x, then its Fourier series is a series of this form. Here you can see that n is from 1 to infinity, so we can expand this summation, and similarly here this term is also n is from 1 to infinity, so we can just put n is equal to 1, then 2, then 3, and we can expand this series. But these coefficients a0 is equal to 1 over pi minus pi to pi f of x dx, and the coefficient an is given by this one, which is integration of f of x cos nx. Similarly, the coefficients bn is given by 1 over pi minus pi to pi f of x sin nx dx if the interval is given from minus pi to pi. These three coefficients are called the Fourier coefficients. Now, if we are given a function f of x, how we can find its Fourier series? So first of all, we have to write this as 1. Now for this series we need a0. So we can obtain a0 by using this formula. F of x will be given in the question. Similarly, we have to obtain an, and an can be obtained by using this formula. Similarly, we can get bn by using this formula. So let us solve some examples to obtain these coefficients. Problem number 1. Let f of x is equal to x by 2. Find the Fourier series of this function over the interval 0, 2 pi. To find its Fourier series, first of all we have to write the formula for the Fourier series, which is given by a0 divided by 2 plus summation an cos nx, n is from 1 to infinity, plus summation bn sin nx, n is from 1 to infinity. Let us say this is equation number 1. Now we need a0, an and bn, and by formulas which we have seen, a0 is equal to 1 over pi integration from 0 to 2 pi, the interval is from 0 to 2 pi, f of x dx. So we have to put the value of f of x, and we will get that this is equal to 1 over pi integration from 0 to 2 pi, f of x is x by 2. So x divided by 2, let us take 1 over 2 outside from the integration. And now we have to integrate this term. So if we integrate this, we will get 1 over 2 pi, and integration of x is x square divided by 2. The interval is from 0 to 2 pi. Now we have to put the intervals. So 1 over 2 pi, and let us put 2 pi here, so we will get 4 pi square divided by 2 and minus 0. Now 2 2's are 4, and this 2 will cancel with this one, and 1 pi will cancel, so we can get that this is equal to pi. So a0 is equal to pi. Next we need an. So we know that an is equal to 1 over pi. Integration is from 0 to 2 pi. f of x cos nx dx. Let us put values. So if I put values, I will get 1 over pi. Integration is from 0 to 2 pi. F of x is x by 2. So again I take 1 over 2 as common. I will write x here, and this is cos nx dx. And now let us integrate this, so we can use integration by parts. This is first function, this one is second function. So we get 1 over 2 pi. First integration of the second. X integration of cos is sine. So we can get sine nx divided by n. And the limits are from 0 to 2 pi. Minus big integration. This is okay, 0 to 2 pi. And differentiation of first, integration of second. We can get sine nx divided by n into dx. Now let us put these values. We can get 1 over 2 pi. This will be 2 pi, and from here we can get sine 2n pi minus this term is 0 and whole divided by n. And this one is minus, let us take 1 over n as common. So we have to integrate sine nx. Integration of sine is now minus cos. So I can write that this is minus cos nx divided by n, and the limits are from 0 to 2 pi. Let us take minus as common, so this will become plus. But look at here, sine 2 pi is 0. So sine, if we put n is equal to 1, 2, 3, any number, we can get that sine 2n pi is 0. So from here we can get that this is 1 over 2 pi and this term is 0. And let us take this minus minus is plus, this is 1 over n square. And now let us put the limits. So if I put the limit cos, I will get cos 2n pi minus cos 0. And this is equal to 1 over 2 pi, this is 0. And from here you can see that cos 2n pi is equal to 1. Cos 2 pi is 1. So if I take cos 3 pi, cos 4 pi, cos 6 pi, cos 8 pi, we get 1. So this is 1, sine 0 is also 1. So 1 will be cancelled with 1, this is 0, and 0 multiplied with anything is 0. So we get that an is equal to 0. This is the value of an. Now finally we have to get the value of bn. Now bn, to obtain bn, we know that bn is equal to 1 over pi integration from 0 to 2 pi f of x sine nx dx. Let us put the value of f of x, which is equal to 1 over pi, and here we can get 0 to 2 pi, and this is x by 2. Again I take 1 over 2 outside, so I get x sine nx dx, and we can now integrate this by parts. So to integrate this by parts, we can get that this is equal to 1 over 2 pi. First integration of second is minus cos. So I can write cos nx divided by n, and I take minus as common here. and limits of integrations are 0 to 2 pi. Minus big integration, differentiation of first, integration of second is again minus cos nx divided by n, but I write minus here, so it will become plus. And now let us put these values. So we get that this is equal to 1 over 2 pi, and if I put 2 pi here, I will get 2 pi. This one is cos 2n pi, and the other term is 0. And this 1 over n, let us take 1 over n here. And plus this is 1 over n. Now integration of cos nx, this is equal to sin nx divided by n. Limits are from 0 to 2 pi. From here we can see that cos 2 pi is 1. So cos 4 pi, cos 6 pi, they are 1. So the value of this is 1. We can get that this is equal to 1 over 2 pi, and this is minus 2 pi divided by n. And from here 1 over n, 1 over n, we can write 1 over n square. If I put 2 pi here, I will get sine 2n pi minus sine 0. But we know that sine 2 pi, 4 pi, 6 pi, they are 0. Sine 0 is also 0. So this is 0. This one is also 0. And we can get that this is equal to 1 over 2 pi into only this term, 2 pi divided by n. So this will cancel with this one, and we can get that Bn is equal to minus 1 over n. And now let us put values in equation number 1. So I can write that 1 implies f of x is equal to a naught divided by 2. So what is the value of a naught? The value of a naught was pi, so we can write pi divided by 2. A naught is equal to pi, so we can write pi by 2, and plus the value of, you can see the value of an is 0. So if the value of an is 0, if I put 0 here, multiply 0 with anything is 0, and I will get 0. Next term is summation Bn, where n is from 1 to infinity, and we know that Bn is minus 1 over n. So I have to write minus 1 over n here, and sine nx. So if I simplify this, I will get f of x is equal to pi by 2 minus summation sine nx divided by n, where n is from 1 to infinity, and this is the required solution. You can also expand this function. So if you expand the function, just put n is equal to 1 here and here, we can get sine x, plus put 2 here and here, we can get sine 2x divided by 2. Put 3 here and here, we can get sine 3x divided by 3, and plus up to so on. So in some books you can see that the answer is this one. So just expand this, you will get this solution. Problem number 2. Let f of x is given by this piecewise continuous function, and the interval is from minus pi to pi. Then find its Fourier series. So the method is same like the previous example. First of all, we have to write the formula. F of x is equal to a naught divided by 2 plus summation. N is from 1 to infinity. A n cos nx plus summation. Bn sin nx. Let us say this is our equation number 1. So now we have to find the value of a naught, an and bn. Let us start from a naught. A naught is equal to 1 over pi. Integration is from minus pi to pi. F of x dx. But we can see that the function is splitted between two values. So we can write that this is equal to 1 over pi. Integration is from minus pi to 0. The first interval from minus pi to 0. F of x dx plus 1 over pi. The second interval from 0 to pi. F of x dx. Now let us put values. 1 over pi. Integration is from minus pi to 0. From minus pi to 0, f of x is 1. So let us put its value. So this is 1 dx plus 1 over pi integration from 0 to pi. From 0 to pi, the value of f of x is 0. So 0 dx. Now integration of 0 is 0. So 0 multiplied with anything is 0. This will cancel. And we can get only 1 over pi integration from minus pi to 0, 1 dx, because the other term is 0. Now let us integrate this. So integration of 1 is x. Limits are from minus pi to 0. Let us put the limits. We can get 0 minus of minus pi, which is equal to 1 over pi into pi. They will cancel and we can get that a naught is equal to 1. This is the first value. Now we have to obtain the value of an. An is equal to 1 over pi integration from minus pi to pi f of x cos nx dx. This is formula for an, which you have to remember. And from here I have to split the limits. I can get 1 over pi integration from minus pi to 0 cos nx dx plus 1 over pi integration from 0 to pi f of x cos, this is f into cos nx dx. But we know that value of the function from minus pi to 0 is 1. So I have to write 1 cos nx dx. And the value between 0 to pi is 0. So 0 multiplied with anything is 0. So the other term must be 0. Now let us integrate this thing. Integration of cos. Differentiation of sine is cos. So integration of cos is sine. So we will write sine nx divided by n. And the limits are from minus pi to 0. Now let us put the limits. We can get 1 over pi. Let us take n as common. So sine 0 and minus sine of minus pi. This is an odd function, minus can come outside, but we know that sine 0 is 0 and sine pi is also 0. So we get that this thing is equal to 0. So the value of an is 0. Now in the next step we have to find the value of Bn. Now Bn is equal to 1 over pi. Integration is from minus pi to pi f of x into sine nx dx. This is formula for Bn which we have to remember. Now let us split the limits because this is piecewise function. So we can write from minus pi to 0 f of x sine nx dx plus integration is from 0 to pi f of x sine nx dx. Now you can write that this is 1 over pi. Integration is from minus pi to 0. F of x in this interval is 1 sine nx dx. And in this interval the value of f of x is 0. So 0 multiplied with anything is 0. So let us integrate only this term. Integration of this term is 1 over pi. And we know that integration of sine is minus cos. So we can write minus cos nx divided by n. The limits are from minus pi to 0. Let us put the limits. Take minus is common. We can write that this is equal to minus 1 over n pi. And now let us put 0. Cos 0 minus cos of minus n pi. Cos is an even function, so cos minus n pi is cos plus n pi. And from here we can get that this is 1 over n pi and cos 0 is 1 minus cos plus n pi. Because here I have to write something like cos n pi. If I put 1 here, this will be cos pi, and cos pi is minus 1. If I put 2 here, this will be cos 2 pi, and cos 2 pi is plus 1. Cos 3 pi is minus 1, cos 4 pi is plus 1. So you can write that this is actually 1 if n is even and minus 1 if n is odd. But just ignore this thing. Let us write these values in the given formula. Now the given formula is, let us put these values in 1. The given formula is f of x is equal to a naught by 2. You can see f of x is equal to a naught by 2 and the value of a naught is 1. So I will write that this is equal to 1 over 2 plus summation a n cos nx, but a n is 0, so this term will be 0, plus summation bn. The value of bn is this one. You can see from here. Just put this value. We can write that this is equal to minus of 1 over n pi into 1 minus cos n pi into sine n pi. Let us simplify this a little. So f of x is equal to 1 over 2. I take minus 1 over pi as common. I will get minus 1 over pi, and this is summation, n is from 1 to infinity, and 1 minus cos n pi divided by n into sine, this is nx, sine nx. So this is the required solution or the required Fourier series. But if we expand this, we can simplify this a little more. We can get 1 over 2 minus 1 over pi. This is common. If I put 1 here, cos of pi is minus 1. So minus minus will be plus. So we can get 2 sine x plus. If I put 2 here and here, cos 2 pi is 1. 1 minus 1 is 0. So we will get 0 here. Again, if I put 3 here, cos 3x is minus 1. So we will get plus 2 and divided by 3 sine 3x plus. Now if I put 4 here, this will be 0. If I put 5 here, this will be 2 divided by 5 sine 5x plus up to so on. Let us take 2 as common. So we can write f of x is equal to 1 over 2 minus 2 by pi into sine x plus sine 3x divided by 3 plus sine 5x divided by 5 and plus up to so on. So in some books you will see that the solution is this thing. You can just expand this summation and you can get the answer. This lecture is still continuous, so please watch its second part for better understanding of the Fourier series. So till the next lecture, Allah Hafiz, Assalamu alaikum. These are the contents of this lecture. Let us revise the previous lecture, in which we have studied that if we are given a function f of x with a fixed period 2 pi, then its Fourier series is given by this formula. F of x is equal to a naught by 2 plus summation a n cos nx plus summation b n sin nx, where the coefficients a naught, a n and b n are given by these formulas. And now let us generalize this result to the Fourier series of functions with any period p is equal to 2l. In this case, the Fourier series is given by this formula. F of x is equal to a naught by 2 plus summation a n cos n pi x divided by l plus b n sin n pi x divided by l. The Fourier coefficients a naught, a n and b n are given here. You can see that if I replace L by pi, then I will get a period 2 pi, and we can reduce these results to the previous results. Just replace L by pi here, pi will cancel with pi, here pi will cancel with pi, we will get the previous formula. Similarly, if we put L is equal to pi in all of these formulas, we can get previous formulas. So it is better to memorize only these formulas. And now let us use this formula to find the solution of some problems. Calculate Fourier series of f of x defined on minus 2 comma 2, where f of x is equal to minus 1 when x is between minus 2 and 0, and this is 2 when x is between 0 and 2. Here the period is 4. So first of all we have to obtain L. From the given results we know that p is equal to 2l. We should use this formula to find L. Now just put p is equal to 4 The period is 4, so we can write this is 2L is equal to 4, and from here we can get that L is equal to 2. Now let us write the general formula of the Fourier series. F of x is equal to a0 by 2 plus summation n is from 1 to infinity an cos of n pi x divided by L plus summation bn, n is from 1 to infinity, sine of n pi x divided by L. Just replace L by 2, put L is equal to 2 in this formula, and we can get that f of x is equal to a0 by 2 plus summation an cos of n pi x divided by 2, where n is from 1 to infinity, plus summation n is from 1 to infinity bn sine of n pi x divided by 2. Let us say this is our equation number 1. Now we have to find a0, an and bn. Formula for a0 is equal to 1 over L, integration is from minus L to L, f of x dx. Just put L is equal to 2 and we can get 1 over 2, integration is from minus 2 to 2, f of x dx. Now let us split this interval, so we can get 1 over 2, integration is from minus 2 to 0, and from minus 2 to 0 the value of the function is minus 1, plus 0 to 2, and the value of the function in this interval is 2. Now let us evaluate these integrals. a0 is equal to 1 over 2, let us take minus as common, integration of 1 is x from minus 2 to 0, plus let us take 2 as common, and integration of 1 is again x. So we get this thing. Let us simplify. If I simplify, I will get minus 1 over 2, 0 minus of minus 2, so I will get plus 2 here, and here I will get 2 minus 0. And now if we simplify this, we can get that a0 is equal to 1. In the next step we need an. So formula for an is equal to 1 over L, integration is from minus L to L, f of x cos of n pi x divided by L into dx. Just put the value of L, we can get 1 over 2 from minus 2 to 2, f of x cos of n pi x divided by 2 into dx. And from here we can get that n is equal to 1 over 2, integration is from minus 2 to 0. From minus 2 to 0, the value of the integral is minus 1 cos of n pi x divided by 2 into dx, plus 1 over 2, integration from 0 to 2. In this interval, the value of the function is 2 cos of n pi x divided by 2 into dx. And now let us just integrate this thing. So taking minus as common, we can get that this is minus 1 over 2, and integration of cos is sine. So we can write sine of n pi x divided by 2 and this divided by n pi divided by 2. And the limits are from minus 2 to 0. Now we have to integrate. The second or 2 will come outside, they will cancel, so we can get plus integration of cos is again sine of n pi x divided by 2 and this divided by n pi divided by 2. Integration is from 0 to 2. Now we have to put values and it will go outside, so we can write minus 1 over 2 into 2 divided by n pi, and here if I put 0 I will get sine 0, minus if I put 2 here, minus 2 here, 2 will cancel with 2 and I will get sine of minus n pi. Similarly, from this we can get plus, let us take 2 over n pi outside, and we can get, if I put 2 here, I will get sine n pi and minus sine 0. But we know that sine 0 is 0, sine n pi is 0, sine pi is 0, sine 2 pi, sine 3 pi, sine 4 pi, they are zeros. So we can see that this term is 0, this one is 0, the value of this one is 0, the value of this one is 0. So a n is equal to 0. Now we have to find bn. So bn, to obtain bn, we know that bn is equal to 1 over L. Integration is from minus L to L f of x sine of n pi x divided by L into dx. Let us put the value of L. So I will get 1 over 2, here is minus 2 to 2, f of x sine of n pi x divided by 2 dx. And now we can write that this is equal to 1 over 2 integration from minus 2 to 0. F of x in this interval is minus 1. And sine of n pi x divided by 2 dx plus integration from 0 to 2. The value of the function is 2 in this interval, and we can write sine n pi x divided by L into dx. And now let us evaluate the integrals. So minus will go outside, we can write minus 1 over 2. Integration of sine is minus cos, so we can write minus cos of n pi x divided by 2 whole divided by n pi divided by 2. Limits are from minus 2 to 0. 2 will cancel with 2, and here again we can get that this is minus cos of n pi x divided by 2 whole divided by n pi divided by 2. Limits are from 0 to 2. And now let us evaluate these results. So if we evaluate these results, we can get that minus will go outside, so we can write 1 over 2, and this is 2 divided by n pi. And now let us put 0 here, so this is cos 0 minus, put minus 2 here, we can get cos of minus n pi. Similarly here minus, and this will go outside, we can go 2 divided by n pi, and now this is cos of n pi and minus cos of 0. So just simplify these results. 2 will cancel with 2, and if we simplify, at the end we can get that this is 1 over n pi into 3 cos 0 minus 3 cos n pi. If I simplify a little more, I can get, just take 3 outside, 3 divided by n pi, and we can get cos 0 is 1, so 1 minus cos of n pi. So Bn is given by 3 by n pi, 1 minus cos n pi, this is Bn. Now let us put values in 1. So if I put values in 1, I will get f of x is equal to a naught by 2, but a naught is 1. So we can write 1 over 2 plus. We know that an is 0, so this term must be 0, plus summation n is from 1 to infinity Bn. Bn is 3 divided by n pi into 1 minus cos of n pi into sine of n pi x divided by 2. If I simplify a little more, I can get 1 over 2 plus, just take 3 by pi outside. So we can get summation 1 minus cos n pi divided by n sine of n pi x divided by 2. And this is the required solution for the given problem, where n is from 1 to infinity. If we evaluate this summation, we can get that f of x is equal to 1 over 2 plus 3 by pi. Let us put n is equal to 1 here. If I put 1 here, cos pi is minus 1. So this will be 1 plus 1. So we can get 2 and sine pi x divided by 2. Now let us put n is equal to 2 here. This will be plus 1, so we will get 0 from this term. Now again, let us put n is equal to 3 here. So cos 3 is minus 1, so again we can get 2 divided by 3 sine 3 pi x divided by 2. Similarly, we can get the next term will be 0, and the next one will be 2 by 5 sine of 5 pi x divided by 2 plus up to so on. If we just rearrange, we can write it in a proper form, 1 over 2 plus, taking 2 common, this will become 6 by pi, and we can get sine pi x by 2 plus sine 3 pi x by 2 whole divided by 3 and plus sine 5 pi x by 2 whole divided by 5 plus up to so on. So this is the required solution for this problem. Even and odd functions. Even and odd functions play an important role in the calculations of Fourier series. In the previous lecture, we have studied that if we are given a function f of x and we replace x by minus x and simplify, as a result, if we get that f of minus x is equal to f of x, then f of x is called an even function. So x square is an even function. You can take f of x is equal to x square and repeat this process. You will get f of minus x is equal to f of x. X power 4, x power 6, any x to the power even number is an even function. Similarly, remember that cos x is an even function. So this is now an important result, that if f of x is even, if this function f of x is even, then we have this important formula, that integration from minus L to L f of x dx is equal to 0 to L f of x dx. It means that if we are given minus 1 to 1 or minus 2 to 2 or minus 3 to 3, then this thing is equal to multiply with 2 and just replace these limits from 0 to L. If you take f of x is equal to x square and you take any limit just like minus 1 to 1 and evaluate this thing, also evaluate this thing, you will get that both sides are equal. So we have to remember this formula, and I will call this formula as even formula. Now let us see the odd functions. In the previous class again we have studied that if f of minus x is equal to minus f of x, in that case f of x is called an odd function. So x is an odd function, x cube is an odd function, and similarly remember this thing, that sin x is an odd function. Now if f of x is an odd function, then we have this important result, that integration of that function from minus L to L is equal to 0. I will call this formula as odd formula. So if you take f of x is equal to x and integrate it from minus 1 to 1 or minus 2 to 2 or minus 3 to 3, you will get 0. So don't do the process, just remember this thing, that if we have an odd function, its integration from minus L to L must be 0. Sometime we will be given functions in product. So we will apply these rules. Even into even function must be equal to an even function. And if we have odd function multiplied with an odd function, it will be even function. Odd into even must be equal to odd. It is just like the plus minus rule, that plus into plus is equal to plus, minus into minus is equal to plus, and minus into plus is equal to minus. And now we are in the position to define a Fourier series of even functions. Let f of x be an even function of any period. Then how to find a naught? We know that a naught is equal to 1 over L minus L to L f of x dx. But according to the even rule which we have just studied, just multiply this with 2 and replace the limits from 0 to L. So a naught must be equal to 2 1 over L 0 to L f of x dx. Now look at an. An is equal to 1 over L minus L to L f of x cos n pi x divided by L. But you can see f of x is even and cos is also even. So even into even is an even. So the result is an even function. So apply the even rule. Multiply with 2 and replace the limits from 0 to L. So an is equal to 2 by L, 0 to L f of x cos n pi x divided by L. Now look at Bn. Formula is 1 over L minus L to L f of x sine of n pi x divided by L. But f of x is an even function, sine is an odd function. Even into odd is an odd function, and apply the odd rule, you will get that this is 0. So now you don't need to calculate Bn. Just put Bn is equal to 0. So the Fourier series will become like this one: a naught over L plus summation a n cos of n pi x divided by L plus 0. So we don't write the other term. And this series is also called half range Fourier cosine series. And now let us define the Fourier series of odd functions. Let f of x be odd with a general period t is equal to 2L, then a naught is equal to 1 over L minus L to L f of x dx. Now f of x is an odd function, so apply the odd rule, a naught is equal to 0. An 1 over L minus L to L f of x cos of n pi divided by pi x divided by L. Now f of x is odd but cos is even. Odd into even is odd. Apply the odd rule and you will get 0. Look at Bn. Bn is equal to 1 over L minus L to L f of x sine of n pi x divided by L. Now f of x is odd and sine is also odd. Odd into odd is even, so apply the even rule. 2 by L, multiply it with 2 and replace the limits from 0 to L. So now if we are given an odd function, don't evaluate a naught and a n, they are 0. Just evaluate Bn, and the series in this case is given by summation Bn sine of n pi x divided by L. This is also called half range Fourier sine series. Now let us obtain the Fourier series of an odd function. The period of this function is 2 pi. So let us find L. P is equal to 2L. So just put the value of P which is 2 pi. We can get that L is equal to pi. And now you can see that f of x, fi is equal to x, replace x by minus x, we can get minus x, which is equal to minus f of x. So we can see that f of minus x is equal to minus f of x, which says that the given function is odd. And now if the function f of x is odd, we know that in that case a naught is 0. So don't evaluate a naught. In that case a n is equal to also 0. So don't evaluate a n. And the Fourier series in this case can be written as a naught is 0, a n is 0. So this is summation Bn sine of n pi x divided by L, where n is from 1 to infinity. Just replace L by pi. So we can get that this is equal to summation n is from 1 to infinity Bn sine of, if I put pi here, pi will cancel with pi, I will get nx. Let us say this is equation number 1. So now for this equation I need to obtain Bn, and Bn is equal to 1 over L, integration is from minus L to L f of x sine of n pi x divided by L dx. Let us put the value of L. We can get 1 over pi. Integration is from minus pi to pi. This is f of x and sine of n x dx. Now f of x is an odd function and sine is also an odd function. Odd into odd is even. So just reply the even rule. We should multiply this with 2. So this is 2 by pi and integration is from 0 to pi now. F of x sine of nx dx. And now just put the value of f of x. We can get 2 by pi. Integration is from 0 to pi x sine of nx into dx. We have to use integration by parts here. So we can write 2 by pi. First, integration of second. Integration of sine is minus cos. So we can write cos nx divided by n. Let us write minus here. And the limits are from 0 to pi. Minus big integration. Integration is from 0 to pi. Differentiation of first and integration of second, which is again minus cos nx divided by n. So I will write minus here and it will become plus. Now let us put values. So we can get this is equal to 2 by pi. Taking minus as common, I can write pi cos n pi and minus 0 divided by n. Plus let us take n outside, and if we integrate cos, we can get sine nx divided by n, and the limits are from 0 to pi. So let us evaluate this. We can get 2 by pi minus pi cos n pi divided by n plus 1 over n square, and this is sine n pi minus sine 0. Sine n pi is 0, sine 0 is also 0. So we can get only 2 by pi. Let us take minus outside. Pi cos n pi divided by n. They will cancel, and we can get that Bn is equal to minus cos n pi divided by n. So this is the required Bn. Just we have to put this value in 1. So 1 implies that f of x is equal to summation Bn. Bn is minus 2 cos n pi divided by n, and sine nx. N is from 1 to infinity. This is the required solution. Or if we expand this, we can get that f of x is equal to, just put n is equal to 1 here, here in each place, and you can get that the required result will be 2 sine x minus sine 2x divided by 2 plus sine 3x divided by 3 and minus up to so on. Now let us obtain the Fourier series of an even function. F of x is equal to x absolute having a period of 2. So from here we need L. So let us put p is equal to 2 and we can get that L is equal to 1 here. Now f of minus x is equal to minus x absolute, which is equal to x absolute, and this is equal to f of x. So this implies that f of x is even. Now since f of x is even, so we know that in that case Bn must be equal to 0, and the Fourier series can be written as a naught by 2 plus summation an cos of n pi x divided by L, where n is from 1 to infinity. Let us put L is equal to 1, so we can write this is equal to a naught by 2 and plus summation an cos of n pi x. N is from 1 to infinity. Let us say this is 1. So now we have to obtain a naught and a n. But first of all, let us write the function. The function is f of x is equal to x absolute. So it is the definition of absolute function that its value is minus x if x is less than 0. So it means that from minus 1 to 0 it is minus x, and it is plus x when x is between 0 and 1, because the given limits are only between minus 1 and 1. So let us obtain a naught. A naught is equal to 1 over L. Integration is from minus L to L f of x dx. Now f of x is an even function, so we can apply the even rule. Just multiply this with 2, also replace L by 1. So we can write 2 divided by 1, the limit is from minus 1 to 1, f of x dx. Okay, so this will change from 0 to 1 now. If the limits are from minus 1 to 1 and we apply the even rule, so it will become from 0 to 1. And from 0 to 1, the value of the function is x dx. So if I simplify this, I can get 2 x squared divided by 2, integration is from 0 to 1, and if I simplify I can get 1. So in this case a naught is equal to 1. In a similar procedure, let us obtain an. An is equal to 1 over L. Integration is from minus L to L f of x cos of n pi x divided by L dx. First let us put the value of L. So the value of L is 1. 1 by 1 is 1. We can write minus 1 to 1 f of x cos of n pi x into dx. Now f of x is even and cos is even. Even into even is even, so we can apply the even rule. The even rule is multiply with 2 and replace the limits from 0 to 1 with the 0 to 1. So we can write a n is equal to 2, integration is now from 0 to 1, f of x cos n pi x dx. Now let us put the value of f of x. In this interval, the value of f of x is plus x cos of n pi x into dx. Now we shall use integration by parts here. So by integration by parts we can write 2. First, integration of cos. Differentiation of sine is cos, so integration of cos is sine. We can write sine n pi x divided by n. The limits are from 0 to 1 minus big integration from 0 to 1. Differentiation of the first, integration of the second, n pi x divided by n pi into dx. And now we can obtain the result on another page. Let us write an is equal to 2 and put the limits. We can get sine n pi minus 0 divided by n pi, and minus take 1 over n pi is common, and now integration of sine is minus cos. So we can write cos n pi x divided by n pi. I will write minus here, and the limits are from 0 to 1. So let us simplify this thing. Sine pi, sine 1 pi, 2 pi, 3 pi, 0. So we can write that this is 0. So 2, this is 0, plus this is 1 over n square pi square. And here we can get cos of n pi minus cos of 0. So we can get that this is equal to an is equal to 2 divided by n square pi square cos n pi minus 1. And now let us put values in equation number 1. So equation 1 implies that f of x is equal to a naught by 2, and the value of a naught is 1, so 1 over 2, plus summation n is from 1 to infinity an. An is given here, so just write the value 2 by n square pi square cos n pi minus 1 and cos of n pi x. So this is the required solution for this problem. Or you can just evaluate this summation, and if you evaluate you will get that this is equal to, just put n is equal to 1 here and here, then 2, 3, 4. Finally you will get that this is equal to minus 4 by pi square cos pi x plus cos 3 pi x divided by 3 square plus cos 5 pi x divided by 5 square, and plus up to so on. Now at the end I have to give you some homework. So using the method of this lecture you can solve all these problems. The answers are given in front of each question. You can see it. So just solve all these problems for practice. So till the next lecture, Allah Hafiz, Assalamu Alaikum. In this lecture we shall learn the Fourier integral, the Fourier cosine integral, the Fourier sine integral, the Fourier transform, the Fourier inverse transform. So let us start from the Fourier integral. If we are given a function f of x, Then the Fourier integral of f of x defined on this interval is given by f of x is equal to 1 over pi 0 to infinity a of w cos wx plus b of w sin wx, and integration is with respect to w, where the value of a is given by this formula from minus infinity to infinity f of x cos wx dx. B of w is equal to integration from minus infinity to infinity f of x sine of wx dx. This equation 1 is called the Fourier integral formula. It is also called representation of the function f of x in the Fourier integral. So if we are given a function f of x from 2, we have to obtain the value of aw, and from 3 we should obtain the value of bw, and then we have to put these two values in 1, and that will be our required solution. So let us see an example to solve this problem number 1. Find the Fourier integral representation of the function f of x is equal to 0 when x is less than 0 and 1 when x is between 0 and 2 and 0 when x is greater than 2. So to solve this problem, first of all we have to write formulas of the Fourier integral. So formula of the Fourier integral is 1 over pi, integration is from 0 to infinity a of w cos wx plus b of w sine of wx, and integration is with respect to w. The value of a is equal to integration from minus infinity to infinity f of x cos wx dx, and the value of b is equal to integration from minus infinity to infinity f of x sine of wx dx. Now we have to obtain the value of a from 2 and the value of b from 3, and then we have to put these two values in equation number 1, and that will be our solution. So let us do that. From 2 we can see that a of w is equal to, I have to split this interval, integration from minus infinity to 0 f of x cos w of x dx plus integration from 0 to 2 f of x cos wx dx and plus integration from 2 to infinity f of x cos wx dx. But you can see from the function that value between minus infinity to 0 is 0. The value of the function f of x between 0 and 2 is 1, and the value from x is equal to 2 to infinity is 0. So this term will vanish. This term will vanish. So we will get that a of w is equal to integration from 0 to 2. The value of f of x in this interval is 1 cos wx dx. Now let us integrate this. So differentiation of sine is cos. So integration of cos is sine. Sine wx divided by w, limits are from 0 to 2. Now let us put x is equal to 2 here. We will get sine 2w. And now let us put 0 here. We will get sine 0 divided by w. Now sine 0 is 0. So we get that a of w is equal to sine 2w divided by w, and this is the value of a. Now we have to obtain the value of b. So from 3 we can get that b of w is equal to, integration is, again if we split this interval, you will get that the value between minus infinity and 0 of the function f of x is 0. Similarly, the value here is 0. So only we have that the function value is 1 in the interval from 0 to 2. So I can write b of w is equal to 0 to 2. F of x, the value is 1, and sine wx into dx. Now we have to integrate this thing. So the integration of sine is minus cos wx divided by w. Limits are from 0 to 2. Now let us put the limits. So if we put the limits, we can get that, let us take minus 1 over w is common. So if I put x is equal to 2 here, I will get cos 2w, minus if I put 0, I will get cos 0. Now cos 0 is 1, so we can get that this is equal to minus 1 over w cos 2w minus 1. And if I multiply minus inside the brackets, I will get that the value of b of w is equal to 1 minus cos 2w and whole divided by w. So this is the value of b. Now we have to put these two values in equation number 1. So from equation number 1 you can see we can obtain that 1 implies f of x is equal to 1 over pi. Integration is from 0 to infinity, and the value of a of w, the value of a of w is sine 2w divided by w into cos wx plus the value of b of w, which is 1 minus cos of 2w divided by w into sine of wx into dw. And this is the required solution, because the remaining is just simplification. So if we simplify this by putting sine 2w is equal to 2 sine w into cos w, and 1 minus cos 2w is equal to 2 sine square w, then we can get f of x is equal to 1 over pi. Integration is from 0 to infinity, and if we take sine w over w as common, we can get cos w into cos wx plus sine w into sine wx into dw. And from the formula of cos, you can see that this is equal to 1 over pi. Integration is from 0 to infinity, and sine w over w into cos of w into 1 minus x dw, and that is the required solution of the given problem. Fourier cosine integral. To study Fourier cosine integral and Fourier sine integral, we shall use the concepts of even and odd functions, which we have discussed in previous 2 classes. Let us revise 2 properties. That if the function f of x is even, then integration from minus infinity to infinity f of x dx is equal to 2 times integration of the function f of x from 0 to infinity. And if the function f of x is an odd function, then its integration from minus infinity to infinity is 0. One more thing we have to revise, that sine x is an even function and cos x is, sine x is an odd function and cos x is an even function. Now, we have also studied that if we multiply an odd function with an odd function, we get even function. If we multiply even with even, we get even function. If we multiply odd with an even function or even with an odd function, we get an odd function. And now let us start this one, which says that if we are given a problem and in the problem we have a function which is an even function, then how we can find the Fourier integral? We shall use the same method. We know that a of w is equal to from minus infinity to infinity f of x cos wx dx. But you can see that if f of x is even, cos is already even. Even into even is an even function, and we have to use this property of even functions, definite integrals. So this must be equal to 2, 0 to infinity f of x cos wx dx, because this product is even. Similarly, look at b. b is equal to integration from minus infinity to infinity f of x sine wx. Now you can see f is an even, but sine is an odd function. So even into odd is an odd function, and using property number 2 of the definite integral, this is equal to 0. So now you can see we don't need b of w because it is 0 if we are given a function which is even. So the integral formula, the Fourier integral formula, will reduce to this one because the other term is 0. So just we have to evaluate the value of a w, and then we can put the value here and we will get the answer. Let us discuss the Fourier sine integrals. Again, if we are given a question, in the question the function is an odd function, then how we can obtain a and b? Again, a has the same formula, but if f of x is odd, cos is even, so the product is an odd, and we know from this property that integration of the odd function from minus infinity to infinity is 0. Similarly, if we see b is equal to this one, which is the same formula, but f is odd, sine is also odd. Odd into odd is an even function. So we have to use property number 1, which is equal to 2, 0 to infinity f of x sine wx dx. Now, we don't need a because this is 0, so we have to use the value of b in the given formula and we can get the solution. Problem number 2. Find the Fourier integral representation of the function f of x is equal to 1 when x is between minus a to a and 0 otherwise. To solve this problem, you can see that f of minus x is equal to 1, because f of x is equal to 1. If I put minus 1 here, again I get 1. So f of minus x is equal to f of x, which shows that f is even. Now f is even, so if I obtain b of w, let us write the formulas. B of w is from minus infinity to infinity f of x sine wx dx. Now you can see that f is even but sine is odd. Even into odd is odd, so using the property of definite integral, b is equal to 0, so we don't need to obtain b. We only need to obtain the value of a, and the value of a is given by a of w is equal to integration from minus infinity to infinity f of x cos wx dx. Let us say this is 1. Now if b is 0, what will be f of x? F of x is equal to 1 over pi. Integration is from 0 to infinity a of w cos wx plus b of w sine wx, but b is 0, so we don't need to write this term into dw. This is our required formula for the Fourier integral. So we have to obtain the value of a from 1. So 1 implies that a of w is equal to, integration is from minus infinity to infinity f of x cos wx dx. Now f is even, cos is also even, so product is even, so we have to use the even formula from the definite integral, which says that this must be equal to 2 times integration from 0 to infinity f of x cos wx dx. Now the function has two values. Between minus a to a it has 1 and otherwise 0. So I can write that a of w is equal to 2, 0 to a f of x cos wx dx plus 2 a to infinity f of x cos wx dx. But you can see that the value between a to infinity of the function f of x is 0. So we have only this term. Now let us solve this integration from 0 to a. The value from 0 to a of the function is 1. So we can write 1 cos omega x dx. Now integration of cos is sine wx divided by w. Limits are from 0 to a. If I put the values, I will get sine AW minus sine 0. But we know that sine 0 is 0. So A of W is equal to 2 sine AW divided by W. This is the value of A. Now we have to put this value in equation number 1 to get the Fourier integral representation of the function f of x. So 2 implies that f of x is equal to 1 over pi, integration is from 0 to infinity, 2 sine AW divided by W cos W x into dW. Taking 2 as common, we can get f of x is equal to 2 by pi. Integration is from 0 to infinity sine AW cos Wx divided by W into dW, and this is the required representation of the function f of x in the form of Fourier integral. The Fourier transform. The Fourier transform of a function f of x is denoted by this symbol, and it is defined by Fourier transform of the function f of x is equal to integration from minus infinity to infinity f of x e power minus iota wx dx. If we evaluate this integral, which is with respect to x, we shall get a function of w. That is why it is also denoted by f of w. So this is the formula which can transform a function f of x from the variable in x to another function f of w, which is a function of w. And the inverse Fourier transform of f of w is given by this one, which is equal to 1 over 2 pi. Integration is from minus infinity to infinity f of w e power iota wx dx. And you can see if we evaluate this limit, which is with respect to w, we shall get a function of x again. So here I would like to explain that in some books you can find that the Fourier transform of the function f of x is defined by e for integration from minus infinity to infinity f of x e power minus iota wx dx. This one and this one are the same, but in some books you will find that there is a constant multiplication of 1 over 2 pi. Similarly, Fourier inverse transform of the function f of w is equal to 1 over 2 pi under the root. Integration is from minus infinity to infinity. F of w e power iota wx dw. So here we don't have a root, but in this formula there is 2 pi under the root. So you can use these two formulas to find the Fourier transform and inverse transform, or you can use formula number 1 and 2 to find the Fourier transform and the Fourier inverse transform. I shall use in this lecture formula number 1 and 2. And if you use formula number 1 and you want to get similar answer, just multiply with 1 over 2 pi under the root and you can get the answer obtained by this formula. But just ignore these two formulas, concentrate only on these two formulas. So first of all, let us concentrate on the Fourier transform. Problem number 3. Find the Fourier transform of the function f of x, which is equal to 1 when x is between minus a and 0 otherwise. To find the Fourier transform, we know that the Fourier transform of a function f of x is defined by integration from minus infinity to infinity f of x into e power minus iota wx dx. Now, if we split these limits, we can get that integration from minus infinity to a f of x dx plus integration to minus a, because this is from minus a to a, and then integration from minus a to a f of x, this one is e raised to power minus iota wx, e raised to power minus iota wx dx plus integration from a to infinity f of x e raised to power minus iota wx dx. But we can see that the value from minus infinity to minus a of the function f of x is 0, so this one is 0. Similarly, the value from a to infinity is 0. So we only have integration from minus a to a f of x e raised to power minus iota wx dx. So let us evaluate this. Between minus a to a, the value of this function is 1. So we can write that this is equal to minus a to a 1 e raised to power minus iota wx dx. Now we have to integrate this. So we can get that f of w is equal to e power minus iota wx divided by minus iota w, and the limits are from minus a to a. Now let us put the values. So if I put the values, I will get 1 over iota w. I am taking minus 1 over iota w outside. So we can get e power minus iota AW and minus e raised to power, if I put minus a, I will get iota AW. If I multiply minus inside the brackets, I will get f of w is equal to 1 over iota w into e raised to power iota AW minus e raised to power minus iota AW. So this is the required solution, but we can simplify this a little more, and from the Euler formula we can obtain that e power iota AW is equal to cos AW plus iota sin AW. And if we have minus here, minus, we will get cos AW minus iota sin AW. Let this is 2 and this one is 3. So I have to obtain the value of this thing. So let us subtract 3 from 2. So if I subtract 3 from 2, I can get e power iota AW minus e power minus iota AW, which is equal to, if I subtract they will cancel, here I will get 2 iota sin AW. Now let us put this value in 1. So 1 implies that f of w is equal to 1 over iota w, and the value of this is 2 iota sin AW. Now iota will cancel with iota, and we can get f of w is equal to 2 sin AW divided by w, and this is the required solution. Now if you use the other formula, you will just multiply here 1 over 2 pi under the root. So you will get similar solution. So we have obtained that if we are given a function f of x equal to this one, then its Fourier transform is given by this one. Now if a is 1, we are given another question in which f of x is equal to 1 if x absolute is less than equal to 1, and 0 when x absolute is greater than 1. We will get the same solution, but just we have to replace a by 1 here. Similarly, if we are given this question in which a is 2, the solution will be the same one, but we have to replace a by 2. And if we are given a function f of x of the same form, but x absolute is less than 3 and 0 when x absolute is greater than 3, so we will get the same solution. F of w is equal to 2 sine of AW, but a is 3, so we have to write 3w divided by w, and so on. Now let us solve another problem, problem number 4. Find the Fourier transform of the function f of x equal to 0 when x is less than 0, and e power minus ax when x is greater than or equal to 0. A is a positive number. So here we have to write formula of the Fourier transform, which is equal to integration from minus infinity to infinity f of x e power minus iota wx dx. Now I have to split these limits. I can write integration from minus infinity to 0 f of x e raised to power minus iota w plus integration from 0 to infinity f of x e power to dx. Now you can see that the value when x is less than 0 of the function f of x is 0. So this value is 0. So we have integration from 0 to infinity f of x e power minus iota wx dx. And in this interval, the value of the function is e power minus ax into e power minus iota wx dx. Bases are same, so I can write that this is equal to integration from 0 to infinity e power, let us take minus as common, I can get a, x is also common, a plus iota w into x dx. And now let us integrate this. So if I integrate this, I will get that its integration is e power minus a plus iota wx divided by minus a plus iota w, and limits are from 0 to infinity. Let us simplify this. I have to take this as a common, minus 1 over a plus iota w. And now I can write this thing 1 over e power a plus iota wx, limits are from 0 to infinity. Now if I put infinity here, e power in infinity is infinity, and anything divided by infinity is 0. So I can get that this is equal to minus 1 over a plus iota w, 0 minus. If I put 0 here, e power 0 is 1, so I will get 1 here. So the solution is f of w is equal to 1 over a plus iota w. This is the required Fourier transform of the given function f of x. You can see f was a function of x, but its transform is another function which is a function of w. Again you can see that if we are given e power 1x, we have to just put 1 here. If we are given e power minus 2x, we have to put 2 here, and so on. Now let us solve another important problem. Find the Fourier transform of f of x is equal to e power minus ax square, where a is greater than 0. In a similar procedure, we have to write formula for the Fourier transform, which is given by integration from minus infinity to infinity f of x e power minus iota wx dx. And now if I put the values, the value of f of x, I will get integration is from minus infinity to infinity, and the value of this function is e power minus ax square into e power minus iota x dx. You can see bases are same. So I can write that this is integration from minus infinity to infinity e power, let us take minus as common, I can get ax square plus iota wx dx. To solve this problem, let us explain something. We know that integration of e power minus x square, let us take this t, e power minus t square dt, integration is from minus infinity to infinity, is equal to 2 times integration from 0 to infinity e power minus t square dt, because e power minus t square is an even function. So from the property of definite integral, we can write that this is equal to 2, integration is from 0 to infinity e power minus t square dt. And now we have to remember that integration from 0 to infinity of e power minus t square dt is equal to under the root pi divided by 2. So they will cancel and we can get pi under the root. So what we have to do here? We have to make these two terms as square. We have to convert ax square plus iota wx square to another formula, which is something whole power square. So by adding and subtracting, we can obtain that this is integration from minus infinity to infinity e power minus, let us take a as common also, so I will get x square plus iota w divided by ax into dx. From this we can obtain e power minus a x square plus iota w divided by ax. Let us add iota w divided by 2a whole square and let us subtract iota w divided by 2a whole square into dx. And now you can see that this is a formula, integration from minus infinity to infinity e power minus a, and here I can write that this is x plus iota w divided by 2a whole square, and iota square is minus, so minus and minus this will become plus. We can get w square divided by 4a square here into dx. Now let us write in a separate product that this is equal to e power this portion into e power this term. And now we can see that if a is multiplied with here, a will cancel with a, so we will get a here, and taking this as outside from the integration as it is a constant, we can get e power w square divided by 4a. Integration is from minus infinity to infinity e power minus a x plus iota w divided by 2a whole square dx. And now we have to do some substitutions. So by substitutions we can put, this is 1, we can put a under the root into x plus iota w divided by 2a is equal to t. And if I differentiate both sides, I will get that dx is equal to dt divided by under the root a. Therefore, 1 implies, so this one will become f of w is equal to e power w square divided by 4a. Integration is from minus infinity to infinity, e power minus t square. Putting this equal to t, we will get t square here. Dx is equal to dt divided by under root a. Under root a, 1 over under root a will go outside, and now we can use this property. So according to that property, we can get that this is equal to e power w square divided by 4a whole divided by a under the root into pi under the root. And this is the required Fourier transform of the given function. This lecture is still continue, so please watch its part 2 to better understand the concepts.
Mapping a real function. It is a relation between two variables or two sets in which each element of the first set is connected to a unique element of the second set. Let us consider a real function y is equal to x square. To draw the graph of this function, we give values to x. As a result, we get the values of y. If we put x is equal to 0, we get the value of y, which is 0. So we get a point 0, 0. We draw that point on the graph paper, which is the origin here. If we put x is equal to 1, we get the value of y, which is 1. So we get a point 1, 1 and draw it on the graph paper. If we put x is equal to 2, 2 square is 4. So we get another point 2, 4. We draw it on the graph paper. If we put x is equal to 3, we get 9. Similarly, if we put x is equal to minus 1, we get 1. So that is the point minus 1, 1. If we put minus 2 here, we get 4. And we draw that point here, which is minus 2, 4. Similarly, if we put minus 3, we get 9. So we draw this point here. Now we connect these points by a curve, and that is called the graph of this real function y is equal to x square. The set of values of the first variable, which is x, that is called domain. And the set of values of the second variable, that is y, it is called range of this function. The complex mapping has the same definition as that of the real function. The difference is that its domain as well as range will be the set of complex numbers. However, to draw the graph of a complex mapping, it is totally different from the graph of the real function. Because for a complex function, we need a plane in xy, which is two-dimensional plane, and we need another plane in uv, which is also two-dimensional plane. So this is actually a plane of four-dimensional, which is not possible to draw on a graph paper. So what we do, we consider two planes. One is called z plane in xy, the other is called w plane in uv. Now we substitute the value of x1 and y1 here. Let us say the value of x is x1 and y is y1. So we draw that point here. Now putting x is equal to x1, y is equal to y1 in u, we get u1. putting the value of x is equal to x1, y is equal to y1 in V, we get the value of V1. So from this we get a point here which is U1 V1. So we combine or connect this point of the xy plane to this point in the UV plane. Similarly, we give values to xy, we get a point x2, y2 in the xy plane, and with the help of this we get the values u2, v2 in the w plane, and so on. Let us draw the graph of a complex function f of z is equal to z square under the condition that y is equal to 1. Before to draw the graph, we must simplify this function in such a way to get the value of u and v. So we substitute z is equal to x plus iota y on both sides, and then expanding this whole square, and after simplification we get this thing. Now we are given that y is equal to 1, so put y is equal to 1 on both sides. We have f of x plus 1 iota is equal to x square minus 1 plus 2x iota. Now since w is equal to f of z we have obtained it here, and w is u plus iota v. Comparing the real and imaginary parts on both sides, we get two equations. From equation 2, we can obtain the value of x. Substituting this value in 1, we get, after simplification, a relation between u and v. And now we are in the position to draw the graph. First of all, let us consider the z-plane, which is in xy. Now since it is given that y is equal to 1, so we can just draw a straight line passing from y is equal to 1, and that is the graph. On this line, y is 1 but x is changing. The second method is that since z is equal to x plus iota y, but y is given which is 1, so we have z is equal to x comma 1. Now y is fixed which is 1, and giving values to x we get different points. Plotting these points on the graph paper and passing a curve from these points, again we get the same straight line which is passing from y is equal to 1 and parallel to x-axis. Let us draw the graph in the w plane. So we have obtained a relation between u and v. Let us substitute different values of u here. First we put u is equal to minus 1 and we get v is equal to 0. That is the first point, minus 1 comma 0. Let us plot this point on the graph paper. Now substitute u is equal to 0 here. So we get two values of v, plus minus 2. So these are 2 points, 0 comma plus 2, which is this point, and 0 comma minus 2, which is this point. Similarly, we substitute u is equal to 1. We get this point, which is plus minus 2.8. We plot this point on the graph paper. So this is 1 comma plus 2.8, and this point is 1 comma minus 2.8. Now substitute u is equal to 2, we get this point, u is equal to 3, we get this point. Plotting all these points on the graph paper and passing a curve from these points, we get the graph of this relation. And we can see that with the help of a complex function, we transform a straight line parallel to the x-axis from the z-plane to a parabola
in the W plane.
Conformal mapping. Consider a complex function f of z and draw the graph of this complex function. Let us, under some condition, the graph of this function in the z-plane is a curve C1 whose image in the W plane is R1. And under some other condition, the graph of this function in the z-plane is a curve C2 whose image in the W plane is R2. Let us say that C1 and C2 intersect at the point P0, while R1 and R2 intersect at the point P1. So now we can find an angle between C1 and C2 denoted by θ1. And we can also find the angle θ2 between R1 and R2. If the angle θ1 is equal to the angle θ2 in the sense of magnitude as well as direction, then the mapping of this complex function f of z is called a conformal mapping. In the sense of magnitude, we mean that if θ1 is 30 degree, θ2 must also be 30 degree. If θ1 is 45 degree, θ2 must be 45 degree. If we measure θ1 in the anti-clockwise direction, then we shall also measure θ2 in the same anti-clockwise direction. This example can be solved by using the same method which we have discussed in this lecture. That's all.
Of the Z transform. So first of all, let us see the definition of the Z transform. If we are given a sequence xn, then its Z transform is denoted by Z of xn or capital X of Z, and it is defined by Z of xn is equal to summation n is from 0 to infinity xn divided by z power n, where z is a complex variable. Let us recall that the definition of Laplace transform involves an integral, but you can see the definition of the Z transform involves a summation. We can use Laplace transform to solve different ordinary differential equations, and we can use the Z transform to solve different type of difference equations. Another thing which we have to keep in mind is the causal sequence. Let us see its definition. A sequence xn which is from minus infinity to infinity is called a causal sequence if xn is equal to 0 for n less than 0. Let us expand this sequence. If I expand this sequence, I will get x0, x1, x2 and up to so on. On the other hand, I can get x minus 1, x minus 2 and up to so on. A causal sequence has these terms equal to 0. It means that if x of minus 1 is 0, x minus 2 is 0, x minus 3 is 0, all these terms are zeros, then this sequence becomes xn, where n is from 0 to infinity, and this is called the causal sequence. So throughout this lecture we will consider these types of sequences. Now let us remember or keep in mind this definition of the Z transform, which we shall use to solve different problems. Let us start from problem 1. Determine the Z transform of this sequence where xn is equal to c power n, where n is greater than or equal to 0. This c is a constant which may be a real or a complex number. To solve this problem, let us write the definition of the Z transform, which is equal to summation n is from 0 to infinity xn divided by z power n. But we can see that xn is c power n. So we can write that the Z transform of c power n is equal to summation n is from 0 to infinity c power n divided by z power n. And I can write that this is equal to n is from 0 to infinity c divided by z whole power n. If I expand, I can get that the Z transform of c power n is equal to, let us put n is equal to 0, we can get 1. If I put z is equal to 1, we can get c divided by z plus c divided by z whole square and plus c divided by z whole cube and plus up to so on. Now let us recall the geometric series. We know that a geometric series is a series of the form this. If I put the values, I can get a plus ar plus a r square and plus up to so on. So you can see that each term is obtained by multiplying a fixed number to the previous one, which is r. So here the first term is a and r is the common term which we multiply with the previous term and obtain the next one. Another thing, this is an infinite geometric series. So the sum of an infinite geometric series is equal to first term divided by 1 minus r. And we know that the geometric series converges if r absolute is less than this number, which is equal to 1. So we have to remember this thing. Now you can see this is a geometric series. So we can write that this is a geometric series. Here a is equal to 1 and r is equal to c divided by z. So we can sum this series. If I say this is 1, so from 1 I can get that Z transform of c power n is equal to, let us sum this series. We have to write A divided by 1 minus R. R is C divided by Z. And this will converge if this absolute value of C divided by Z is less than 1. From this we can obtain that C absolute is less than Z absolute. Or we can also write that Z absolute is greater than C absolute. So if I simplify this, I will get that Z transform of C power n is equal to Z divided by Z minus C. And this is the required Z transform of the sequence C power n. So you can see that the original sequence was a sequence of x, but its transform is another sequence, another function, which is function of z. We can write that if xn is equal to c power n, then the z transform of Cn is equal to z divided by z minus c, and this is called z transform pair. We have to remember this result because we shall use this result in several places. So let us start to use this result by solving another problem, problem number 2. Now in this problem you can see that we are given xn is equal to 3 power n. So just remember the original. If Zn is equal to c power n, then the z transform of Cn is equal to, just we have written that this is z divided by z minus c, where the condition is that z must be greater than c absolute. So now here you can see that c is equal to 3. So you can see that if I write c is equal to 3, I can write the z transform of 3 power n according to this result as z divided by z minus 3, under the condition that z absolute is greater than 3. Let us solve problem number 3. Again, you can see that in this question c is equal to minus 1 over 3. So I have to use the same result. And I can write that the z transform of minus 1 by 3 whole power n is equal to z divided by z minus c, but c is minus 1 over 3. So I can get that this is z divided by z plus 1 over 3, and if I simplify, I can get 3z divided by 3z plus 1, and this is the required solution. In a similar procedure, we can solve problem number 4. In this problem, we are given xn is equal to minus 1 power n. So you can see that here c is equal to minus 1. Again, using the same procedure, z transform of minus 1 power n is equal to z divided by z minus c, and c is minus 1. So we can write that this is given by z over z plus 1. The condition is that z must be greater than 1. In another problem, let us see problem number 5. We can use the same result again here. You can see here c is equal to e power minus 1. So again we can use the same result. The result is that z transform of c power n is equal to z over z minus c. So let us find the z transform of e power minus n. This is equal to z divided by z minus c, and c is e power minus 1. Condition is that z must be greater than e power minus 1. Let us see problem number 6. In this problem you can see here alpha is a constant. So c here, c is e power minus alpha. Again we can use the same result, and the z transform of e power minus alpha n is equal to z divided by z minus c, and c is e power minus alpha. The condition is that z absolute must be greater than e power minus alpha. Problem number 7. Find the z transform of the unit impulse sequence or delta sequence given by delta n is equal to 1 if n is 0 and 0 otherwise. So to solve this problem, let us write the definition of the z transform of a sequence xn, which is equal to summation n is from 0 to infinity xn divided by z power n. Here xn is delta n, so we can write delta n is equal to summation n is from 0 to infinity delta n divided by z power n. If I expand this sequence, I can get delta naught plus delta 1 over z plus delta 2 over z square and plus up to so on. But from the definition we can see that delta naught is equal to 1. Let us put 1 here. Plus delta 1 is 0. Delta 2 is 0. And similarly all other terms are zeros. So we can write 1. This is 0 plus 0 and plus up to so on. So we can see that the z transform of the impulse sequence is equal to 1. Now let us solve problem number 8. Again we can use the result that the z transform of c power n is equal to z divided by z minus c. Now differentiating both sides with respect to c, we can get that this is equal to d by dc of z divided by z minus c. Here we can use the linear property which we will see after this example, and this is equal to d by dc of z over z minus c. To differentiate c power n with respect to c, we can get n c power n minus 1, which is equal to, if we differentiate this, we can get z. You can use the quotient rule or taking this to the numerator as z minus c power minus 1, and then you can also use the product rule. So by anyhow you will get z divided by c minus z minus c whole square. And now if I put c is equal to 1, I will get that z transform of n is equal to z divided by z minus 1 whole square, and this is the required solution for this problem. Now let us discuss different properties of the z transform. So the first property is the linear property, linearity property. So let us see that what this property says. If we have two sequences xn and yn, then how we can obtain the z transform of axn plus byn, where a and b are any constant, they may be real or complex numbers. So z transform of axn plus byn is equal to a z transform of the first sequence plus b z transform of the second sequence. So we shall use this property to solve different problems. Let us see problem number 9. Find the z transform of 2n of this sequence. To find the z transform of this sequence, we can use the above linear property. According to that property, 2 will go outside, and we have to find the z transform of n, and we have just solved that the z transform of n is z divided by z minus 1 whole square. So we can write that this is equal to z divided by z minus 1 whole square, and that is the required solution. Now let us solve another important problem. Problem number 10. Find the z transform of sine an. A is a constant. So let us write that sine an in the exponential form can be written as e power iota an minus e power minus iota an divided by 2 iota. And now let us find the z transform of sine an. So the z transform of sine an is equal to the z transform of e power iota an minus e power minus iota an divided by 2 iota. Now we have to use the linearity property, and according to that property we can write this is equal to 1 over 2 iota z transform of e power iota an minus 1 over 2 iota and z transform of e power minus iota an. Now we can use the previous result, that z transform of c power n. So here c is e power iota a. So according to that property we can write that this is equal to small z divided by z minus e power iota a and minus 1 over 2 iota z divided by z minus e power minus iota a. And now if I take z over 1 over 2 iota as common, I can get z over 2 iota into 1 over z minus e power iota a minus 1 over z minus e power minus iota a. And now let us take the LCM and simplify this. So if I take the LCM, I can get that this is equal to z over 2 iota, and the LCM will be z minus e power iota a into z minus e power minus iota a. So here I can get z minus e power minus iota a minus z plus e power iota a. Now you can see that these two terms will be cancelled. So I can write z over 2 iota, but let us see this thing. I can write this e power iota a minus e power minus iota a, and this 2 iota will go here and whole divided by, if I multiply these two terms, I can get z square minus z into e power iota a plus e power minus iota a plus 1. And now if I put the values, so you can see that the first one is equal to sine a divided by z square minus z, and this is equal to 2 cos a plus 1, and this is the required solution. So the z transform of sine an is equal to this thing. In a similar procedure, you can prove that z transform of cos an is equal to this thing, and z transform of sine hyperbolic an is this one, z transform of cos hyperbolic an is this one. And you can see that in the hyperbolic formulas you only have a hyperbolic on both sides, the remaining are very similar to each other. So this is your homework. You can solve these three problems. Now let us discuss another property, the first shift property, or the property for the delaying sequence. Let us discuss what is a delay sequence. A sequence of the form xn minus n naught, where n is from 0 to infinity, is called a delaying sequence, where n naught is number of steps in the delay. Let us explain this by an example. If this n naught is equal to 1, then we have xn minus 1, n is from 0 to infinity. If I put 0 here, I will get x minus 1. If I put 1, I will get x naught, and so on. If I take n naught equal to 2, then this sequence becomes xn minus 2. N is from 0 to infinity. If I put 0 here, I will get x minus 2. If I put 1 here, I will get x minus 1. If I put 2, I will get x naught, and so on. So we can see that the sequence xn has just moved backward or delayed 2 steps. These are 2 steps in the backward direction. In this case, there is only 1 step in the backward direction. So n naught is the number of steps in the backward direction. Now, if we are given a delaying sequence, how we can find its Z transform? So let us use the definition of Z transform, which is Z of xn minus n naught is equal to summation, n is from 0 to infinity, xn minus n naught divided by Z power n. This is the definition of Z transform. Here I put n minus n naught equal to m. Then what will be the limits? If n is 0, then m is equal to minus n naught. And similarly from here, I can obtain n which is equal to m plus n naught. If I put these values in this equation number 1, I can get summation m is from minus n naught to infinity xm divided by z power m plus n naught. And if I take 1 over z minus n naught outside, I will get this summation. And you can see xm is a causal sequence. So we can write that Z transform of xn minus n naught is equal to 1 over z power n naught summation m is from 0 to infinity xm divided by z power n. So now let us straightforward define the first shift property. So just ignore these things if you can understand the basic concept. And let us define the first shift property. The Z transform of xn minus n naught is equal to 1 over z power this n naught z n into Z transform of xn. And we know that Z transform of xn is defined by this thing. So we can use this definition to solve different problems. For example, let us see this problem number 11. Determine the Z transform of the shifted sequence xn minus 2, where the causal sequence is given by 1 over 2 power n. To solve this problem, we shall use this definition. So let us write the definition. According to the definition, the Z transform of xn minus n naught is equal to 1 over z power n naught Z transform of xn. Now we can see that xn minus 2. So here I can write Z transform. From this I can obtain the Z transform of n minus 2. So n naught is 2. I will write Z power 2 and Z transform of xn. But xn in this case is given 1 over z square. In the question xn is 1 over 2 power n. So I have to obtain Z transform of 1 over 2 power n. Again I can use the same result, that Z transform of c power n is equal to Z divided by z minus c. Here c is 1 over 2. So I can write this is equal to 1 over z square into c divided by z minus the value of c, which is 1 over 2. Condition is that z absolute is greater than 1 over 2. And if I simplify this, I will get 1 over z square into 2z divided by 2z minus 1. And if I simplify a little more, I can get 2 divided by z into 2z minus 1. And this is the required solution. Now let us see the second shift property. The second shift property, or this is also called the property for the advancing sequence. In the previous sequence, we have xn minus n naught, but in the advancing sequence, we will have xn plus n naught. So let us see that if we are given a single step advancing sequence, xn plus 1, then what will be its z transform? We use the definition of z transform, which is equal to summation xn plus 1 divided by xn. Now just divide and multiply by z, it will become zn plus 1 and z will come here. Now in this sequence, let us put n plus 1 is equal to m. So what will be the limits? If n is 0, m will start from 1. So using these substitution in this sequence, we get that the z transform of xn plus 1 is equal to z summation. Now the limits are from m is from 1 to infinity. Xm divided by z power m. And now let us write add x naught and subtract x naught with this sequence. So if I add and subtract this, you can see from these two terms I can get summation m is from 0 to infinity xm over z power m minus x naught. If I put m is equal to 0, I will get this term. M is equal to 1 to infinity is this term. Now you can see this is the z transform of xm. So if I multiply this z inside, I will get z transform of xm minus z x naught. So this is the first result, that z transform of xn plus 1 is equal to z transform of xn minus z x naught. Now let us take two steps. Xn plus 2 is two-step advancing sequence. Then what will be its z transform? Its z transform will be z square z transform of xn minus z square x naught minus z x1. Similarly, z transform of xn plus 3, we have to multiply this with z. So this will become z power 3, this term, minus z3, this one, minus this will become z square x1 and another term minus z x2. Similarly, if we proceed in the similar way, we can get a general formula that z transform of xn plus n naught is equal to z power n naught z of xn minus summation z power n naught minus k, where k is from 0 to n naught minus 1 into xk here. Now Let us see some more properties. If we denote the z transform of xn by capital X of z, then we have the first result, this one, that z transform of n power m xn is equal to minus z d over dz whole power n m and x of z. X of z is z transform of xn. Another one is z transform of c power n xn. This is equal to z transform of z over c. Similarly, this is called initial value theorem, that limit z approaches to infinity, x of z is equal to x naught, and this one is called the final value theorem, that limit n approaches to infinity, xn is equal to limit z approaches to 1, 1 minus 1 over z, and z transform of xn. Finally, I have to show you a table in which we have obtained these z transform. If xn is c power n, its z transform is this one. Xn is 1, its z transform is this one. Xn is this one, it has the z transform this one. And similarly, you can see we have discussed all these important z transforms. So we have to remember these z transform. In the next lecture, we shall study the inverse z transform and solution of difference equations with the help of z transform. This is part 2 of that lecture. So let us revise the definition of the z transform. So if we are given a sequence xn where n is from 0 to infinity, then the z transform of this sequence is denoted by z of xn, and it is defined as z transform of xn is equal to summation n is from 0 to infinity xn divided by z power n. This is the basic definition of the z transform. And we have seen that when we transform xn, we get another function which is a function of z. So that is why sometime we denote the z transform by capital X of z. In the previous lecture, we have studied several properties of the z transform, in which one property is that if we are given c power n xn, then how we can find the z transform of this thing. So the z transform of c power n xn is equal to capital X of z divided by c. We will use this property to solve some problems, but let us explain this property. This property says that if we have to find the z transform of c power n xn, what we have to do? First of all, we have to find the z transform of xn, which is given by x of z. Now just replace z by c and we can get the z transform of c power n xn, which will be equal to x of z by c, and that will be our required solution. We have solved 11 problems in the previous lecture, and now let us use this property to solve problem number 12, which says that find the z transform of 1 over 2 power n cos alpha n. To solve this problem, we know that from the previous lecture that the z transform of cos alpha n is equal to z square minus z cos alpha divided by z square minus 2z cos alpha plus 1. And now we have to use this property. In this case, you can see c is 1 over 2. So we have 1 over 2 power n. So using this property, we have to just replace z by 2. So z by 1 over 2. So let us write this property that z transform of c power n xn is equal to x of z by c. Here we can see that c is equal to 1 over 2. So let us now we have to obtain z transform of 1 over 2 power n cos alpha n. So what we have to do? We have to just replace z by c, but c is 1 over 2. So we can write, let us put this z or replace this z by c, but c is 1 over 2 here. So we will get this thing, minus z over 1 over 2 cos alpha, and divided by this z is again z over 1 over 2 whole square minus 2 z over 1 over 2 cos alpha. And now if we simplify this, we can get that this is 4z square minus 2z cos alpha divided by 4z square minus 4z cos alpha plus 1. And this is the required solution of the given problem. So we can see, to obtain the z transform of 1 over 2 power n cos alpha n, first of all we have to obtain the z transform of cos alpha n. So you can use the definition if you forget this formula. So just use the definition and you will obtain this transform. Now in the solution, just replace z by z over 1 over 2, and after simplification you will get the solution. Now let us solve problem number 13. Find the z transform of e power minus 2n sine 3n. To solve this problem, again we have obtained the z transform of sine alpha n, or just replace alpha by n. So the z transform of sine 3n is equal to z sine 3 divided by z square minus 2z cos 3 plus 1. If you forget this result, just use the definition of Z transform and you can get this result. Now to obtain the Z transform of e power minus 2n, so sine 3n. So in this case we can see that here C is equal to e power minus 2. So we have to just replace. We replace z by z divided by e power minus 2, which is equal to z e power 2, and we can get the required result, because again here we are using this rule that z of c power nxn is equal to x of z by c. So just replacing z by z e square. So we can get, therefore the z transform of e power minus 2n sine 3n is equal to, replace z by z e square sine 3 divided by, again replace z by z e square whole square minus 2, again replace z by z e square cos 3 plus 1. Now just divide the numerator and denominator both by e power 4, and dividing numerator and denominator by e power 4, we can get that the required solution is z e power minus 2 sine 3 divided by z square minus 2z e power minus 2 cos 3 plus e power minus 4, and this is the required solution of the given problem. Now by using the same techniques, you have to obtain the z transform of e power minus alpha n cos beta n is equal to this thing. Similarly, you have to prove that the z transform of e power minus alpha n sin beta n is equal to this result. So this is your homework. Problem number 15. In the previous lecture, we have obtained the z transform of n is equal to z divided by z minus 1. Here I have to use a different technique to solve this problem. Now to solve this problem, we know that by the definition of the z transform, that this is equal to summation n is from 0 to infinity xn divided by z power n. To obtain the z transform of n, we can write according to this definition that this is equal to summation n is from 0 to infinity n divided by z power n. Now let us expand this summation. If I put 0, I will get 0. If I put 1, I will get 1 over z. Similarly, I can get 2 over z square plus 3 over z cube and plus up to so on. Let us take 1 over z as common from here. So if I take 1 over z as common from here, I can get that this is 1, plus I can write this is 2 z power minus 1 plus 3 z power minus 2 and plus up to so on. Now here we can use the binomial theorem. According to this theorem we can write that this is 1 over z of 1 minus z power minus 1 whole power minus 2. And if I simplify this, I will get that this is equal to 1 over z into 1 minus 1 over z whole square. If I take the LCM of here, the z will be LCM. So if I take the LCM and simplify this a little more, I can get z square divided by z into z minus 1 whole square. This term is 1 over z. Now we can see that they can cancel, so we can get z over z minus 1 whole square, and this is the required solution. And from here you can get the origin of convergence, which is 1 over z must be less than 1, and from here we can obtain that z absolute must be greater than 1. So this is the required solution of this problem. Another important property of the Z transform is that if we have a sequence xn and its Z transform is x of z, then the Z transform of n xn is equal to minus z d by dz x of z. It means that if we are given a sequence of this form nxn, so if we have to find the Z transform of nxn, what we have to do? We have to just obtain the Z transform of xn, and then we have to use this property that Z transform of n xn is equal to minus z derivative with respect to z of x of z. Now let us use this property to solve problem number 16. Problem number 16 is find the Z transform of n square. Now again we know that the Z transform of n is equal to z divided by z minus 1 whole square. Now to obtain the Z transform of n square, we can write that this is given by Z transform of n square is equal to Z transform of n into n. And now we know that the Z transform of n is this one, so we have to use this property. According to this property, here xn is n. So according to this property, we can write that this is minus z d by d z of z divided by z minus 1 whole square. So we have to just differentiate this. If I differentiate this, we can get that this is minus z into minus 1 minus z divided by z minus 1 whole cube. And if I simplify this, I can get that this is z into 1 plus z divided by z minus 1 whole cube, and this is the required solution. Now using the same procedure, you have to solve problem number 17. Problem number 17 is find the z transform of n cube. Then find the z transform of n power 4. This is the required questions and we have to find its solution. So it is all. In this video, we use z transform to obtain the solution of difference equations. Let us see some examples of difference equations. The first example is yn plus 1 minus yn is equal to 1. N is from 0 up to so on. This is called first order difference equation. Let us see another example. Yn plus 2 plus 3 yn plus 1 minus yn is equal to n square. N is from 0 up to so on. This is called second order difference equation. Let us see third example. Yn plus 3 minus yn plus 1 plus 7 yn is equal to 3. N is from 0 up to so on. This is called third order ordinary difference equation. So the highest order is called order of that equation. For example, in example number 3, you can see this is yn plus 3. So this 3 is order of that equation. In the second example, you can see the highest order is 2, yn plus 2. So this is called second order difference equation. Similarly, if we have yn plus 4 plus up to so on, then that equation will be called fourth order difference equation. So we shall use the method of z transform to solve such type of equations. Before to start the solution of some problems, let us revise some useful formulas. The first formula is that we know that the z transform of yn is denoted by capital Y of z. And this is defined by summation. N is from 0 to infinity. Yn divided by z power n. The second important formula is that one, that if we are given a sequence yn where n is greater than or equal to 0, equal to 1, then the z transform of 1 is equal to z divided by z minus 1. We have proved this result in the previous video lecture. Now, if we have another example, let us say yn is a sequence which is equal to some constant. Let us say a power n. N is greater than or equal to 0. In that case, the z transform of a power n is equal to z divided by z minus a. In this case, z absolute is greater than a. And in the above case, z absolute is greater than 1. Another useful result is called the time shift property. Time shift property. According to this property, if we are given yn plus d and we have to find its z transform, then the general formula for this is given by z power d. D is this number which is in the subscript of y, into capital Y of z minus summation. N is from 0 to d minus 1 yn divided by z power n. Now, from this general result, we can obtain several formulas. For example, if d is equal to 1, then just replace d by 1 on both sides of this result, and we can get that the z transform of yn plus 1 is equal to, after simplification, we can get that this is small z y of z minus zy naught. Similarly, if d is equal to 2, just replace d by 2 on both sides of this equation, and we can get that z transform of yn plus 2 is equal to, replace d by 2, and after simplification we can get z square y of z minus z square y naught minus z y1. Key point: to solve a difference equation, we use 4 steps. If we are given a difference equation, first of all, take the z transform on both sides and simplify this. In the second step, put the initial value. In the third step, solve the resulting equation for y of z. It means that keep y of z on one side of the equation and transfer all other terms to other side of the equation. The last step is take the inverse Z transform on both sides. Inverse Z transform on both sides. And simplify. In this way, after simplification, we can get the required solution. So now we are in the position to obtain the solution of a difference equation by using the method of Z transform. In this example, we are given a difference equation yn plus 1 minus 3yn is equal to 4 with the initial condition y naught is equal to 1. And we have to obtain its solution by the method of Z transform. In the first step, we shall take the Z transform on both sides of this equation. So let us do that. Z transform of yn plus 1 minus 3yn is equal to Z transform of 4. And now by the linear property, we can write that this is Z transform of yn plus 1 minus 3 Z transform of yn is equal to 4 Z transform of 1. And now we can use the formula from the shift property that Z transform of yn plus 1 is equal to Z capital Y of Z minus Z y naught minus 3 y of Z is equal to 4, and Z transform of 1 is Z divided by Z minus 1. Now let us put the value of the initial condition y naught, which is equal to 1, and taking y of Z as common, after simplification we can get that this is Z minus 3 y of Z is equal to 4Z divided by Z minus 1, and minus Z, this minus Z will go to other side of equation, so it will become plus Z. Let us simplify this by taking the LCM. So if we take the LCM, we can get that this is Z minus 1, and after simplification, we can get 3Z plus Z square. Now, if we divide both sides by Z minus 3, we can get that Y of Z is equal to Z square plus 3Z divided by Z minus 1 into Z minus 3. Now we can take Z as common from here. So it will become Z into Z plus 3 divided by Z minus 1 into Z minus 3. And now from here we can see that dividing both sides by Z, we can get Y of Z divided by Z is equal to Z plus 3 divided by Z minus 1 into Z minus 3. And here now we can use the partial fraction. So according to the partial fraction, we can get a divided by z minus 1 plus b divided by z minus 3. Let us say this is equation number 1. Now, if we simplify this, we can get z plus 3 is equal to a into z minus 3 plus b into z minus 1. If we put z is equal to 1 in this equation, after simplification we can get that a is equal to minus 2. And if we put z is equal to 3 in this equation, after simplification we can get b is equal to 3. So therefore equation 1 becomes y of z divided by z. This is equal to minus 2 divided by z minus 1 plus 3 divided by z minus 3. And if we multiply both sides by z, we can get that y of z is equal to minus 2z divided by z minus 1 plus 3z divided by z minus 3. And in the last step, we take the inverse z transform on both sides. So by the z inverse of y of z, which is equal to minus 2, z inverse of z divided by z minus 1 plus 3, z inverse of z divided by z minus 3. Now we know that the z transform of yn is capital Y of z. So therefore the z inverse transform of capital Y of z is yn, which is equal to minus 2. Now we also know that the z transform of 1 is z over z minus 1. So the inverse z transform of z over z minus 1 is 1 plus 3. We know that the z transform of a power n is equal to z over z minus a, but here a is 3. So therefore the z inverse transform of z over z minus 3 is 3 power n. And now if we simplify this, we can get yn is equal to minus 2 plus 3 power n plus 1. And this is the required solution of the given equation. That's all.